it's 8:59 and 30 seconds. It says it's preparing, is setting up. Done. And there's a live stream.
Okay, let me bring up.
And okay, so it's in the chat window.
Okay.
And Zoom chat window.
I see you've posted the YouTube live streaming URL as well.
That's what I just said I posted, yeah.
Okay, so Stana, there you go. And so let me go ahead and start with the greetings and the welcomes to everyone, the early birds that have joined us this Saturday morning for the 39th annual ARRL and TAPR Digital Communications Conference. Good morning, good afternoon, good evening. My name is Stephen Bible. I'm the president of TAPR, and it is George going to mute your mic. And it's our pleasure to bring you day 2 of the conference. We completed day 1 yesterday. It was 9 hours and 30 minutes long with about 2 hours worth of breaks inside there. There was a total of about 14 talks, and we only had a couple of minor glitches that we were able to recover from very quickly. So everything's been going pretty well, and we're very happy with it, getting a lot of comments on the Zoom chat window. We're also monitoring the YouTube live stream, live chat channel as well. So go ahead and ask your questions, make your comments in either chat window that you're in, whichever the stream you're involved in on that. So we have our schedule for today. It's up on the website and allow you to be able to follow along. We had one cancellation today, and that was Bob McGuire's talk. And in its place, we got Michelle Thompson's going to be talking. So we still have a full schedule today. And we're going to finish up today with the TAPR annual meeting. We encourage everyone to stick around there. This is where the TAPR officers and the board of directors will be available to give you a very quick status report about TAPR and how it's doing over the past year and what we're looking for going forward, and allow you to ask questions of the officers and the board of directors. So TAPR's mission is to promote the amateur radio state of the art. The Digital Communications Conference is one of many ways that we do that, and we're always open for volunteers and projects and the ability to be able to support others in what they're doing. So let us know how we can help you. So even though we're virtual this year, we wanted to continue the tradition of a proceedings. We did a call for papers. We received 14 papers. 13 of those are being presented yesterday and today by the authors, so we're very appreciative of them. And the total number of pages is over 230 pages. Now, in the Zoom chat window, there's a link where you can go and download the PDF version of it, and this is available to those who are registered on the Zoom channel. And we, of course, will be making all of the talks available on YouTube. The actual contiguous live stream of yesterday is available up there right now. This one, of course, will be available at the end of the conference, and then we're going to slice and dice each one of them into each individual talks, get those edited, and get the supporting materials for those posted as well. So give us some time to do the editing, author the web pages, and get that up there. But as we do with all of our DCCs, we get the information online for everyone to be able to watch and read and continue propagating this technical state of the art that is amateur radio, continuing with our mission. And again, going virtual, we wanted to be able to offer up a printed version of the proceedings. The link is available on the screen right now, and it is going at cost, and that is $9 plus shipping. Of course, there's 2 P's in shipping, if you've noticed. And this price is going to be available for a week to 2 weeks after the DCC. Then after that time, it may go back up to the regular price of $20, but this is the at-cost price for all the ones that want to be able to get an early bird version of it. And it's on a print by demand, and it will take a little bit to get printed and sent off to you, but you will have in your hands a printed version, especially for those that are keeping a collection of all of the proceedings from the DCCs. And finally, we have a survey, and the link is there on the bottom of the page. We encourage you to go there anytime, all the time, as many times as you need to make your comments, good or bad, or suggestions. We're always looking for suggestions. We're also paying attention to the chat window. We're making notes of the suggestions that you have, and we are paying attention. So we want you to know that we're observing. Okay, so let us know what your thoughts are in the chat windows, and we're actively monitoring that. Okay, so with those welcomes out of the way, let's go ahead and take a look at the time. It's about 6 minutes after, and I'd like to introduce the first talk. And this is from Marco Bersani, IK2PIH, and regretfully, Marco has some family affairs that have taken him away from being able to do the live question and answer. If you joined us yesterday, we have each of the talks in a recording. We bring them up, we play the recording, and then we have the presenters available for a live question and answer. So you can actually type your questions into the chat window during the talk, and the presenter can answer them as they come around. At the Q&A time, the moderator will collect the questions and ask the moderator, and then of course everybody will hear the question and the answers with that. So that's kind of how we're producing the DCC this year. So George, are you ready?
I am ready, Steve.
Okay, so let me introduce Marco Bersani, IK2PIH, and his talk is APRS Performance and Limits.
Hello to everybody. I am Marco, IK2PIH, and I am here to show the contents of my paper, APRS Performance and Limits. My paper, as the title suggests, is about the performance of the APRS network, about its limitation, and about new possible arrangements. Almost all users have experienced difficulty using the APRS network due to the congestion that occurs when a fairly limited number of stations send report and messages. In recent years, several strategies have been carried out to improve its performance, but there is not yet an analysis of the efficiency of the system that could serve as a guide to identify the main critical issues and to formulate coherent reorganization proposals. In my paper, I have developed a simple performance analysis of the APRS network, which I used to identify the main problems and propose some alternative solution to the current network. Before going into technical matter, I wanted to report some information about the APRS network and its operation I found on the internet. This part of the document is the more discursive and has an introductory function for all those that don't know about APRS. After the introductory part, I started with the analysis of the access to the shared channel. I reported some basic information about the radio channel capacity and the two contention access methods used in the APRS network, Aloha and CSMA. I tried to summarize the information I found on the internet, trying to present the result in the simplest possible way. First of all, I have estimated the length of a frame, of an APRS frame, 200 bytes, and the overall capacity of the radio channel. And in agreement with several authors, I found that at a speed rate of 1200 baud, you will be able to transmit up to 900 APRS frames for a network cycle of 20 minutes. Then I described the Aloha protocol that is heavily used in APRS networking. The Aloha protocol places heavy limitation on overall traffic maximum 50%, on throughput maximum 18%, and on the probability of communication success 36%. Only at low network loads does communication become reliable. After describing the Aloha protocol, I described the CSMA protocol. The CSMA protocol guarantees superior performance for high load, but only if the collision window is small. But there is a problem. In order to be used by all stations have to listen to each other. In APRS networking is mainly used in terminal to digipeater communication, but not between terminals, because terminals do not listen to each other. After describing the two methods to access the shared channel, Aloha and CSMA, I began to consider an APRS network with a single digipeater. Starting from the expression of the throughput of the Aloha protocol, I obtained a table and then a graph of the throughput in a network with only one ISO frequency digipeater. This was very interesting because I realized that the performance is not much lower than the Aloha case without digipeater, especially at low network loads, and this was a surprise for me. With an Aloha access, you have 18% of throughput with a load of 50%. With a digipeater, you have a throughput of 15% at a load of 42%. That is not much lower. Next, I tried to figure out how to improve the network performance with a single digipeater. And the first idea that came in my mind was to use multiple uplink channels. I concluded that a single digipeater can serve up to 4 uplink channels at the same downlink rate. I also wanted to investigate an unorthodox solution, such as the use of an analog repeater to repeat the APRS traffic, concluding that the performance is not much superior to traditional digipeating, especially at low network loads. In this table, we see that with an offered traffic of 20% of the channel capacity, the throughput in the three situation, CSMA, Aloha, with uplink and downlink on 2 separate channels, and Aloha and an ISO frequency digipeating is not so different. After considering the situation of a network with a single digipeater, I wanted to analyze the impact of several digipeaters on the same frequency. I found that if multiple repetition don't occur, neighboring digipeaters quickly saturate the channel with their disturbance, preventing a local station from accessing the network. In the case of multiple repetition, the probability that a frame will be repeated decrease exponentially as the repetition increase. Multiple routes increase the chance of success, but also increase network congestion. So, at this point, I realized that, in my opinion, the main problem of the APRS network is the presence of ISO frequency digipeaters. I have searched and identified some configuration that don't suffer from this problem, trying as much as possible not to increase the complexity of the necessary hardware and software. The first solution I found is to add a listen-only channel on the existing network. The solution improves local throughput, but degrades communication between digipeaters and thus multiple digipeating. Is better with local traffic, but is worse with the traffic between shells. The best solution I have identified to make a network exclusively via radio is to fragment the network into independent shells operating on different frequencies, connected together by a network of digipeaters operating on another band. In this way, each shell operates at its maximum capacity, and the data transfer between the shells is not affected by the local traffic. Another very efficient solution I found, feasible with current hardware and software, is to use the internet to collect packets by creating an iso-frequency diffuse listen-only network with receiving only high gates. Packet transfer takes place via the internet. Packets of local interest are retransmitted by transmitting only high gate station operating on another frequency, on the same band or on another band, but on another frequency. And that's all. I thank you for your attention and apologize for my English. Goodbye.
And we thank Marco for his presentation. He also has a paper in the proceedings. And in the Zoom chat window, I posted Marco's email address if you would like to contact Marco with some questions or comments. And we're about 10 more minutes before the next talk. So what we'll do is basically take a short break, I think. And then, of course, we're taking a look at your comments. Thank you for the compliments, guys, that his English was good, and virtual applause is much appreciated. Okay, what we struggle with in times like this is dead time. So we don't want people to get unnerved by the quiet time that you're going to be hearing, and probably random conversations between the producers. Scotty, would you like to transfer that over to YouTube, or have you already done that?
What, the link?
Marco's email address. I see you posted it. You copied and
to everyone. Yeah, I'll do that too.
Yeah, George repeated it. You repeated it. So there's a question from Dave Larson. You know, oh, it's actually a statement, but anyway, we're storing all of the chat. So if you want to come back and review, or if you want to invite others to be able to come and watch the recordings, then you will see the chats are actually preserved.
Yeah, I would suggest somebody in the chat just mentioned that some video needs to be on right now to kind of, there you go. There we go. That's better. It was just a Zoom window with a voice behind it.
Yeah, doggone it. Thank you for that. And Freeman, does that include Zoom chat? And the answer is yes. So the entire conference here is being produced on Zoom. And Zoom has a method where the host, which in this case is George, can click on a magic button and it's sent over to YouTube, to the TAPR Digital YouTube channel. So everything's primarily on Zoom. What you're seeing on YouTube is the stream that Zoom is sending over to YouTube. Now, what's interesting is we have a chat window here in Zoom that only the Zoom attendees can see. And then on YouTube, there's its own chat window. So we've got both windows open, and we're sitting here watching the chats go by. And George says, remind everyone to post chat to all panelists and attendees. If just a panelist, the rest of the chat doesn't. The rest of the attendees don't see the question. That's quite correct, George. Thank you for that, because you'll have on Zoom a selection box that says to. And what's interesting is you can message people directly. I found that you can click on the person's name if it's provided as a link, and you can then type a message directly to them. Or you can send it just to the panelist, and the panelists are the ones that are behind the curtain that you see here on the screen, and attendees are those that are observing and part of the audience.
So if I may ask, Steve, since I'm not able to successfully monitor a lot because I don't want to affect the outbound quality of the stream and all that, what's our current count on YouTube, and how are we doing?
Okay, so to answer that, we got 95 participants on Zoom right now, and we got 47 watching on YouTube. So we'll probably notice what we did yesterday. It's a little slow at the beginning. Of course, it is very early on the left coast of North America, and yet there's still, I can see a couple of the California folks are logged in. And I do see the attendees. So Dave New did comment that the attendees don't get an attendees list to click on. So thank you for that, Dave. So that's your viewpoint. It's a lot different than ours here. Okay, so the question from Ed Dunlap. Where is the final recording of the conference going to be placed? YouTube? And the answer is yes, it'll be YouTube. The contiguous recording of day one is already available on the TAPR Digital channel. And when we conclude today, day two, which is today, will be available there immediately as well. And one of the things we're going to do is we're going to slice and dice all of the video into individual talks, put those up on YouTube so that they're searchable, and you can then find the one particular talk that interests you on that, rather than bringing up the one large recording.
And Steve, isn't it fair to say that shortly after the conference is over, all the PDFs will be linked to from the TAPR website for
as
each
we
of
always do?
Yes, as we always do. And the PDF, the link for the PDF of the printed proceedings will also be available on our site after the conference and during the conference is only available on the Zoom chat to participants.
And on the Zoom chat, we've got the question from N9NL, where will the record of the Zoom chat be? So that is recorded into the video. So it will be available as you watch. Oh, I take that back. All right, George, the Zoom chat, how's that going to be preserved? Do we have some thoughts?
It's due to the Zoom crash that we had yesterday, the chat is split into two pieces. But I have the Zoom chat as text files almost immediately afterwards. And I did share them with the rest of the showrunners on our back channel yesterday, immediately afterwards, which raised the topic about trying to preserve, extract and preserve the YouTube chat text as well, which we discussed before starting the conference today.
Okay, so we are preserving both chats. We're preserving the Zoom chat and we're preserving the YouTube chat. We were discussing this morning where we were reviewing the YouTube channel and wondering how we can recover that. So it turns out when you watch it, you can see the YouTube chat. So the question would be how we can get people to be able to view the Zoom chat. So we'll work on that, but suffice to say, we're working on preserving everything. So we're not letting any of the bits fall into the bit bucket.
Yeah, the Zoom chat text files we will place either in our Google Drive we can link to directly from the TAPR website as soon as it's over and we've recovered sufficiently and regained our brain capacity.
Okay. All right. So we're ready to go ahead and tee up the next top. Let's bring Anthony on. Anthony, you want to go ahead and unmute your audio and your video?
Yes. Okay.
And go ahead and do a real quick introduction of yourself and a very short what your talk is about.
Okay. I'm Anthony Lecrane from France. I live near Le Mans now for this 24 hours racetrack. I'm talking about the use of ESP32 microcontroller and to use it for transmit RTTY messages, and with also Wi-Fi and use web browser management to send message. So I didn't program any software for Android or iOS. I directly use my smartphone, and I connect to the Wi-Fi in the ESP32 and download with my web browser a web page and send RTTY message.
That sounds good. And then Anthony mentioned he's in France, so we really welcome him. It's his.
This is, yes.
Yeah, and we got a picture of
Prototype.
it also in your presentation, Anthony.
Okay.
Okay, we're ready to start your
Morning,
presentation.
everyone. I am Anthony Lecrane from France. I live near Le Mans, now for his 24-hour racetrack. Today I am going to talk about the use of the ESP32 microcontroller, and in particular in use of the APRS bus, facilitating the realization of signal processing. The project present in my slide allows to send and receive mini RTTY coded messages. This picture is a good illustration of my interest. I have the French license since 2010 and the general license since 2019. I am not really active on the air, but rather with the soldering tools. I work as an electronics and computer science teacher. Since I got the ham license, I've been having fun building projects around an Arduino. You can see here some projects I have made. Most of them are high-frequency beacon and antenna analyzer. To build a beacon, an Arduino is enough and you don't need much processor power. To decode an analog signal, it's much more difficult. Indeed, it is necessary to apply a filter, a spectral analysis, and to finally find the transmitted binary frame. Doing all of this in an Arduino Uno is not easy. For a few years, I have been working on an ESP32 microcontroller. With the same pinout as an Arduino Uno, it is very easy to connect different shields. The ESP32 can run up to 240 MHz and has a very interesting Wi-Fi connection for embedded system. The ESP32 has two core processors, Wi-Fi management, as well as different communication buses that will interest me for my project. For example, I2C, I2S, UART, and digital analog converter, and also analog digital converter. I made a specific shield to realize my test. It is composed of the DRA818 transceiver and a OLED display. On the bottom, there is some SMD component for level adaptation and filtering. As a reminder, the DRA is a frequency modulation analog transceiver. So I will use the output of the DRA on the analog digital converter input of the ESP32, and the DRA microphone input will be connected on the digital analog converter output of the ESP32. As I said earlier, the advantage of the ESP32 is the Wi-Fi management. The ESP32 is configured as an access point with a web server. The user can send messages using the web browser. There is no specific program in the smartphone. This offers greater versatility. The smartphone is used as a terminal, only keyboard and display, and does not require a 4G connection. The processor has two cores. Core 0 handles digital processing and RTTY decoding, while Core 1 handles the main loop and the web server. This is possible with the RTOS library. RTOS means Real-Time Operating System. The ESP32 can handle multiple tasks in parallel. It works like a turnstile where each task is executed by the core for a fixed time. In my project, I use only 2 tasks, but the microcontroller I can handle more of them. As reminder, the RTTY is encoded in 5 bits with a start bit and 1.5 stop bit. But to make programming easier, I prefer to use 2 stop bits. I use the well-known Bodo table of the RAM users. The signal processing detects the 2 mark and shift frequency of the RTTY transmission. The ESP32 also has a DMA controller. A direct memory access automatically fills the memory with samples from the ADC. This relieves the processor of this tedious task. This is made possible with the use of APRS bus, specially designed for transfer of audio data. To detect the 2 frequency mark and shift, I use the GaN algorithm. That remains this to decode the RTTY character in order to send them to the web server. The RTT encoder is based on a software DDS described in TAPR number 37. They are 2 years ago. The samples are loaded into the DMA, which sends them to the ADC. The web server is composed of 4 HTML pages and JavaScript. A home page allowing to choose your call sign and an option to configure the DRA transceiver and mark shift frequency. The message entered by the user is sent to the RTTY encoder via the web server. The HTML page that manages the sending and receiving of the message makes AJAX, asynchronous JavaScript and XML requests to the server to update the reception area. This reception area is refreshed every 2 seconds. Sent and received messages are also displayed on the OLED display. I tested the project in a real-life situation. My son, Johan, with his smartphone, connects to the ESP32 in the car and sends me a message. I can decode his message either with the same system as him or with a PC software connected to the classic FM transceiver, for example, a Baofeng or my Kenwood directly connected on the PC. I still have work to do on this project. I want to add numeric passband filter on reception. I want also to use 1.5 bit stop. I need to record RTTY configuration for mark and shift frequency. And I want to update this program to APRS user and decode and encode signal. If you want more information about this project, you can send me an email. All my software will be updated on my GitHub soon. And thanks for listening. Goodbye.
Okay, and thank you very much, Anthony. George,
Okay.
can you restart my video, please?
I'm sorry, you're able to start, you should be able to start your video. All panelists have video enabled.
Yeah, I'm getting a pop-up box saying you've stopped it.
There it is.
No, I'm still getting blocked.
Well, there you go this time. I stopped and restarted everybody's ability, so I'm doing what I can.
Okay. Scotty, can you jump in there?
Sure.
There you go. I can see you, but for some reason, okay. Scotty,
so
can you take the questions, please, for Anthony? Anthony, go ahead and bring your audio and video up.
Yes, my audio is on, but not my video.
Okay, we have some questions for you. Can you, even without video, you can still answer the.
My video was blocked by you. Okay.
So while George is working on that, we can take a couple questions. First one is, some folks have complained about RFI from the OLED display. Have you seen any of that in your design?
Okay. Yeah, the OLED display and could check any RFI.
Any RFI from the OLED display on your board?
No, I have no RFI from OLED. Did you see? This is, excuse me, the OLED display. The OLED display is used just for debug software and see messages will be incoming and outgoing. For example, I use my I don't know if you see it. Sorry. I send a message and
okay, back up a little bit from your camera, I think that might.
And the RTTY signal was sending. And the other module, another module can receive it, or for example, a Kenwood or a Yaesu transceiver. This is simple for my student. I want to use RTTY and analog transmission just to study Fourier transform and this, in this case Goertzel algorithm to decode just two frequency for mark and shift. Yes, for two stop bit. Yes, it was more simple to use a two stop bit from to when I start the programming, but I program 1.5 stop bit because the different sample from Goertzel algorithm, for me it is more simple to use a two stop bit. But now my software is available for 1.5 stop bit.
Okay, here's another question. What was the item that had the frequency limitation of 240 megahertz?
The limitation of DRA, I think DRA doesn't support 220 megahertz, but you can easily, you don't need to use DRA. There is a little connector here, and you can connect that to simply a pocket with some wire directly on this board with the pocket, and the DRA is not used.
Okay, and have you tried this on HF using audio data modes?
I try to decode weather data, for example, RTTY weather data for marine traffic. It is more difficult because there is some noise, and I must add some filter to improve decoding. But I think ESP32 can decode easily RTTY messages, or there is no problem. I want also to improve encoding and use convolution encoding and Viterbi decoding like D-star transmission. But it is another step in my study.
Okay, and a question from YouTube. Did you use the Expressive DSP library?
Yes, I use the USP library directly used in Arduino IDE.
Okay.
And FreeRTOS is directly included in the ESP32.
And could you use the same configuration to create an APRS messaging solution?
Yes, I think there is American OM use the ESP32 to decode and encode APRS. I think the software exists for ESP32.
Okay. And another question was, did you try to adapt the algorithms to MicroPython?
Sorry, excuse me.
Did you try to adapt the algorithms to MicroPython? Was the question.
The MicroPython, okay. Yes, I use MicroPython with my student, but MicroPython is not very fast comparatively with C++ programming. I think this is more difficult to adapt this software in MicroPython. I think it is not possible. I need also more resource to use web server, and MicroPython I think is not very a good software platform to decode RTTY analog signal.
Okay. There was another question on YouTube, and they were asking, I'm not sure how you're going to answer this, but what kind of decode performance do you see? I'm not exactly sure what the expected answer is as far what I mean. What is performance?
Alors, the performance, the performance to decode RTTY is very good. I try to use it around my home and send messages with my sound. There is no convolution, no code corrector. I think in the future is the best way to improve the decoding. But now the first objective is to use RTTY decoding. For me, is a simple way to explain for my student how to decode frequency shift keying signal.
Okay, and the question was clarified as compared to say Dire Wolf, and they're asking about bit error rate and the percentage of frames of track 2. Does that make sense to you? The bit error rate is probably most important.
Excuse me.
The bit error rate.
The data rate. Data rate is same as HF transmission. I use 50 baud bit rate transmission. I've not done any test to increase data rate. For the moment, I use only 50 baud rate, but I think I've tried to upper the data rate.
Okay, very good. Thank you. I think that's all the questions I see in the chat windows.
Anthony, you did get several applause and lots of compliments on your talk in the chat window, by the way.
Yes. I write another things. You can see it on my website. This is a tutorial for to use Raspberry Pi in AM project and configure a Raspberry Pi for beginners. But it is another project.
Yes, thank you, Anthony. You sparked a lot of conversation over on the YouTube channel, so there's lots of interest.
Any other questions for Anthony while we have him here?
Don't see any here. Let's see. Nope.
Comment from Donald, great talk. As another ESP32 developer, I really appreciate seeing it used.
Yes, thank you. Thank you, Michael.
Can you give the link, Anthony?
For the moment, my software is not on my GitHub, but I post my software soon on GitHub. My GitHub. My GitHub link.
How about your website URL?
And AM project. AM project here.
Very good. Thank you.
Thank you. So for everyone, Anthony posted his project's URL in the Zoom chat window. We'll transfer that over to the YouTube channel. We're still taking questions for Anthony.
I choose ESP32 also to is a Wi-Fi solution, and I can program a web page inside, and I don't need to use a Android program.
Stephen, could I offer something quickly?
Yeah, go ahead.
Yes, the default setting in the chat window is to send only to all panelists. And for best communication to everybody, you need to ensure that the dropdown is set to all panelists and attendees.
Yeah, and that's what happened when you...
Yeah, and so just make sure in the chat window you're set to all panelists and attendees to send your messages, both attendees and panelists.
We do have a couple more questions. First of all, N9NL is asking how many hours of work did this take you to complete?
I think the project will be finished in 1 or 2 months, and I think I can publish software soon. It's just 1 or 2 months.
Okay, and have you calculated the processing time required for higher baud rate?
No, I only made test in 50 baud rate. I don't test upper baud rate, but I think there will be error. I think I want to make the transmission more robust, and I think I try to use like D-star transmission, convolution, and Viterbi decoding.
Okay, and I want to refine the other question about how long did it take. The question was about the web-based UI. How long did that piece take you? The user interface, the web-based user interface?
I use NetBean, just NetBean IDE development, and I just program HTML, CSS, and Ajax request. I know this language, and it is not a problem for me to program with it.
So how long did you say it took you? How quickly did it go?
Excuse me?
How much time did it take you then to do that web?
How much time? The web page, I programmed the web page in 2 or 3 hours maximum.
Very good.
But I have some sources, donc it is easy for me to copy and paste a sample I have made before.
All right, very good.
Okay, I think we thank you profusely, Anthony. Thank you very much for taking the time out of your day and providing a paper for the proceedings and your talk. It's very much appreciated. You can certainly tell from the activity in the chat room here.
Okay, thank you.
Take care, and we will hopefully see you later.
Yes.
Okay,
Goodbye.
so let's go ahead. We've got Rob Robinette chimed in. Gwen, do you want to go ahead and unmute your video as well?
Hello, good afternoon.
Hi,
Good day
Gwen.
to you all.
And a real quick introduction and a little brief mention of your talk before we start it.
Yes, good afternoon, good day to you all. Gwyn Griffiths, based in Southampton, the UK, and this is a joint presentation, a joint paper as well in the proceedings with Rob Robinette from Berkeley, California. And we've got a shared interest in trying to make the most out of whisper reception data. You can do far more than what you can access using the standard website. But everything that we've done builds on the standard website. I must make that explicitly clear. Without whispernet.org, we wouldn't really be anywhere. WhisperDemon builds on top of that, adds many features, as we'll see in the presentation. We're using a special time domain database and Grafana to produce the graphics.
Sounds like a few tongue twisters in there.
Too many.
Okay, yeah, with all of our technical terms. All right, George will cue it up and play your presentation.
Hello, I'm Gwyn Griffiths. Rob Robinette and I would like at the outset to acknowledge the sterling efforts of Gary, Corey, and the team that delivers the WhisperNet service. Our work builds on their solid foundation. This talk will show, with examples, how a modern time series database and visualization using Grafana can be most helpful to the amateur community using the Whisper digital mode. I'll cover the following topics: our motivation for this work and how it has changed over the last year, since Rob presented early ideas at the 2019 DCC at Detroit. I'll summarize our use of the timescale database and our current hardware, and then delve into several examples of uses, which after all is why we've created this tool. And I'll end with some thoughts on next steps, recalling that this is essentially a two-person part-time effort. The initial idea from Rob for a robust software program, WhisperDemon, to report whisper spots from one or more multi-channel Kiwi SDRs, initially up to 8 channels per receiver, and now up to 14, with Glenn Melmore and others saw the advantages of estimating noise at the same time that Whisper was estimating SNR so that we could get to the signal level. I joined the team and contributed and tested 2 noise estimation algorithms. And by the 2019 DCC, Rob's friend, Tommy Norse, had implemented an influx database for the noise estimates, with Grafana providing some simple graphs. With that success under our belt, we thought it useful to add spots data to the influx database, and also to learn to do it ourselves. So we could add fields not available from WhisperNet. For example, azimuth at the receiver, latitude and longitude as numbers as well as grid squares. The story of why we had to move from influx to timescale is set out in our paper. In summary, influx's indexing methods resulted in very long query response times for the type of data that's there in Whisper, character as well as numeric. It's an issue called cardinality. With that step completed, Rob invested in the hardware needed to gather spots from all users of WhisperNet, not just the users of WhisperDemon. In part, this was to help our own long-term studies to gain access to the entire Whisper dataset from all providers. But it also, we thought, might help WhisperNet reduce the load on their own server, especially that from third-party apps. This is a summary of where we are today. Essentially, the path for WhisperDemon users to WhisperNet is essentially much the same. Reports via HTTP put into the WhisperNet engine. But most of the rest is different. The routes for WhisperDemon users' spot data now gets into the timescale database. There's some initial pre-processing in Bash and Python, and this adds the derived variables. There is now a route from WhisperNet into WhisperDaemon via the API, where we whitelist the existing data and then add the equivalent derived variables before going into the PostgreSQL database, and that has the timescale extensions. All of that data from WhisperDaemon users is mirrored using an FTP to a second backup server, completely independent. That backup server also runs PostgreSQL with timescale extensions and gets its own data from WhisperNet via the API. We also have an arrangement where we bring in third-party data. This is an area we'd like to expand, but for now, the data set that we gather is, for instance, from the Space Weather Prediction Center and the KP Geomagnetic Disturbance Index is what we gather. From the PostgreSQL database, we serve a number of third-party apps. In particular, using Node.js, we have to web users and then to mobile users via Swift and Postgres client kits. And these are users that have come to us because of the added features of WhisperNet. We also serve Grafana dashboards to a number of web app users, and you can also have an old-fashioned command line access using PSQL into the database. Currently, at least to our own knowledge, we're serving data to two well-known apps. First, on the left is the well-known site of VK7JJ, Phil Barnard, where he's added options to construct advanced searches, essentially a form-filling query builder to take full advantage of a direct PostgreSQL interface to WhisperDaemon. In turn, Phil has several hundred regular users, and they're now hitting WhisperDaemon via his app rather than having their load put onto whispernet.org. And another app is WhisperWatch from Peter Marks, VK2 TPM, shown there on the right with some graphic screens from his iOS application with a nice range of presentation graphics from Peter. Let's move on to Grafana so we can look at the data that we've collected. To be honest, I don't find it the easiest or most intuitive of user interfaces, but it has got better with the recent release of version 7. I've written a guide available on the whisperdaemon.org website at this address that goes into the installation details for Grafana on your own machine, or how to access Grafana on the WhisperDaemon server itself. And this is a screen, a startup screen, if you got along to the point of wanting to construct your own dashboard. This is what Grafana looks like. At the bottom left here is a form-filling query builder that knows the syntax for your data source. So it knows the exact syntax for PostgreSQL and gives you prompts as to how to construct a query. Not all of these you will need, and so you will need to remove these when you build up your query, and then by the plus sign, you will then add other clauses onto the bare bones template that you've been provided. Or you can toggle away from the query builder and enter a direct query editor with text entry and just write your SQL as you would for any other machine. You can add a second query down here to show data onto the same panel. You can add panels up here. You give the panel title on the right-hand side. This is where you customize your plot. You can choose your visualization. Do you want a simple line graph? Do you want heat maps? Do you want a gauge type of display? Do you want just a simple digital readout? You choose those in visualization. In display, you customize the options available for you, the colors and so on. In the axes, you will set the limits to the y-axis in particular, choose your annotation, place labels, and so on. On the basis that plots in academic journals are an indication of useful data, let's see how we can obtain an equivalent in timescale database and Grafana, the tools we're using, to this plot on the top left from McNamara et al., published in Radio Science in 2008. This data is 24 hours of signal power received at Boston from the transmissions from CHU, a time signal station near Ottawa, Canada, on the 1st of September 2003. McNamara point out several features. The trough here in signal level, which is during the night time, but during the night there is this episode of sporadic E causing a rise in signal power to that of the highest levels received during daytime. During the day, McNamara points out a trough with a minimum around 1700 UTC, which corresponds to the middle of the day in local time at Boston, and this is due to absorption by the D layer in the middle of the day. The authors also point out that there is more fading, greater dynamic range in the signal level during the day than at night, arising from polarization fading. On the right-hand side, what we have are a series of 3 panels from signals received at KD2OM near Rochester, upstate New York, on the 40-meter band, 7.04 megahertz, from transmissions from N1ZPY in Maine. The upper panel is signal-to-noise ratio, the basic measurement from WSPR, dBm in 2.5 kilohertz bandwidth, from -40 to +40 on the y-axis, and over 2 days. And we see the same essential features as in McNamara et al. We see evidence of sporadic E during the night, 2 episodes on the 24th of August, and this larger amplitude sporadic E event on the 25th. We see a minimum here, this broad minimum here during daytime from the D layer absorption. What we have in the second panel is signal level. Now that's been estimated by taking the WSPR measurement of SNR together with a local measurement of noise level at KD2OM at the same time and at the same frequency band as those WSPR transmissions. And by taking those two together, those coincident measurements, we obtain the estimate of signal level shown here as a heat map in the center panel. Heat maps are also useful for other forms of data. Here are 2 panels that seek to reproduce a figure similar to that in a Ham-Sai presentation by Nathan Frizzell, W2NAF. Our PostgreSQL query selected all receivers in grid squares starting with FN13, New York State again. Actually, the grid square is a Grafana template variable. We can select any grid with reporters in it that's offered up to us here in this pull-down list at the top of the panel. Next, we set a center bearing. In this case, we're interested in those stations with a center bearing of 270 degrees at the receiver. And the next template variable sets the beam width, 40 degrees. So we're looking at plus minus 20 degrees from a heading of 270 from grid area FN13 in New York State. And this map, courtesy of NS6T, shows on a great circle projection the extent of the data set that we're extracting from timescale. So the upper panel is for 14 megahertz and the lower panel for 7 megahertz. And what we're showing in heat map format using the colors from blue to red to show the number of spots received in 200-kilometer range rings spreading out from our grid square of interest, and 20-minute time intervals on the x-axis. So the y-axis has the distance from 0 to 4,000 kilometers, and we've got time incrementing 20 minutes at a time on the x-axis. Of course, we have to keep in mind that the distribution of whisper transmitters over the US is far from even, and that the area covered by each of the range rings expands as the range increases. Nevertheless, these two panels show nicely the contrasting diurnal patterns of propagation on the two bands. And of course, we can select different headings for our telescope, if you like, to study propagation along different directions. Combination of timescale and Grafana can also help us understand conditions at our own station. This is data from my station here in a smallish suburban garden in Southampton, UK. I can just about fit in a pair of 40-meter inverted V dipoles, which I've connected to a homebrew adaptive noise cancellation system. That's G3ZIL. G3ZIL portable is an active vertical dipole antenna, 2 meters tip to tip. It has a fully differential high impedance input buffer and a line driver designed and built by Glenn Elmore N6GN. Using PostgreSQL, we can calculate the SNR difference for each exactly coincident whisper spot received by the two antenna systems, each with their own QESH. The 4-day point cloud in the upper panel is really of limited use. Of more use are the median and the upper and lower quartiles, the upper quartile in blue, the lower quartile in green, on the center panel here. And what becomes immediately clear is that there is a diurnal variation, a daily cycle, but also changes between each day in the differences between the two receivers. So one lesson that's really very clear is that to give very little credence to a claim made, even with an hour of data, that antenna B is XdB better than antenna A. It really does. You need to look at a long data set to be able to really understand the differences between two antennas. Now, as well as its own graphics, Grafana offers third-party plugins. In the bottom panel, I've used Plotly to plot the SNR difference against heading this time from 0 through to 360 degrees. And what we see is a broad minimum here at about 150 degrees. And what that is from is that that's the null that's been steered there by the noise cancellation system. And luckily for me, there are rather few whisper transmitters in that direction here from the south coast of the UK. Let's take now a long view. So far, we've looked at a few days of data at a time. Here, let's look at 50 days. To help us comprehend that quantity of data, I'm using an hourly heat map plugin for Grafana. I'm binning the data into 30-minute intervals along the y-axis. So at the top of the y-axis is 0 UTC, and at the bottom here we have 2359 UTC, and along the x-axis each column represents 1 day. Hours on the y-axis and days on the x-axis. All of the data is from the Northern Utah SDR site at 14 megahertz, courtesy of Clint Turner KA7OEI. The top panel is noise level in dBm in 1 hertz, and the scale goes from -147 in blue to -130 in red. The noise level is highest in the evening local time, with a sudden decrease as the sun sets. There's a slower rise at dawn, and if you squint, you might just convince yourself that there is an increase in the duration of the nighttime minimum noise as we progress from July into August. The second panel is over the same time interval and shows the number of spots in each 30 minutes, from in blue 1 to 350 spots per 30 minutes in red. Here there is a very definite change in the duration of the nighttime minimum from early July into the end of August. We see most spots in the morning and in the afternoon, coinciding with the time of lower noise. We see fewer spots in late evening when the noise is higher and I think as the band closes for stations from the east. The bottom panel is the mean distance of spots received, but we'd really need to look at the median and quartiles of distance and azimuth to be sure of where they're coming from, and of course to look at the raw data. What this shows really is that the higher mean in red here, just before the band closes, is the path from Australia to New Zealand, dominating the mean. Whisper Demon accesses the whispered decoding program written by Frankie and Taylor, and that program has a number of internal parameters that are not sent to whispernet.org. In case they may be of interest to some Whisper high priests or wizards, Rob logs them to the Whisper Demon spots table. Here we show scatter plots of metric on the left and sync quality on the right, both against SNR on the x-axis. All I can say about metric is to quote that it represents closeness of a path to the received sequence. The peak at 810 at an SNR range from -32 to -20 or so is when the primary decoder in Whispered gives up and hands over to the ordered statistics decoder, which will always produce an output, although it may be wrong. And it is only logged if it was previously the call sign in your hash table. Both of these scatter plots show the usefulness of non-parametric density contours. So the contours of high number of values in red out to a lower number of values through the greens and into the blue help pick out the structure in otherwise what would be an amorphous blob of dots. But Grafana doesn't have, at least to date, a plugin with non-parametric density contours. For the immediate future, these are our next steps. Rob is clearly wanting and dearly wanting to find the time to extend Whisper Demon to handle SDRs with a SOAP-y interface, and I'll concentrate on improving the Grafana dashboards, using other forms of graphics, and we both welcome approaches from app developers to consider using Whisper Demon for those with an interest in its particular features and to help offload from whispernet.org. And we'd also dearly like to hear from those with an interest in analyzing Whisper data, so please do get in touch. Thank you very much.
And thank you very much, Gwen. Let's go ahead and bring Gwen and Rob up, audio and video.
I can't start my video here. It doesn't allow me, but I've turned on my mic. Can you hear me?
Okay. Yeah, we can hear you, Rob.
Oh, there we go. Okay, start my video. I'm here.
Okay, and let's get Gwen up there. All right, so some applause on the chat window. Fascinating visualizations, very cool, extremely thorough. Let me make sure. Scrolling very quickly here.
What's the question on historical data, Steve?
Yeah, well, I'm making sure I'm getting things in order here. Phil asked, are there other hidden places in the Whisper decodes where you expect statistics to change, as in the case you mentioned?
Rob, do you want to take that one?
I'm sorry, I missed the question.
Okay.
Start
All right,
again.
here we go. Phil Erickson is asking, are there other hidden places in the Whisper decodes where you expect statistics?
I picked it up now, sorry. But yes, well, we record everything. I'm not understanding all the parameters. That if you look at it, the philosophy of Whisper Daemon is to record everything, all the data produced by the Whisper D binary. So Professor Steve Franke, who develops the Whisper D module that's part of WSJTX, it supplies a binary that's part of that distribution. And his Whisper D utility is we execute that same binary that he supplies. And the function, of course, the source is available, but in contrast with JTX, which and WhisperNet, which only records some of those parameters, we chose to record all of them. We don't really understand. They have names, and I don't think we've invested the time to understand those parameters. There have been several updates to Whisper D in the recent years to increase its sensitivity. And there have been associated with those changes, there have been additional parameters provided by Whisper D for each spot. And we have added fields in our database to record all of them. I think Gwen has a better understanding. His presentation discussed one of those parameters, but there are others we don't. I haven't studied. I don't know what they are. Our idea is that hopefully we'd encourage others who want to understand the algorithm and perhaps improve the sensitivity to study these, do queries and studies, and perhaps it would be a path to further improve the quality of the sensitivity of the algorithm. But that's kind of outside of our purview. We're providing the tools and the data that would allow others to do that work.
Okay, and Phil is also interested in particular in Gwen's statement that the behavior changed at a given low SNR threshold.
Yes, thank you for that question, Phil. I wouldn't say it's an exact threshold. It's a region, and that's what the peak in the metric picks out. I've put in the chat window to everybody a link to a page on the Whisper Daemon website where I have tried to compile definitions of all of the Whisper field names, including these that are hidden to the normal user of WhisperNet. But I would be absolutely delighted to receive any corrections or additions to what I've tried to gather from looking at the open source of those. Specifically on that, yes. So there are the two decoders within the Whispered program, and there is a flag, a 0 or a 1, to indicate which decoder has provided you with the information for each and every spot.
Okay. Tim asked, are you using the PostGIS extension to Postgres SQL to enable efficient geospatial queries?
No. What an excellent question. Life is always a learning experience, and I am continuing on this path, hopefully in a long retirement. No, I have seen it. When we get to mapping, what you'll have seen in the graphics is that they're essentially time series or with another X variable and not geospatial on a map. When we get to that, yes, indeed, I will be exploring that and hopefully using great circle maps, because many of the maps that are out there, Mercator and the radio amateur world is, I think, more of a great circle world than Mercator, at least if you're interested in DX.
Yeah.
Mm-hmm. Okay, great. Comment, such a beautiful data science. Another comment, have a much better appreciation for whisper data after seeing this presentation. Question, oh, okay, Gwen, you posted, and okay, so a question from Dave. Did you say that whispernet.org does not have all historical information? If so, how do you get access to historical whisper?
Okay, I think there are two aspects to that question, and to the response to that question, and part of it perhaps was me trying to rush. Whispernet.org, its normal interface is essentially full data for you for the last 2 weeks. All of the data is there each month or each day, each night. There is a zip file that is updated and you can download. So all of the information, all of the historic information is there in whispernet.org, but the user accessible, easy access data is over 2 weeks or so. And you are limited to a number of spots.
Okay.
There is just to add to that, the we're also learning that there does seem to be some problem with the database, the WhisperNet data, in that now that we have access to the API, the proprietary API, and we can extract based upon sequence spot number, we're finding big gaps in both the last 2 weeks data and in the historical, the zip files for the previous months going back 10 years. Gaps of 200 or 500 spot numbers. Perhaps this is nothing, maybe nothing really is lost. Maybe that's an artifact of some side, processing of the WhisperNets that you're uploading. But one of the studies we'd like to do is we could compare, at least for the Whisper daemon users, make sure that all of our spots actually made it in to Whisper net. And it's not clear, there's no real, at the moment, no real way to validate that your spots have actually made it, okay, short of, and no automated way of doing that. So there's a bunch of data validity and issues that we are worth exploring. But now that we have the infrastructure in place, I could go on for hours on all that subject.
Well, just a note to everyone, we are on break time, so we've kind of officially started the break, so that'll last for about 30 minutes. However, if Gwen and Rob are willing, we'll continue with the questions. We still got several more questions here in the chat window. You guys game for a little more questions and answers?
Of course, yeah.
Okay, Gwen, your audio is muted.
Gwen is
I don't know.
Maybe we lost him.
I think it's a frozen. Yeah, I think it's frozen.
Or his software.
Okay.
Problem. Well, I'll try to. I'll answer what I can. Okay. There he is. Hey, I think Gwen is back.
He's rebooted.
Okay.
So he may be rebooting again.
Okay. Where do you want to list what questions should we answer? Where are we?
Okay. Yeah. Hold on just a second. Looks like we might have Gwen back.
No.
Well,
yes, he's moving. And is he talking?
No, he's frozen again.
I do apologize. Oh.
It's the trusty internet, right? Your ISP.
Okay. Well, so.
Okay, I got some questions. I'll continue with the questions here.
If you're hearing me, I think you better just I think you better.
Gwen, I think what would work best is just mute your video, give your bandwidth to your audio.
Yeah.
Okay, and I think that'll help situation here so we can still hear you.
Yeah.
Okay, question from Roy. Is there a way to save the log2 file as it shows only as a web complete page?
Rob, that's definitely yours.
Oh my goodness, I don't, which logs 2 file are we talking about? I don't, you want to save a web page snapshot? I don't know anything about web programming, so I can't really tell you. I'm sorry.
Okay. Roy, if you want to type into the chat window, let's see here. Roy. Roy, do you want to, I can allow you to talk if you want to come in. Okay, are you there, Roy?
Yeah, hi, Steve.
Yeah,
Yes.
go ahead and expound on your question there.
I was just asking on the logs 2 file that the link was posted above there, you know, like a lot of web pages, when you open them up, you try to save them, they tell you you can only save them as a web dot like MHT or a web complete page, and it doesn't say save it like as a PDF type file. I guess that's kind of where I was getting at, where you can actually have that so you can download it. So that was all.
Yeah. Well, I'm a Macintosh user, and I can go, and you can on Windows. I just copy. I do screen captures if there's some visual page I want to see, and save away a PNG and convert it to JPEG. So that's my response. So that's how I deal with trying to get a save a web page image.
Okay, Roy.
Yeah, that was.
But
yeah,
if you learn another way, please tell us. We'd be happy to learn about.
I've been trying to get around that, just like you might have. I was a Mac user at work for all these years with the Navy contract. So yeah, it can be painful, but it can be workable. So I appreciate your efforts there.
I think actually Windows has a very nice print screen function. You can just bam, and I think now I haven't used Windows much for a while, but Shift or Alt Shift screen will copy off to the currently active window. So I think actually in some ways the Windows is better at saving screens than the Mac is. But anyway, that's
I use a Snippet app that works real well. It's not expensive.
Yeah. We have a number of other questions about us I wanted to address.
Yeah.
So,
okay. Thank you, Roy. I'm going to go ahead and mute you. Next question. How do you know something is sporadic E?
I think that's a response for Gwen, right?
Yes, it's the strength of the signal to start with. So it's happening during the night in that respect. It's the marker of the strength. The duration being limited are the markers. So at on 40 meters, it certainly wasn't anything like very short-lived aircraft reflection or meteor reflection or of that kind. So it's by elimination. By elimination.
Well, okay. Oren asked, what kind of server-side performance parameters are required to run the system?
Well, that was been the subject of the last couple of months. We started out, we implemented this in a cloud server, service, and it's just I paid for a couple of CPUs and 4 gigabytes of RAM, but that was prior to understanding the requirements of a real database. So as we studied it, we realized that, of course, any queries that you're going to do, if they go to disk, even solid state disk, they're going to really slow down. So so we needed a lot more to do more than the last day of quick queries. We needed to expand the memory. So 4 gigabytes of RAM allowed us for quick queries for the last 24 hours. So I built and we decided that and it's frightfully expensive to have a cloud server with you know, tens or hundreds of gigabytes of RAM. So I decided we had to have our own piece of hardware. So I bought a pair of servers, Dell PowerEdge servers, and filled one of them with 192 gigabytes of RAM and a 7 terabyte RAID array. So that has been just deployed at a co-location facility here in California, and will become the primary Whisper daemon server in the next few days. With 192 gigabytes, I'm sure we can do, you know, rapid queries in the last, you know, for at least a month, perhaps 2 months. And then beyond that, of course, queries would have to go to disk. This is a 8 CPU, you know, Xeon server. It's an antique, but still remarkably powerful. But it's startling to see, as probably many of you know, that there's that queries can chew up an amazing amount of CPU time. So I can see that some of Gwen's Grafana queries, where we're looking for the last month for, you know, across many variables, can completely saturate even this 8 CPU system, you know, for seconds at a time. But I think nevertheless, the you know, and we that those sorts of queries are rare, and in normal queries of you know, that people would ask for spots for the last day, week, month, are satisfied in fractions of a second. If you guys go to and use Phil's VK7JJ .com you know, user interface, you know, he'll spend 10 seconds going to WhisperNet to get you know, the last hour. He'll get his responses from us in 100 milliseconds. I mean, most of the delay time in both JJ and the WhisperNet or Whisper Watch application, most of the delay occurs in their software, not in the queries, returning the query data from us. So I think you know, we have orders of magnitude better query performance than you get from whispernet.org. Not to mention we have a real SQL, you know, language database at the same time.
Okay, great. Well, I'm not seeing any questions on YouTube, and there's no other questions.
I did want to, someone was talking about WWV. By the way, one of the things you can use Whisper Daemon, and is being used to do, is to record WWV levels and signal noise ratios. So this is not an application I'd ever thought of or that could be used, but one of our users, Clint, K70EI, came up with the idea of just tuning to WWV as if it were the middle of a whisper band. And it turns out that the decoder actually will output the it will output data about the and record it to our database. So there is WWV historical data coming from, well, from Clint, and could be from other users. So this is, you know, I hadn't really explored it much, but if for those of you who are pursuing WWV data, it might, you know, our database might be a suitable location for you to store your data if you cared to. We'd be happy to support such an application.
Okay, great suggestion. Okay, well, I think this is a good time to go ahead and take a break. So I want to thank Gwen and Rob. Gwen, thank you for your afternoon in your garden. If for all the attendees, we finished the first 3 talks this morning. We got Marco from Italy. I'm afraid he wasn't available due to family commitments. We had Anthony from France, and then we have Gwen here from the United Kingdom, Rob from the great state of California. So let's go ahead and segue into our break time. I'll put up the break slide, and we will see you in about 15 minutes at the top of the hour. And we have Dan Fay on deck. Hi, Dan. There he goes. He's waving, and we'll work on, or I'm sorry, we'll present his talk on QESH. All right, it's break time. we'll see you in about 15 minutes, and go ahead and keep up on the chat room if you like.
Hey, Dan, do you want to test your microphone out since we're on break and just get ready? I've got your presentation all queued up and ready to go in about 15 minutes.
Okay. Do I sound reasonable?
You do. And,
Okay.
and it's a nice front lit video image, and those are always better than the backlit Madonna style images.
Okay, sounds good.
Oh, okay. I think we're ready. Whoever's moderating, I think it's Stana, right after the break, will ask you to unmute about 30 seconds before we're getting started, so you can maybe do your own intro to your own talk, and after we introduce you, and then we just ask that everybody mute their audio and video during the presentation, and if you don't, I can help you. Let's just put it that way.
Okay. All right, sounds good.
Okay, great. So let's just all sit back and let the text chat go crazy and stuff for 15 minutes, and then you'll be up. Thank you very much for your presentation, Dan. Hey, as long as we're on break, CQ, Whiskey 1, Papa, John, Echo, Phil, can we do a sound and video check with you as long as we're on break, since you're in the next group? Mr. Erickson, are you there? Mr. Erickson, are you there?
George, this is Dave. You sound very much like the Apollo people waiting for the capsule to pass through the atmosphere.
Yes, or around the backside of the moon.
That's correct.
Yes, I remember those days. Okay, well, likely Phil's on break, so we'll just, it was an opportunity.
Yes.
Hey, Phil, do you want to do a quick sound check?
Hi, George. 1, 2, 3. 1, 2, 3.
Very good audio, good video. We have your updated presentation.
Oh, and I really appreciate that, George. I'm sorry, my clerical mistake got the better of me.
Hey, these things happen. And fortunately, we're reasonably agile.
Yes, I could tell.
Except I would have missed it because I didn't see the email. I'd already gotten the Google, this whole Zoom thing going, and John pointed it out, so not a problem. So we're under a minute, so I'm going to be quiet so that Stephen and Stana can step in here and introduce the next prezo.
Fantastic.
I'd like to introduce Stana, and she's going to be the moderator for the next 2-hour period here. So take it away, Stana.
Okay, Steve, thank you. First up for our second session today is Dan Fay, KG5 VBY. You want to introduce yourself, Dan?
All right, so quick introduction to me. Name's Dan Fay. I live in Albuquerque, New Mexico in the United States. And what I'm about to present here is really an itch that I found and started to scratch when I was performing some long distance LoRa testing roughly 2 years ago. I actually presented it here in the 2018 TAPR DCC conference. And in the process of kind of scratching this itch and thinking about some aspects of the LoRa waveform, I came up with this idea for QESH, which uses the LoRa waveform to make a novel mesh networking protocol. So without further ado, here's the presentation. I'll be
Hello, my name is Dan Fay. My call sign is KG5VBY, and I will be presenting QESH, a long-range, low-cost wireless mesh network for digital voice communications. So here's some background on who I am. I've been a licensed radio amateur since September 2017. My main interests in amateur radio are special event communications, such as providing communication support for different distance running events like the La Luz Trail Run that's depicted here. I am also interested in the packet radio digital communication side of amateur radio. At the 2018 TAPR DCC conference, I presented a paper entitled Beyond Line of Sight UHF Digital Communications with the LoRa Spread Spectrum Waveform. This paper explored using LoRa on the 70 centimeter band at higher transmit power, approximately 25 watts, and high gain antennas to achieve long distance communications via diffraction and troposcatter. The work demonstrated successful beyond line of sight communications at nearly 125 miles. This distance set a ground-to-ground distance record for LoRa communications. For this talk, I'm going to discuss a project inspired by this work, where I leverage many of the features of LoRa to develop a mesh network that will allow for relaying voice data across multiple wireless devices. Okay, so you're probably wondering what QESH is. Well, QESH happens to be yet another low-power wireless mesh network protocol. Yes, there's many others out there. What makes QESH unique is that, unlike the other common wireless mesh network protocols out there, this one is designed for more than just small bursts of telemetry data. It's designed to support streaming data, including and especially vocoded voice. The protocol is relatively low data rate, supporting at most a few tens of kilobits per second. While this isn't much, it's enough to support vocoded data, which can use a maximum around 3 to 4 kilobits a second. While the primary use case is for vocoded data, QESH also supports moving small amounts of data around, such as location, telemetry, text messages, and so on. QESH is currently based on a specific waveform, and this waveform is the LoRa chirp spread spectrum waveform. At a given power level, this LoRa waveform provides better range at a given bit rate than other modulations such as FSK and PSK. LoRa spread spectrum properties are utilized by QESH to enable its isochronous protocol to work. This slide provides an overview of what MANETs and wireless mesh networking actually are. MANET, which stands for Mobile Ad Hoc Network, describes a network where nodes can arbitrarily join and leave. Key aspects of MANETs are the ability to self-assemble, where new nodes can quickly join and communicate with other nodes on the network, and the ability to self-heal, which means that the network can continue to function with nodes leaving the network. Mesh networking is a non-hierarchical type of networking where nodes relay data until it gets to its destination. There are two major types of mesh networking, routed and flooded. In routed mesh networks, nodes repeat data along a predetermined route. For node-to-node communications, this is more efficient as it eliminates redundant communications. It can also increase the aggregate capacity of the network, as multiple nodes can communicate different data at the same time. A major challenge with routed networks, especially in the context of MANETs, is building and rebuilding routes as nodes enter and leave the network. For large hop counts, such as 6 or more hops, building routes can become intractable. Building and rebuilding routes typically requires additional mesh network traffic to allow nodes to discover their neighbors in order to keep their routes up to date. In flooded mesh networks, every node repeats every message it receives. Doing this vastly simplifies conveying data to its destination, as there is no need to constantly discover and rebuild routing tables. As a result, self-healing is straightforward to implement. Another benefit it provides is that the redundant communications provides backup communications that can improve overall network reliability. While flooding is good for multicast and other one-to-many communications, it is inefficient for point-to-point communications. Now, mesh networks can implement both types of protocols at the same time. Many times, flooding is used for broadcast and node discovery messages, while routing is used to move specific data between nodes. A major problem with flooding and routing in some cases in wireless mesh networks is known as the broadcast storm problem. In the broadcast storm problem, multiple nodes try to communicate at the same time, causing their communications to destructively collide with each other. After collision, the nodes attempt to retransmit the data and once again destructively collide. This process of nearly endless collision and retransmitting causes lots of wireless traffic, but little actual meaningful communication to occur. QESH uses a special form of flooding called synchronized flooding, along with some LoRa-based waveform tricks to mitigate the broadcast storm problem. In synchronized flooding, each node repeats a received data packet at a specific time, and in the case of QESH, all nodes repeat the received packet at the same time. Besides providing a way to mitigate the broadcast storm problem, which I will discuss later, it also provides a way for the low latency streaming bandwidth needed for real-time voice. This slide shows an example of synchronized flooding. At time 0, the originating node produces a packet. This packet is received by the two adjacent nodes. At the next time interval, these nodes will simultaneously retransmit the received data, which will then in turn be received by the final nodes. These nodes will then repeat the packet at the subsequent time interval. Now it is time to provide some background on LoRa. LoRa is Semtech's proprietary implementation of chirp spread spectrum. LoRa is designed for low-power Internet of Things-like devices such as wireless sensor nodes. The most common use of LoRa is to implement the low-power wide area network, or LPWAN for short, protocol called LoRaWAN. A major benefit of LoRa's chirp spread spectrum is that it provides additional processing gain versus other modulation forms such as FSK and PSK. As an example, at roughly 1200 bits per second, LoRa enjoys a 9 dB receive sensitivity improvement versus FSK. Depending on the specific LoRa chipset used, LoRa can support bit rates of up to 62,500 bits per second. In terms of product support, LoRa is becoming increasingly popular as the LoRaWAN LPWAN standard becomes more popular. Many companies make LoRa modules for integration into other designs. The most commonly supported amateur radio bands of these modules are the 33 centimeter band and the 70 centimeter band. LoRa communications can be parameterized along 3 major degrees of freedom. The first one is the spreading factor. Each chirp is comprised of a series of very short tones called chips. The number of chips per chirp is equal to 2 to the power of the spreading factor. Higher spreading factors gives higher RF sensitivity at the expense of a lower data rate. The next LoRa parameter is the modulated bandwidth. LoRa allows for bandwidths ranging from up to 500 kHz all the way down to 7.8 kHz. As expected, narrower bandwidths improve receive sensitivity at the expense of bitrate. The final major parameter is coding rate, which specifies how many redundant bits to use for error correction. Key to the success of the QMesh protocol is the capture effect. The capture effect is where a receiver, upon receiving multiple simultaneous signals, only receives or captures the strongest signal. Receivers that capture signals are generally needed for wireless protocols that operate in unlicensed bands like Wi-Fi and Bluetooth due to the need to coexist with other transmitters in the area. It is important to note that LoRa is a constant envelope modulation scheme that does experience the capture effect. The capture effect means that we can successfully receive collisions if the colliding packets are far enough apart in received power. We can then leverage the capture effect to make synchronized flooding work better. Previous work has shown that synchronized flooding with FSK can be made to work, but the performance in terms of successful packet receipt is not that great. What does work significantly better, however, are spread spectrum techniques. The Glossy project demonstrated that synchronized flooding can be used with the direct sequence spread spectrum implemented in the 802.15.4 PHY. Subsequent work has demonstrated that this effect also works for LoRa. LoRa has some features that can help improve capture success. Conceptually, these features involve moving around the chirps in time and/or frequency so that they overlap less with other chirps. Some of these features include utilizing the frequency separation between chips, leveraging the low chirp or symbol rate, and leveraging the LoRa chipset's tolerance of up to plus or minus 25% of the modulated bandwidth. One technique to reduce the amount of chirp overlap is to randomly wobble the frequency. This can help by both shifting around chirps as well as causing chips to slot in between each other. Another way to shift around the chirps is to add in a timing offset. This requires encoding the timing offset into the packet so that the next node can compensate. It is important to note that the timing offset cannot be shifted by more than half of a symbol period. This is because for larger offsets, a situation can occur where if a weaker packet comes in first, the receiver will lock onto it first, and the stronger packet will not get locked onto and instead just create heavy destructive interference. This slide illustrates the chip-level overlap reduction. The first diagram on the left shows two LoRa signals on completely different channels where there is no overlap whatsoever. The second picture shows two LoRa signals that are completely overlapping. The final diagram shows what the LoRa signals look like when there is a small frequency offset. Note that this frequency offset is quite small, and typically it may be a few tens of hertz. The diagrams here show the two different techniques that are used to reduce symbol overlap. The first two diagrams show completely separate LoRa signals and completely overlapping LoRa signals. The next diagram shows what the two LoRa signals look like when the frequency wobbling is used. The final diagram shows what the two LoRa signals look like when a timing offset is used. Now we can move on to describing the QMesh protocol itself. QMesh is based on a time division multiple access TDMA based protocol, with each time slot being the same length. In QMesh, the transmitter operates at a maximum 33% duty cycle, where the transmitter can transmit at most once every third time slot. When a node receives a packet, it first decodes it. If it should retransmit it, it waits one time slot before doing so. The gap time slot serves three purposes. 1. The first purpose is to give the system time to decode, because forward error correction can take a long time to decode and some time to process the packet. The second one is to provide a second chance to receive the packet if there is a downstream node retransmitting it. Finally, it reduces collisions between nodes. The above diagram shows the QMesh protocol across time. Node 0 first transmits a packet. It gets received by node 1. Node 1 decodes and retransmits the packet at n+2. Node 2 receives the packet at n+2 and retransmits it at n+4. Finally, node 3 receives the packet, waits one time slot, and then retransmits it. Next, at n+3, node 0 originates another packet. This packet goes down the line in a similar fashion. You can also see here the second chance feature of the TDMA protocol. For example, if node 1 does not receive the packet from node 0 at the first time slot, it has a second chance to receive it from node 2 at n+2. The next key feature of QMesh is the use of sophisticated forward error correction. While LoRa has a form of forward error correction built into it, this code is limited in its ability to correct errors as compared to more sophisticated algorithms. A better forward error correction algorithm can bring several benefits to QMesh. The first and most obvious one is that it can improve the effective link budget of the QMesh system, allowing for longer range. Another benefit is that it helps improve the packet receive rate in the presence of heavy interference, such as the interference caused by multiple nodes transmitting at the same time. Currently, QMesh is using an RSV or Reed-Solomon-Viterbi error correction algorithm. RSV combines a convolutional code with a Reed-Solomon code. The forward error correction algorithm currently uses hard decoding, as the LoRa radio does not provide soft bits in any sort of straightforward manner. Next, I'm going to discuss the hardware used by QMesh. A QMesh node consists of two parts, an STM32 Nucleo 144 development board, and a custom LoRa shield that mounts on top of it. It is designed so that the two boards can be powered via a USB cable. The red USB cable seen in the lower right can be used to provide debug and a console serial port. Finally, there is an OLED display that provides live information about the operation of the node. The LoRa shield is a custom design that's designed to work with the ZIO connector on the Nucleo 144 board. The shield has a 1-watt LoRa module, a 128 megabit QSPI NOR flash chip for storing configuration and logging information, an I2C OLED display, and it has a mini USB connector to supply 5 volts to the shield, as well as to the STM32 board. The shield uses an eByte 400M 30S module. This module is designed to operate from 410 MHz up to 493 MHz, which covers the entire North American 70 cm amateur band. It is based on the SX1268 LoRa radio chip. It has 3 features that are valuable here: a 1-watt power amplifier, an external LNA that improves the receive sensitivity by about 2 dB, and a TCXO. eByte also makes a version of this module that supports the 33 cm band. The final shield was tested clean, with no spurious harmonics outside of regulations. The LoRa shield board design was done in KiCad. It's a 2-layer board that was fabricated and partially populated at JLC PCB. JLC PCB populated the board with everything except the pins, the LoRa module, the USB socket, the OLED display, and the SMA connector. The RF traces were done as a coplanar waveguide, as microstrip transmission lines can be tricky to design with a 2-layer board. Lots of power decoupling capacitors and ESD protection diodes were added to help add robustness and protection to the design. Next, I'm going to talk about the experimental setup. To test how well QMesh can successfully receive from multiple retransmitting nodes, a worst-case test scenario was built, as shown in the picture. The worst-case scenario here is to have 3 nodes retransmitting close together with the same type of antenna gain, polarity, and so forth. By putting 3 identical antennas roughly 1/4 wavelength apart, the worst-case retransmit scenario here should be realized. Determining the packet receive rate, then, was done by having another node receive the packets as I walked around my backyard with the node. This setup helps test QMesh's ability to receive colliding packets throughout a variety of multipath fading scenarios. The final results are fairly straightforward to explain. When forward error correction is used, the 1, 2, and 3 node setups enjoy a packet receive rate of 99% or more. Without forward error correction, we see a significant steady decrease in the packet receive rate as more retransmitting nodes are added. It also appears that the effective noise floor is raised and weak signals are not received as well. The next step is to develop FM micro repeaters that encode and decode the analog FM voice as codec 2 and use the QESH protocol to relay this digitized voice between other QESH nodes. These FM micro repeaters make it easier to use QESH as they allow people to use their existing FM radios with QESH. It also provides the opportunity for interfacing with existing FM repeater systems to extend coverage, as well as to potentially provide APRS support. Above is an overview of the architecture of the FM micro repeaters. The micro repeaters supplement the QESH node with an RDA 1846S module. The MCU provides commands to the RDA 1846S module over a UART, along with analog audio going in both directions. A 2-meter 70-centimeter diplexer is used to allow the 2-meter analog FM communications from the RDA 1846S module to be shared with the 70-centimeter LoRa module. Here's my contact information. In general, the most up-to-date ways to get information about QESH are through the GitHub project page and after that the Hackaday page. I'm also fairly responsive to email, and I periodically provide project updates on my Twitter feed. That concludes my presentation, and the rest of this time will be available for additional questions.
Hello, can everyone hear me? Okay. All right. Hi, everyone. Can you hear me?
Yes, we can hear you.
Okay. So I've been answering questions. I'm sorry?
Sorry, never mind. Go ahead.
Okay. Okay, so I've been answering some of the questions in chat. I would personally say, I think one question that's been popping up on both the YouTube side and the Zoom side is a question about the forward error correction. Maybe and the noise floor. What I'm observing, I think there's some confusion, probably the way I presented it, with the thing that's raising the noise floor is basically all the nodes transmitting together. So what's going on here is the receiver basically captures one of the transmissions and ignores the others. The others aren't completely ignored in a sense. They raise the noise floor. So if you have a really weak signal and everyone's transmitting together, that kills that basically hurts your ability to hear the weaker signal. And I thought in general, that's one of the ways like spread spectrum communications often appeared, was it in effect raised the noise floor for everyone else. In terms of the forward error correction, it appears the big benefit here is it just improves interference survivability. Because right now, I'm trying to think how, yeah, when I turn it off, you get higher error rates in the interfering scenarios. So if you use forward error correction, that seems to fix that. I'm trying to think, okay, I'm looking at some of the other questions here.
There were a couple of questions you answered, but maybe every YouTube folks didn't hear it. DK5HH asked, is broadband transmission in the US allowed with the ham license?
I believe it is. I've seen, I think in 2011, like there's been, back in the 90s, there was a spread spectrum rule that said you had some kind of like automatic power control. As of 2011, I believe the rules state you can do spread spectrum subject to you have a 10 watt PEP input, but you can have as much antenna gain as you want. If you want to use more power, you can, but you have to get a special temporary authority, which I did for my long distance LoRa work 2 years ago. That's exactly what I did. You can only do it on 1.25 meters and up. So no 2 meters, no HF. And you're always a secondary user. So, I mean, I think, and the other one is, I think there's some authority somewhere. I don't know the exact rules on this, but that you have to, either coordinate with local authorities like frequency coordinators or log what communications you're doing, but that might be an older rule. I mean, I think the main one is it's just the understanding of you're using a lot of bandwidth lightly, but you have to make sure that you're not interfering with other people.
Okay. He also asked, what is the maximum bandwidth?
I'm not sure if there is a maximum bandwidth. I haven't heard of one. I know there's a discussion, I think on 70 centimeters is for digital communications. You have a 56, there's some bandwidth limitation. It's like 56, the symbol rate's like 56 kilobaud, and there's some bandwidth limitation. But I've seen claims that that doesn't apply when you're doing spread spectrum.
Okay. Scotty, did you have anything?
I just was going to ask for a clarification from a question on YouTube that you sort of answered, but it was it's kind of comparing FEC to multiple nodes. So adding FEC, of course, makes it harder to hear weak nodes, and multiple nodes makes it harder to hear weak nodes. Do you have a feel for which one is more important?
Well, no, FEC doesn't make it harder to hear weak nodes. I think I just maybe conflated two different things in the slide. It generally helps, the forward error correction helps hear interfering nodes. It doesn't, the thing I didn't notice was, I think maybe what I meant to say was, ideally with forward error correction, you'd like the idea of you can hear weaker signals than you could before. In practice, I didn't notice this huge kind of coding gain. And I think the reason is that the receiver, the lower receiver chip is calibrated so that when you receive a packet, it's probably correct. Like it doesn't try to kind of receive really weak packets. I have some ideas on how to change that receive threshold, but I think that was the disappointment I have. I was hoping to get like 5-7 dB more lower receive, better receive floor by using forward error correction. I didn't really see that.
Okay.
Lots of positive comments on YouTube. I'll mature on that channel. So.
Yes, thank you. Appreciate that from everyone.
Very nice.
I don't see any more questions.
Okay.
So.
Anything else, anybody?
Yeah, anybody?
Yeah, I think it's in the paper. It's on the GitHub site. I think it's in the last slide of the presentation. It's on the, yeah, it's like github.com fader. So Foxtrot Alpha Yankee, Delta Romeo. And that should get you on one of the projects. The main project I'm working on is QESH. All right. So that should work out there. All right, anything else?
Guess not. Well, thank you very much for the great talk.
Thank you. Thanks, everyone.
Thank you.
Okay, have a good time.
Thanks.
Okay.
Maybe we can mention a bunch of the links that people might be interested in, Stana, and repost them in the chat.
Well, I wish I had them handy. The most useful one, I think, right now is where you can get the PDFs of the papers, and I'm trying to find it.
Yeah, there was a lot of traffic, so it's kind of hard to sift.
Yeah, and it's a long URL, so oh, where the heck is it? I see, I'm scrolling up. Wait a minute.
Well, while you're looking for that, Stan, there's another question on YouTube that how configurable is a LoRa chipset, or is it relatively fixed?
Okay, for me, okay, so my answer is it depends on what you're trying to configure. I'm sort of frustrated right now on the forward error correction side of things is there isn't a straightforward way to extract soft bits. I think there's a way to do it, but it's kind of a challenging workaround, challenging hack. I think you can disable the forward error correction, but that's actually sort of an undocumented feature. So, I mean, for my work, that helps. I'm not sure what other options you want to do.
Well, it says, David says there's a tool that was shown briefly in one of the slides. Is that?
Yes, I've spent way too much time with the LoRa configuration tool. It's really handy to use. Especially the one for the SX1272 as opposed to the SX1260 series. It's a nice GUI and you just kind of open it up and just play with different settings. They'll give you things like estimated receive sensitivity, link budget. I think it'll actually give you power consumption estimations if you're trying to conserve power. Yeah, there's a lot of stuff there. I mean, in terms of LoRa configurations, the big thing to be careful of is LoRa is extremely fragile to frequency drift within a transmission. So you need a TCXO or you need to make your transmissions reasonably quick, say is like less than 2 seconds in duration. And it will, if you don't do this, what'll happen is your communications will fall over. You'll just be banging your head against the wall trying to figure out what's wrong.
Okay. Thank you again, Dan.
Thank you.
Thank you, Dan.
Okay. Next up is Mohammed Maktoumi from the University of Scranton, and his topic was GaN-based RF power amplifier design. He's not available. Are you going to answer, Nathaniel, or for him, or?
I don't think I'm going to answer the questions per se, but I can certainly, if there are any questions, I can forward them to him. So
Okay.
MD, as we call him, or Dr. Maktoumi, he's another professor here at the University of Scranton. And his interest in RF engineering is quite a bit different than mine. He's interested in microwave RF engineering, where I'm more focused on HF. So yes, he's going to be talking about gallium nitride-based RF power amplifier designs. So certainly, if there are any questions for him, you can put them in the chat, and I can send them off to him. But yeah, I hope you enjoy his presentation.
Okay, George, let her rip.
Hello everyone, my name is Mohammed Maktoumi and currently I am an assistant professor of electrical engineering at the University of Scranton. Welcome to my presentation on gallium nitride based radio frequency power amplifier, its design and simulation. In this presentation, we are going to talk about the RFPA and their key performance matrices, and then a little bit about the GaN device and why we prefer GaN device nowadays, classes of operation of PA, and power amplifier design steps, and then I will be showing you some simulation results. Now, an RFPA, the radio frequency power amplifier, is an amplifier that boosts input power. In fact, any RF amplifier will boost input power and give you some higher output power. But when we talk of RF power amplifier, RFPA or HPA, we basically talk of power amplifier that has an output power greater than 1 watt or so. So if one of the applications of RF amplifier is in wireless communication system, for example, on the transmitter side, when you are sending signal out in the space, before that you would like to boost the power of that signal. Some of the key specification of power amplifiers are gain, which is defined as the output power over the input power. So if this is the power amplifier, you have some input power and you have DC supply power, PDC, and this is the output power. So the ratio of output power, RF output power over RF input power is called the gain of the amplifier. This is in linear scale. In dB, this will simply be P out minus P in. So P out in dBm minus P in dBm will give you the gain in dB for the power amplifier. Also, we talk of efficiency, which is P out over PDC. So how much is the RF output power compared with the DC input power? So essentially, it is at the output you are getting more power. So where that more power is coming from? So that power is basically coming from this DC. So how good is this power amplifier at converting this DC into P out? Because the rest of the power that is not being converted to P out will dissipate as a heat, and that means more money, as I will explain in a moment. So that metric is P out over PDC is called the efficiency, and we would like to have higher efficiency of the power amplifier in general. Now, we also talk of another term, and that is more prevalent in industry, that is called the power aided efficiency, PAE. And that basically takes into account of the fact that when you are supplying input power, this PDC is not the only input power, but also this PIN. Therefore, when you are trying to measure the efficiency, this output power is not the output power only due to this PDC, but it also has contribution from input. So a good measure of efficiency, in fact, should be subtracting the impact of this PIN from this P out. And that's what this power aided efficiency is about, P out minus PIN over PDC. Now, if you look at the graph, so the graph between P out and PIN should be linear. So this is that graph that you see here is the linear graph. And like most of the device, every device saturates. So as you increase PIN, the out will increase with some constant gain because the graph is linear. And gain is basically the slope of P out over PIN graph. So gain will be constant. But after some time, you'll see that if you increase your PIN, your P out will not increase that much as it was increasing here in the linear region. So your device has entered in saturation, and therefore your gain will drop because slope is decreasing. Now, this difference here, where the difference between the actual power you are getting minus the ideal minus the actual power, when this becomes 1 dB, that is called 1 dB P. So at the input side, that point will be called P in 1 dB. At the output side, that will be called P out 1 dB. And that is also a very good metric of power, very important metric of power amplifier, because maybe you have a very high gain power amplifier, but the output power itself is not very high. So this P1 dB or Psat, the power in the saturation, is a key metric of power amplifier. Also, if you plot the power aided efficiency or efficiency with respect to PIN, you will see that it peaks in the region where you have saturation. It means if you wanted to achieve high efficiency, you must be operating your power amplifier in saturation. In saturation, you have bad linearity, of course. So you can deal with those linearity using something called a digital pre-distortion, or the DPD. So that can help you get rid of some of those non-linearity. But the advantage of operating the power amplifier in this saturation region is that you get a very high output power. Also, you get very good efficiency. And there is some sort of course, compromise between the gain, the efficiency, and this output power. Now, having a very high efficiency of power amplifier is very important, especially in base station powers, because the major power consumption in the base station is due to this due to this cooling requirement of the power amplifier heat. So RF power amplifier and feeders, they cost 60 to 80% of the electricity bill. So if you have a very high efficient power amplifier, that means there will be less power consumption in terms of DC, in terms of heat, and therefore less use of air condition, and therefore your power bill will get reduced. Another key metric of power amplifier, and in fact any amplifier, is the bandwidth. So having a high bandwidth power amplifier means you can support very high data rate, which is very crucial for 5G and upcoming next generation wireless communication systems. Now, the power amplifier can be based on the historic microwave tubes, like traditional, traveling wave tubes. So it's still in very high power applications, continuous wave 200 watt, for example. This example is from some commercial company, and it is for very high frequency and very high power. So still in those regime, we use tube-based amplifier, but slowly this solid state or the transistor-based power amplifier are making their way into those regime as well. So most of the cell phone almost all the cell phone power amplifiers are of course transistor based, but even high power application and high frequency application is now like a hot topic for solid state power amplifier research. So the reason we use solid state power amplifier is because it requires low maintenance, it's very, very compact, and it offers very good reliability. Now, before we go further, I would like to point out that if you wanted to have very high output power, so you will assume or you will think that we will use the traditional complex conjugate matching. So when you do perform complex conjugate matching, the maximum power transfer occurs. Unfortunately, that doesn't happen in power amplifier because complex conjugate matching or the maximum power transfer theorem is valid for the sources which has unlimited power, but most of the real devices has limited allowed signal swing, and therefore complex conjugate matching are actually not employed in RF power amplifier design. In fact, we try to present the load to the power amplifier device in such a manner that the voltage swing is maximized as well as the current swing is maximized, and therefore the power, which is V times I, will be maximized. Now, the reason we use GaN device is many. One of the major advantage of gallium nitride is having a very high band gap, energy band gap, and that means it can sustain very high electric field, and therefore it has high breakdown voltage, and it means this signal swing on the voltage scale will be very high, and it is a very good candidate for very high power amplifier. It also has a very high current density, and it means for for per unit area you will always be getting higher output power. So what are we comparing this GaN device with? So the GaN device is being compared with the conventional gallium arsenide or silicon LDMOS devices. Now it has very outstanding thermal properties because the substrate that you use here in the gallium nitride transistors is SiC, especially for RF applications, silicon carbide, and that gives it a very excellent thermal conductivity. And in general, it has higher output impedance level, and because of that, you will achieve higher bandwidth and less loss. You can design a very highly efficient amplifier using GaN devices, and it means the power consumption, the DC power consumption will be low. One of the some of the disadvantages of this GaN device is high cost, and it is because it's not very mature technology at this time, like LDMOS. LDMOS is quite mature. But with time, this cost will reduce because more and more investment will be done in this, and more and more the development will take place in the gallium nitride research and development. So it is expected that the cost will get down. Also, linearity is not good compared with LDMOS and gallium arsenide. But we are, pretty good research is going on in DPD. And now the DPD algorithms are capable of curing a lot of nonlinearity effects. Also, it is not suitable for low power device, but maybe in future it will be possible to design very low power amplifiers using GaN. And one of the things that we do in GaN, as I will talk about this later on, is that we imply harmonic control to enhance the output power and the efficiency, as I will talk about in a moment. Now, PA, most of we have electrical engineers have studied about the PA classes, class A, class B, class AB, and these are based on the so-called the conduction angle of the waveform, of the drain waveform, drain current waveform. And class A, for example, has a very poor efficiency of 50%, but it has a very high linearity. And then class B is 78.5% efficiency, and class AB is kind of in a compromise between these two, efficiency between 50% and 78.5%, and then you have decent amount of linearity. Then you have another kind of amplifiers which are called the high efficiency modes, class F inverse, and class E amplifiers, for examples. So they are mostly based on, especially class F and inverse class F are based on the waveform engineering, and there we basically try to present load network. So these are called the biasing class of amplifiers. So basically we establish some bias current here, and depending upon the level of the bias current, for example, it will be class A, class B, or class AB. Here basically we do waveform engineering, and they are based on the output load network, and we try to present a load network in such a manner that the current and the voltage are complementary of each other. So when you have high voltage, you have low current, and when you have high current, you have low voltage, and therefore their product will be 0, and ideally you can have 100% efficiency. So that's an ideal. But class AB is still quite a popular class of amplifier. It has very decent linearity and efficiency, and it is also important because it is used in a very popular base station power amplifier architecture that is called the RTTY, and that basically is used to enhance the linearity, or sorry, efficiency of the amplifier at the back of power. Now, our RFPS structure is very similar to any other amplifier. If you look at this structure here, you have the device, and then you have the output matching network and the input matching network. And it might be tempting to think that basically the power amplifier design is basically the design of matching network, but as I will show you later, but it involves a lot of things. But essentially the input and output matching network are, of course, two main component of any power amplifier. But how do you find the output impedance? As I said before, the output impedance cannot be complex conjugate impedance anymore. So how do you find that? So we perform something called the load pull analysis of the device, where basically we attach a tuner here at the output of the device, and we try to vary the load and try to present all the load condition on the Smith chart, and try to look at what load, what power, output power, and about how much efficiency will be obtained. And that so that result in power amplifier, power delivered, and PAE, or the power added efficiency contours. And this type of simulation is called the load pull simulation of the device. So how to perform load pull simulation? Well, if you have a very good device model, you can use that device model in software, and then you can set up the simulation, and you can tune, you apply some tuner here in the software, and you can perform the load pull simulation in software, and it's a very cheap, very nice result can be obtained using this, but it does need a very good device model. If you don't have access to good device model, you will have to resort to physical setup, where you will have mechanical tuners at the load side. Sometimes you can do source tuning as well, and this is quite costly setup, but it can give you the measured actual load pull data for any device itself. But these are very costly setup. So it is a good idea if to choose a device which has a very good available model, so that this amplifier can be designed in without spending much money on this purchase of this measurement setup. Also, in power amplifier design, some power can go to the harmonic. So what I mean is, like, if you have your device and you apply a frequency F here, the power can be at frequency F, the output power, and then you also have power at 2F and 3F, and because we want power at the fundamental, so our goal will be to minimize this power at the harmonics, and to do that we will have to know what impedance to present to the device at harmonics. So we also have to do harmonic load tuning, or to find the impedance at harmonic frequencies. Now you can consider like n number of harmonics, but generally if you are trying to deal with more harmonics, or trying to like find impedance at more harmonics, it means your design will become more complicated, and it will become more and more challenging, more complicated, and it is not actually necessary, because at higher harmonics you have output device capacitance which will become shorted. So generally, like 2 to 3 harmonics does give quite decent result for the power delivered and the output efficiency. Now here I list some of the design steps that I have used, for example, in design of my power amplifier. So You basically choose a device, and you choose a device that has non-linear model available from the device vendor. So for example, Wolfspeed Cree makes a very nice device with, and they also provide very nice device models that has been used by a lot of people. So I choose this 10 watt Cree device from Cree, and I perform its IDVGS graph to see, okay, if I wanted to bias this amplifier, say at 100 milliampere in class AB, so what should be the gate voltage, applied gate voltage? So this drain voltage is normally fixed. The manufacturer will tell you how much the drain voltage is needed to be applied. That's a 28 volt, for example, in Cree device. And then from here you can find the required gate voltage. So that is your gate voltage, and this is your drain voltage. And then after that you have to stabilize the device, because your device could be unstable, especially at low frequencies. So it's a good idea to stabilize it before going further. And it is a good idea to look at the data sheet of these devices, and data sheet can give you some hints on what kind of network to employ to kill the oscillations at the low frequencies. After that, once you have stabilized it, so for example, in this figure, I'm showing you how I have this GaN device, and then I have this tab where the device pads will be soldered, the input and output. So at the output, I'll be using the matching network as pad, but at the input, I wanted to apply this resistor and capacitor in parallel to stabilize the device. So I'm putting an extra tab here, and this is basically so-called the EM co-simulation model of this transmission line tab. That I have obtained after the EM simulation. So once you have this, you can perform the load pull simulation, and this is here I am doing fundamental load pull simulation. We will assume some impedance for some high impedance for the other harmonics, and we will perform sweep the fundamental load here, and that will result in this kind of graph that is called the as you can see from here, this results in PAE, or the power added efficiency contour, and power delivered contour. So it's very similar to low noise amplifier design, where you have gain circles, noise circles, and whatnot. And in general, they do not converge at one point. So the best of, for example, this PAE is here, and the best of this power delivered is here, and they are not coinciding. So you have to make some sacrifice. And for example, here I am choosing this point here somewhere, so that I can have decent amount of efficiency and decent amount of output power. So I know that, okay, at this, if I choose that as output load, this will give me 77.4% of efficiency and 41.8 dBm of the output power. And the corresponding the impedances are shown here, the load impedance and the input impedance. So we have this value, and now we can go back to this load pull simulation again, and now we can substitute that fundamental load impedance that we have obtained here, and now we can perform the similar kind of analysis for second harmonic. We can sweep the second harmonic, again obtain the second harmonic impedance, substitute this here, do it for third harmonic, and then again check to see if we have to perform fundamental. So it's a quite to and fro kind of analysis to go back to the fundamental, come to second harmonic and third harmonic, then go back to, until you have achieved a desired result. So it's a very time consuming simulation, but this is the process. So once you have obtained the once you have agreed to a load impedance, and you know the value of load impedance at the fundamental harmonic, second harmonic, and third harmonic, and you know the value of input impedance, now with those data, you can start designing your input and output matching networks. So you design the output matching network, you design the input matching network, you perform the optimization. So for example, here I'm showing you how to design input matching network. So I know the value of the input source impedance at the gate, and I know my source impedance, which is 50 ohms. So I can design a T-network sort of impedance tuner here, impedance matching network, and I will also implement that in real transmission line, and I can perform the EM co-simulation. I have to do the optimization. Sorry, so it's a quite, again, lengthy process. We have to repeat these two steps for the output side of matching and an output side, because you have to match at not only at the fundamental, but you also have to present some, the decent impedances at the second and third harmonic. So output side matching network is designed first, and that is, much more time consuming. So, after taking all those steps, we arrived at this design for the input side of this, and this represents where I will have my semiconductor device, or the Cree 10 watt device to be soldered. This represents the tab here, and this is the output matching network. I have done a couple of modifications from my initial design. For example, to reduce the size, I'm going to bend this line here. Similarly, I have to bend this line here to make some way for the mounting holes and the grounding holes, and also to increase the bandwidth of the lambda by 4 line. Rather than using simple lambda by 4 line, I'm using radial stubs. That basically gives you a higher value or wide bandwidth capacitance. Also, I have these tuning lines here that is used, like after designing this amplifier, you find that your performance of the amplifier is not that good. You can start, kind of, for example, if you find that if you have to increase the length of this line, so you can solder 2 or 3 of these, for example, to this line to increase the length of this line, and so on and so forth. So one more thing, that after designing this, designing some initial network here, their design might not be like very good in terms of bandwidth, so you also have to perform one optimization for the bandwidth, and that was done for this device also. So after this represents my final optimized design, which I will have my Gerber file for, and this represents the simulation result. So it is the power sweep result. So I'm trying to sweep the input power probably at the central frequency of the device, of the power amplifier, and then here is the result of, for example, the power added efficiency, power delivered, and the gain. And it is you can see from this, for example, this measurement, that at this point in saturation I have a gain of around I would say around 10.5 dB, and 10.5 10.8 dB, and the power added efficiency at this time is 67, quite decent for class AB, because it's very difficult to obtain this much efficiency in class AB, especially at high frequency. And the power delivered is quite high, and this is the frequency sweep result. So if I'm getting this at central frequency, what is the condition at the other frequencies? And you can see here, this is how it is varying. It is touching 70% power added efficiency here in this region, but unfortunately the gain here is not very good. It's less than 10 dB. But I can assume that, okay, from here, from 1.7 up to 2.2 gigahertz, I have a pretty decent performance throughout this band. So if I'm happy with this performance, I'll go ahead and fabricate this power amplifier. So this represents the fabrication of this device from this Gerber file. So this was about the design and simulation of the power amplifier, and I showed some results. I have not measured this device yet, but one thing I did is I tested it for DC stability, and I found that this device was unstable. As soon as I will connect DC supply, the power supply will trip. So to reduce or to get rid of that instability, what you do is basically at the gate side, you add a resistor, and generally, like 50 to 200 ohm resistor. I have found that if I add those kind of resistors here, and you have to do some hit and trial here to cut a track and add some resistor. In power amplifier, we add this here. We don't add it at the output, because if you add this resistor at the output, that will reduce your power delivered. So you put it here, and this will cause the the noise performance to deteriorate. But for power amplifier, we don't care much about the noise performance. So this resistor helped me kill the oscillations. And now my next task is to do the power sweep and the frequency sweep in this amplifier. And if when the result is available, I would be very happy to share those results with you. So this is where I will conclude my presentation, that it's a RF power amplifier implying a GaN device is a very hot topic at this time, and it's like any power amplifier design, it's a very time consuming. You have to be very spend a lot of time on EDA tool performing simulations. So if you have a very good device model and a very good EDA tool, that will come quite handy, but still it consumes a lot of time because there are so many optimization steps, so many one harmonic to the other harmonic switching and going back and forth. So it's a very time consuming, and one needs to perform optimization at different level schematic, and then in EM simulation you have to perform the optimization. All these steps were carried out for this 10-watt GaN device power amplifier design, and so far the performance as far as in simulation is concerned, it's quite decent. The real fabrication was showing some sign of instability, DC instability. So we have been successful in killing that instability by putting a resistor at the gate, and the measurement results, further measurement results are awaited, and once that is complete, we will be very happy to share that with you. In case if you have any question, please feel free to email me at mohammad.maktumi@scranton.edu. And two very good reference that I have found on RF power amplifier, especially in L and S band, are these two books from Stephen Krebs and Colantino group in Italy. And they have taught me a lot of things about power amplifier. So I hope that you enjoyed this presentation. In case if you are willing to, if you have some questions, or if you are willing to collaborate with me on a power amplifier design, I will be very happy to collaborate with you. So please feel free to email me at mohammad.maktumi@scranton.edu. Thank you very much for your time and patience.
Do we have any other questions for Mohammed? Nathaniel is collecting them and will forward them to Mohammed.
Yeah. Hi, everyone. Yeah, you can also send your questions directly to MD at his email address. That way you're most likely to get the answer back to you. I will also copy all of the comments I'm seeing in the chat here and send them off to him so he sees those. But if you want a direct response, please email MD directly.
Okay, thank you. Okay, next up is Phil Erickson, W1PJE from the MIT Haystack Observatory. You're up, Phil, go ahead.
Hi there, everybody. Greetings from Eastern Massachusetts or Central Massachusetts, depending on how you look at it. As Stana mentioned, I'm at Haystack Observatory, which is run by Massachusetts Institute of Technology. This next talk is a little bit different. It talks about an upcoming satellite mission in a couple of years, which the observatory is leading, and which has interesting potentials for ham radio collaboration. So with that, I think we should run the video, and I'll answer questions later. Hello, I'm Phil Erickson at MIT Haystack Observatory. Today in this TAPR DCC talk, I'll be giving you an overview of an upcoming twin small satellite project that MIT Haystack is leading and that will fly in 2022. My co-authors are listed here. It's a large team, colleagues from MIT Haystack, from Dartmouth College, from MIT Lincoln Laboratory, in Lexington, Massachusetts, from MIT campus in Cambridge, specifically the Aero Astro department, from Moorhead State University in Kentucky, from the University of Tromsø in Norway, and from Merrimack College in Andover, Massachusetts. The outline of this talk, I'll be giving you first a mission overview, what the goals of the project are, and some basic facts. I'll talk about the science and the technical targets at radio frequencies that we're aiming for, and specifically in the HF band, which is very familiar to radio amateurs. So I'll try to get you oriented there. And then I'll talk about the key payload that these two small satellites will be flying, something called an electromagnetic vector sensor. That is a compact system that nevertheless gives you angle of arrival information, even at HF frequencies, in a high dimensional interferometry setup. And then finally talk about a little bit of collaborative science that we hope we can do once we're on orbit, including with the amateur community. So a brief overview of the ARRO and VISTA missions. ARRO stands for Auroral Emissions Radio Observer. That was our initial mission funded. Both of these are funded from the NASA HTIDES program, Heliophysics Technology and Instrument Development for Science. This enables the advancement of full capable science instruments on small platforms like CubeSats. ARRO targets HF radio, 100 kilohertz to 5 megahertz from low Earth orbit. And as we'll see, it's primarily science focused and is looking at radio emissions that are emitted from the aurora or the northern lights, which we're all familiar with optically. The next year, we got from the same program funding for a second identical build-to-print copy, which we call VISTA, Vector Interferometry Space Technology using ARRO. That extends the HF radio capture up to 15 megahertz. It is primarily technology focused. It goes for I-dimension interferometry, not only from a single satellite, but between platforms. As I mentioned, the partners are listed in the lower left. The green box gives a few facts about the mission. Nominal launch of 2022 with the duration of 90 days, option for extension. I'm the PI of ARRO. My colleague Frank Lind is the PI of VISTA, but we manage it as a joint project. Each of these will be a 6U CubeSat, so that's 20 centimeters by 30 centimeters by 10 centimeters in our case. It will be deployed into a sun-synchronous orbit. That means it's the same local time underneath the spacecraft in a noon-midnight plane, plus or minus, above 450 kilometers altitude, between 450 and 600 kilometers altitude, so in the topside ionosphere, above the normal F region peak that reflects ground-based HF signals. We have deployable antennas for auroral science that will cover between 100 kilohertz and 5 megahertz, and the up to 15 megahertz extension up into the 20-meter band is for the technology vector interferometry demonstration. We have an auxiliary sensor package, which includes a magnetometer and an optical aurora sensor to give us some context with the auroral forms that we see emitting radio waves. And since these are two build-to-print identical copies, we have two shots at auroral science. The mission science target is shown here in this beautiful view out the International Space Station at about 350 kilometers altitude of the optical aurora. As you can see from the picture, the optical aurora has a vast number of scales and structures and dynamics, time scales from milliseconds to hours, spatially from sub-meter to tens of kilometers. In addition to the optical aurora, as in the movie, the radio aurora also exists. It's far less studied because you have to get above the ionosphere, as we'll see in a moment. It's actually radiating in more than a gigawatt EIRP. Much of the radio emission comes in forms of electromagnetic waves, which are quite coherent. They're caused by plasma processes. And because the Earth's atmosphere is strongly magnetized, the magnetic field direction plays a large role because the electrons are strongly bound to gyrate around the magnetic field lines. This plasma physics creates many auroral emissions at radio frequencies, and specifically at LF and HF frequencies, that are really only observable from orbit because the ionosphere blocks them from a ground view. So again, just to give you an idea, once these things have been deployed and are on orbit, this particular movie shows you what they look like moving across the ground at 7 kilometers per second, which is a typical LEO velocity. Nominal 450 to 600 kilometer altitude. That white circle going by is the coverage of a ground station that will talk to the downlink data and uplink commands. Mentioned it's sun synchronous, but somewhere between 9 p.m. and 2 a.m. The radio aurora is most active in the midnight sector. We get a launch through the NASA CubeSat launch initiative, which basically provides ride shares through existing launch services of primary government payloads or dedicated launches from specific commercial contracts that NASA has. This simulation, by the way, was done by Vince Skelton, a student at Merrimack College. Why did these things get cut off from, why did these auroral emissions not get cut off from the ground? This has to do with something called the Langmuir resonance. The ionosphere is a plasma, and if we do the thought experiment as in the left, and that we take the electrons that are in the plasma and move them to the right-hand side, leaving behind the heavy, slow ions. Let them go. Electrons are light and fast. The electric field will then move the electrons back toward the positive charges. When they get there, they'll have an inertia, they'll overshoot, and then the electric field will reverse direction, and you'll get an oscillation back and forth. That oscillation frequency was first derived by Dr. Irving Langmuir, the winner of the Nobel Prize in Chemistry in 1932. The Langmuir frequency is given in the lower left, and if you plug in typical electron densities in the ionosphere, in Earth's ionosphere, you get a number between 1 and 12 megahertz. So anything coming in from the top that is below that frequency is going to be reflected. So in other words, that's going to reflect incoming auroral radio waves above the F region. This is a fundamental resonance property of any plasma. It really provides a hard reflection at HF. And from the ground looking up, it's the principle behind ionosons, which we're all familiar with, or at least most of us are. So what kind of radio auroral emissions do we expect to see from orbit? It turns out there's quite a zoo of them. We've listed the 4 main types here that we're going to be going for. Auroral hiss, which as you see in the table is somewhere below 1 megahertz. It's somewhere in the AM broadcast band area. Auroral kilometric radiation is in the lower part of the AM band and below, 50 to 750 kilohertz. Auroral roar is at discrete frequencies that are harmonics of the electron gyro frequency, which is approximately 1 megahertz in low Earth orbit. So that's at 2, 3, 4, maybe 5 megahertz, somewhere in that range. And then we have medium frequency burst, a more broad range burst between 1.5 and 4.5 megahertz. So down in the 160 and 80 meter bands. And some of these are broadband, other of these are narrowband. They're electromagnetic, so they have both electric and magnetic field components, and they're highly polarized often. Their source regions are probably far above the orbital platform will be, and there are many, many unanswered questions that are just summarized very briefly in that table about how they get generated by the plasma and how they propagate from one place to another. I'll give you just one example down in the lower right-hand corner. This is auroral kilometric radiation. The top plot is a function of frequency and time, frequency from 100 to 800 kilohertz, seen by a spacecraft in the geotail. That's many Earth radii away. This intense radiation is this auroral kilometric radiation beaming away from the Earth. The bottom plot is the same frequency, but from South Pole Station. I shouldn't see that from the ground, yet receivers did. How is that propagating through the ionosphere at cutoff? That is one of the things that we hope to answer by flying the ARRL and VISTA platforms. Here's just an example in a spectrogram format, frequency now going up to about 5 megahertz and time over about an hour. This is auroral roar, that frequency you see around 3 megahertz. MF bursts are the impulsive broader band thing, around 3 megahertz again, and you'll see auroral hiss kind of embedded there in the AM broadcast band and down where the non-directional beacons are occurring. So these are the 4 main types of auroral emission that we hope to be able to see with the ARRL VISTA platform. We'll do this with something called an electromagnetic vector sensor, which is sketched in schematic form for each of the ARRL and VISTA platforms on the left-hand side. The idea is to make 3 measurements of E and 3 measurements of B. We do that with 3 dipoles labeled E1, E2, and E3 is a monopole sticking out the top of the spacecraft, and 3 loops, where loop B1 is formed by the 2 essentially E1 dipoles connecting them to form a loop. B2, the same for that cross dimension, and B3 is a loop that's formed by connecting the ends of E1 and E2. Measuring these 6 things measures the full electric and magnetic field vector, so you can get the E cross B direction, which is the direction at which an electromagnetic wave is propagating. That will determine the source intensity, direction, and polarization in a single snapshot from an electrically small, broad response antenna. This is typically used for finding the direction of strong sources. It can also perform spatially resolved imaging. You can localize human signals, like coherent beacons that are leaking out of the ionospheric cutoff from the ground, or you can do natural signals like those from above, as in the radio aurora I've been talking about. How does this get deployed on a small CubeSat? Well, this particular demonstration, these are gravity offset booms here in a lab demonstration. So just to give you an idea of what it's like to deploy these essentially flexible HF-based sensors. So as I run the movie, you will see the bottom deploy, and then you will see the tapes come out. There you see the crossed E, and then you can also see the magnetic field loops and the third loop connecting. What's not shown here is the monopole that sticks up out of the center of the spacecraft to make the final E measurement. These are about 2 meters on each side, so 4 meters tip to tip. What kind of hardware do we need to fly? Essentially, we're flying an analog to digital converter, a sampling system, and onboard signal processing to do the correlation processing that I'll talk about in a minute that we need to do. So on the right is the RF payload. That has a backplane, various memory cards. We store things on board. We take the antennas times 6, we run that into an LNA front end, and then we sample those, perform cross correlation on board, and store the things in memory until we can take tiny slices of that based on our knowledge of the geophysical conditions and some spectrogram snapshots, and downlink those to the ground on an X-band link. On the left-hand side is the Nano Avionics M6P spacecraft bus, which is what we have selected for these 2 payloads. Contains the normal things you'd see in a spacecraft: solar panels, electric power system, a ADCS system, payload controller. We have a UHF radio for telemetry downlink and also command uplink. And we have an X-band radio for high bandwidth downlink only, which is how we're going to mainly get the snapshots of the correlation data off the spacecraft. So just another example of how this thing can find a particular source. Let's, on the right-hand side, take the simple case of an electromagnetic wave that's propagating in the z direction in that XYZ coordinate system there. We remember from physics that that means that, for example, in this case, the E is in the X direction and the B is in the Y direction, and using your right-hand rule, E cross B is then pointed in the Z direction. If I take the 3 components of E, EX, EY, EZ, and the 3 components of B, BX, BY, BZ, and I correlate all of them, I'm only to get one place where there's a strong correlation, and that is in the direction of propagation of the wave. So in that case, you get an upper triangular matrix with a dominant single entry, which is the K vector or the direction of the source. These sources don't have to be coherent. They can actually be Gaussian random. The math allows that, as long as they're wide sense stationary, their statistical properties aren't changing while you're going by and trying to measure them. By doing this cross-correlation analysis on board, we avoid having to downlink raw data for every single thing we observe. And it also allows this sensor with a broad response pattern to achieve source direction finding or interferometry. It is also relatively insensitive to how the platform is oriented, as long as we know what the orientation is, which we do with a magnetometer. This is just an example of a simulation of a computer algorithm which iterates to find, for example, in this case, 2 sources from the 3 E's and the 3 B's, and correlating every element against every other element for one of those upper triangular matrices. In this case, it quickly converges to the 2 sources we knew were there from the simulation. You can imagine that there are cases where, because phase wraps, it's not completely unambiguous in all situations. Fortunately, when we're trying to observe the radio aurora, they should be reasonably bright and compact, at least according to the theory, which will help us in the convergence of our algorithms to try to find the angle of variable from this small platform. To maximize the science from the CubeSat, we don't do it all in the CubeSat alone. We employ the worldwide scientific measurement network from things like incoherent scatter radars, auroral convection patterns, flow patterns from the HF radio network operated under the SuperDarn Collective. We gather fast optical auroral cameras that are deployed in various places where the aurora is to look at optical dynamics of the auroral arcs that are generating the radio waves we're viewing. And we have ground-based receiver networks to look for those particular auroral radio emissions that we saw from orbit and that in fact leaked through to the ground, to confirm these theories about how they propagate to the ground. Another key mission technical target is the VISTA target, which is doing radio interferometry from orbit. Normally, an interferometer combines signals from two antennas, compares the delay of the signals arriving at those two antennas or a phase measurement. In the end, you get good angular resolution from that precise phase measurement. There are always ambiguities, though, that results in interferometric fringes for a spaced antenna set, especially if you move the antennas past the source. With a vector sensor, each individual platform, either ARRL or VISTA, provides its own angle of arrival estimate, which you can think about as arrival from a short set of interferometer baselines. When you combine coherently the two platforms together, you have additional degrees of freedom available. You can estimate additional quantities, including polarization. You can improve the variance of your estimate. This scales very rapidly with the number of satellites. So ARRL and VISTA is sort of a pathfinder for that. The math development for the analysis is complex and ongoing, especially since we're going to be flying these embedded in a plasma environment, which is not free space. It's got a dielectric constant that is not isotropic. So it's different in the direction of B as opposed to across B. This is a real frontier topic for space-based radio remote sensing, which we will be leading with the ARRL VISTA project. How can the amateur radio community help? We think there's a number of ways once we're on orbit in 2022 that we can involve people. Providing coherent beacons from the ground is useful for vector sensor interferometry signals of opportunity. Where do these beacons leak out at HF? Out of the ionosphere. In ionospheric ducts, where is that structure? Does the interferometric processing on board, on orbit, agree with the known locations on the ground? For this, the very modest kind of antennas, like the one at my home down there in the lower left-hand corner, like an 80-meter dipole, is actually beneficial for this because it has a wide, broad pattern. I don't need to steer to watch the antenna, to watch the satellites go by. If I had the wonderful setup of K3LR there in Pennsylvania, maybe I'm going to have to steer my antennas to follow this thing as it zips by at 7 kilometers per second. But both are valuable because the other one has a lot more gain. So there's two ways to contribute there. We think there may be potentials for wide area capture of AX.25 downlink and heartbeat packets so that we kind of get early indications of when we're on orbit and operating, coordinated with, for example, the SatNOG's efforts for distributed satellite ground stations. And in general, we'd like to do ionospheric HF propagation science in coordination with the HAMSci Collective, TAPR, the ARRL frequency measurement tests conducted by Connie K5CM, and other sorts of things that can provide us either beacons or interesting propagation experiments. Finally, I wanted to mention that this sort of ground to satellite amateur professional science has in fact been pathfinded before by the Canadian EPOP HF radio receiver on board the Cassiope satellite. This is a radio science paper by my colleague Gareth Perry at the New Jersey Institute of Technology. There they actually looked at ground to satellite propagation links, and the propagation dependence provided a very dynamic reception and information about the ionosphere that the satellite was transiting. Here we used, they used amateur transmitters as sources, in fact CW transmissions in this case. In ARRL VISTA, we have the high dimensional interferometry to add to this picture and find out very interesting extra things about plasma structure in the ionosphere. So just a summary, ARRL VISTA, an upcoming mission in 2022, will address radio science of the aurora, a relatively ill-studied subject, and all of this occurs at HF frequencies, a subject that radio amateurs are very familiar with. We're going to fly a novel vector sensor, a compact, electrically small HF set of antennas, and do the cross correlation between all the elements to allow direction finding of both natural and human HF sources, the human ones that leak out of the ionosphere. And we hope to be able to do HF propagation science with amateur radio collaborations. Stay tuned, and you can go to the website that's listed in the lower right-hand corner there to keep up with mission information. Thanks very much, and now I can answer any questions. Okay. All right, so if people can hear me, Stana, if you can let me start my video just so that people...
Yeah, let me take care of that.
Okay, great. All right, start my video. There we go. Okay, so rather than make poor Stan read through the scrolling comments, I kind of kept notes as I went along, and hopefully I've gotten all the questions here, which I'll attempt to briefly answer. If I've missed your question, throw it in the chat and I'll look at that a little bit later and catch up. So I'm going to read the question and my notes on the person who asked it, and then I'll try to answer it. So Freeman asked about whether there's going to be a repeater or other amateur transmitter accessible on board. Unfortunately, this is going to be broadcasting down only, so there is no uplink or repeater available because we are actually running a very power-hungry floating point gate array on orbit. And it turns out, if you know about small satellites, you don't get a lot of power out of a 6U CubeSat with solar panels on it, and we are just barely under the power margin. We're probably eating 30 watts just by running the FPGA and doing all of those correlations that I mentioned in the talk. But we will hope to broadcast AX.25 so you at least can listen for us as we go by. N9NL asked a question which actually I probably unintendedly confused a little bit. I mentioned build to print. And the reason that got a little confusing is that we were funded first to do ARRL. And at that time, our science mission was up to 5 megahertz. And that was what our satellite requirements are. When the next year happened and we were funded to do VISTA, which is going to do interferometry up to 15 megahertz, we sort of back propagated those requirements to ARRL. So they are in fact two identical build to prints. Now both go up to 15 megahertz. The science case still goes to 5 megahertz, and then the interferometry case takes over from there to 15. But each one is essentially completely identical and can do either mission. Dan KM6MTL asks about an AM blocking filter. That wouldn't help us too much from orbit because that's the range of the signals that we're trying to collect, in particular things like medium frequency burst. If you go back to my slide, you will see that in the one plot that I had, there's a spectrogram in there, and you can see the AM broadcast band. If you look very closely, you'll notice that they all abruptly cut down in amplitude about midway through the plot. Those are the broadcast stations in AM switching from daytime to nighttime power. Just happened to have that occur. But you notice that they are a comparable amplitude to the signals that we're hoping to get. So we should be able to fit in the dynamic range that we have available. Bill Engelke asks about Langmuir cavitation versus resonance. We have 3 hours, right, to talk about that? No, I'm kidding. Langmuir cavitation is a different subject that has to do with various voids in the plasma, which create certain plasma structures. The Langmuir resonance is absolutely fundamental to any astrophysical plasma, including the one over our heads. And so talking about Langmuir resonance was just my attempt to remind people that HF is highly reflective and that that's the resonance mechanism that basically causes the wave, say, in a vertical configuration to essentially stop, turn around, and come back. And think about us as the other direction. We're actually coming, the auroral waves are coming down from the top and actually turning around and coming back up. Roy asked about ground refraction. You know, how are we able to see AKR in that ground example versus the one that was a spacecraft? You've hit on one of the key questions. There is a theory that says that these modes propagating above the ionosphere mode convert into something called a Whistler wave. A Whistler wave is a field-aligned wave, which is something called a Z mode. Z mode in orbit converts to a W mode, and then the W mode can actually propagate down through the ionosphere, maybe. We'll actually try to see if we can sort that mechanism out, so that's a good question. Jay Schwartz asks a technical question about the antenna tape measures that were in the demonstration. That was a prototype done essentially before we knew what satellite vendor we were working with. However, HF antennas like this on orbit are a derivative of sort of springy steel tape measures. There's something called load path tapes. They have additional mechanical and materials properties that allow them to be more temperature stable in the environment in low Earth orbit, but essentially they are kind of floppy things that are the same kind of thing. Imagine that you have your tape measure and you're holding it with a spring, and this is pushing that out kind of like your normal tape measure in reverse. So we do in fact use a version of those. Dan, again, KM6MTL asks about a polar orbit. It's not quite a polar orbit, it's a sun-synchronous orbit. That is something that's actually tilted a little bit back toward purely over north and south poles. And that's done so that it's always the same local time under the spacecraft. So for example, in our case, it's going to be either noon under us or midnight under us, no matter where we are. And if you know anything about orbital geometry, that means that it's actually tilted a little bit back because of the offset between the rotational pole, for example, and the magnetic pole. Mark Brownstein, I've got 2 more questions, Stana, and then I will try to answer the rest in the chat because I notice we're already having more questions. Mark asks about 2 flying in tandem. That's an interesting thing. Neither of these spacecraft have propulsion. We can't afford the weight. So the question is, how do you do that? Well, what you do is you use differential drag. Essentially, you turn one of them at a different angle with respect to the other one using a bunch of gyroscopes on board, and you essentially have one of them slow down by interacting with the neutral atmosphere. So as they come out of the dispenser like a spring, they'll start out kind of close together, and then they will begin to separate along the orbit. And by using differential drag, we can kind of hold them there at one point to have different lengths in between the satellites where we can do interferometric tests. Finally, Richard, and people are really paying attention to this talk because these are really great questions. Richard says, I mentioned the polarization. You know, what do you get by having a second platform as opposed to the first one? It has to do with how many variables you can measure versus how much data you get. If you only have the one platform, polarization is another variable, and measuring polarization at the same time that you're measuring angle of arrival and amplitude, the error bars on each of those things are a certain level. By combining it with another coherent platform and trying to process that data together, you actually reduce the variance and it becomes a little bit easier to see the polarization. And that's kind of what I meant. Finally, for those technical people who are interested, you might wonder, how do we keep these little software-defined radios coherent? Each of these platforms have chip scale atomic clocks. There's something about that big with enough stability to approach a rubidium standard. They're actually rather power hungry. That's one of the things that actually is a bit of a power budget thing. The 2 things on the board really that take the most power if we're not doing telemetry are the floating point gate array and the chip scale atomic clock. I will stop there with the questions.
I collected
Yes.
the other questions, so you want to take
Great.
a stab at them now?
Roy, yeah.
Roy asked, what LEO will this vehicle take? Launch site, Canaveral or Vandenberg?
We don't know. Chip scale, the CubeSat Launch Initiative, CSLI, is one of these things they call you get what you get. You basically get in line. You specify the orbit you like, and they know your dispenser and they know your weight, and then you wait for a commercial launch to come up. NASA then plugs you into that commercial launch as a secondary payload. So the answer is, it could be Rocket Labs in New Zealand. It could be Canaveral. It could be SpaceX. We don't know. So we'll find out.
Okay. Sumio asked, what is the possibility of radio observation of meteors?
Meteors. So meteoroids ablate by between 90 and 120 kilometers typically. So we're pretty far above that. Whether any meteor signatures at HF propagate up is really pretty hard to tell. Meteor signatures usually up at VHF, pretty well above our band, but something to think about. I'll pass that along to the science team.
Okay. DK5HH, Michael had a couple more questions. How do you get out of the Aurora signals from the man-made noise from multi-million-dollar devices?
Yes, we are going to be swamped in orbit by things that are not natural. And in fact, interestingly enough, as you're going along, some of them leak out of imagine if the plasma has a little bit of a depression or a lower electron density, some of those signals will actually start punching through. And then if you move a little bit farther, they may disappear. The EPOP satellite that I referred to in Gareth Perry's paper saw that, in fact. They actually ran into extra electron density, which cut off the CW transmissions, even though they knew they were happening. So it's a signal identification problem, but we happen to know the general qualities of the auroral signals, and we think it's reasonably okay to separate those from the human signals, which we can then save and use as interferometry targets.
Okay, Michael also asked, have you any idea for a base station at Antarctica?
Oh, yes. Okay, so in terms of satellite ground stations, Antarctic is just a little bit hard for logistics. The ground stations we plan to use are probably the NASA facility at Wallops Island. We have a ground station at Moorhead and State University in Kentucky. We're standing up another one at Haystack in Westford, Massachusetts. We're also planning to perhaps engage something called the Near Earth Network, which is a bunch of ground stations that you can actually sort of get mission time on. So Antarctic at the moment is still hard.
Okay, and James Wolford asked, possible mission time extension, expected satellite life on orbit.
Yes. CubeSats historically have actually lasted, usually if they don't have an immediate problem, they last far longer than the 90 days that they're normally specified for. My colleagues in Colorado have something called the Colorado Space Weather Experiment. It was running for several years. So what we hope is we get through the primary mission, we approach NASA and we say, hey, it's still running. Can you provide a small, modest amount of support to keep going? Usually, if funding permits, they will say yes to that. So that is our hope, at least, to tick off some of the major science questions first, and then to go after the extended one in an extended mission.
Okay. Scotty, did you have any questions from YouTube?
Nope, there were none from YouTube.
Great. These are terrific questions. Thank you very much.
Okay, thanks for the great talk, Phil.
No problem.
We'll see you at Dayton.
And so we're entering into the break time. So for the next 30 minutes, sit back, relax, stretch your legs. I'll put up a break slide here, trying to chew gum and post slides at the same time. All right, so we'll see you all at the top of the hour. Okay, so we're nearing the end of the break. We got a couple of more minutes here and we'll get started with the next talks. Scotty Cowling, WA2DFI, will be your moderator for the next 2 hours. Michael, are you online? Let's go ahead and unmute your audio and video.
Yes, I'm I'm online. Thank you.
Oh, very happy smile. Good to see you. Okay, I'll turn it over to Scotty.
Okay, very good. Thank you, Steve. And next up we have Michael, DK5HH, going to talk to us. Well, I'll tell you what, Michael, why don't you give us a quick synopsis of what you're going to talk about?
Yeah, I want to talk about ENAMS. It's an electromagnetic area noise measurement system, which has been developed or will be further developed here in Germany by the German Amateur Radio Club, DARC. And well, I think I should mention that, yeah, you can start with the video. Okay. Thank you for the introduction and a very good morning to the audience. I want to present a little bit about the man-made noise measurement system ENAMS called. I will give you an overview and the first results. The ENAMS is an idea of a DARC EMI unit. The head of the electromagnetic interference unit is Klaus Eichel, Delta Lima 6, Sierra Echo Sierra. An independent standalone system operating in the range from 50 kHz to 31 MHz. Measurement results must be comparable to results of standard measurement procedures. I think a good reference will be the EN 55000, CISPR, and ITU recommendations for radio noise. There is a centralized server for administration and data collecting. Control and backup will be done there, but a decentralized independent measurement systems, which I explain a little bit later. We are planning to spread the system over Germany with 50 locations according to the ITU radio regulations paper 372 categories. I explained a little bit later. And we expect stable parameters over the next 5 years. Further informations could be attached from enams.darc.de. Is a question, why do we need this? Well, international treaties bind nations to use spectrum according to the ITU regulations. The EMI certification measurements before you bring a product into the market measure the emissions of the devices, and these are certified. From 0 to 30 MHz conducted line emission measurements, but no radiated noise will be measured. This is due to the laboratory size is much smaller than the wavelengths at these frequencies. Technology of power devices changed over the past 50 years. Increasing number of power electronic devices without certifications came into the market. Fast switching power electronic in solar converters and optimizers do sometimes a terrific noise. What is the solution? Well, we want to collect arguments against radiated noise below 30 MHz and to show the problem. Noise monitoring systems in ham radio activities known to me are the ARRL Noise Measurement Campaign, TAPR Working Group with the development of a Tangerine SDR. I don't know if it is for noise measurement available as well. International Amateur Radio Union Region 1, EMI managers have a hard discussion in the past. Several national initiatives in Europe, in Great Britain, Netherlands, Switzerland, and a lot of more countries in the Region 1 area. This is an open but not a complete list. If you know some more, give me a hint or add it during the discussion. Well, very important is the ITU radio communication sectors, the ITU-R recommendations, paper 372 in the issue 14 from August 2019, titled Radio Noise. The recommendations for radio noise measure the radio noise as noise figure with a measurement of 9 kHz bandwidth. Reference is to the noise of a 50 ohm resistor at minus 174 dBm per hertz. Well, it uses a defined antenna, or we can say a field sensor. And there is a difference for some categories. Category A is the line here. It has the highest level for the environmental noise, and we see residential, rural, and the last one is quite rural, and here you can see the galactic noise. Well, we have a look until 30 megahertz for shortwave only with our measurement system. And the question is, what is the noise at my location? And we want to measure it. What is radio noise level? Measured with our system actual 305 Hertz binwidth, as it is measured with an SDR system, from 55 kilohertz up to 31.1 megahertz. The measurement is done 1 second, and it is evaluated with RMS. The noise floor on a crowded ham band may be easy measured, but if you look here, one can say, well, the noise level could be somewhat here, but we have to extract this noise level by algorithms. And one big question is, what's about impulse noise? Impulse noise or burst noise could be another source. And up to now, we are not decided how to do this. But help comes from the ITU. The ITU has some papers, the Spectrum Management 2055 and 2155, and they showed a solution how to do it. The first step could be only to measure the minimum of the amplitude. Look here, you can see the minimum, it's about minus 10 dB microvolt at this measurement. But when we have the better solution is done with statistics. We extract 100 kilohertz from one of these extracts. You see 100 kilohertz could be part from 7 megahertz to 7.1 megahertz, and you see there is a slightly trend in the noise level decreasing to higher frequencies. So we take only 100 kilohertz. These are 327 bins, and we select the level for the cumulative total frequency. This is done with a histogram in the upper part of this picture. This is a histogram, and here you can see the integrated histogram, and we took a level here and take this as the noise level. But there are other noise sources. PLC, when they are in idle mode, do sometimes a burst noise. Only one packet is emitted. And when you measure from 0 megahertz to 62 megahertz, you can see two curves. One is the average, not exactly the RMS, but similar. And the second is a peak by one impulse within 20 seconds measurement time. It's measured on Sunday, 21st of June 2020 at 11:07 GMT in Bremen. Well, we see only the upper half of the two-band measurement system. The upper band is a little bit over 8 megahertz, so you see a decrease of the amplitude below 8 megahertz. But the difference between the red and the blue curve is the peak value, and here you can see only one peak brings up the PLC by a burst, and when you see on the waterfall downside, you see there's one burst which could be noticed in the waterfall picture. We look on the next foil. What results do we expect from the EMI monitor? What are superimposed results of many electrical systems? What noise levels could be found in different ITU regulation categories? What frequency range is concerned? What is the longer-term development of man-made noise over months and years? With the 50 stations in Germany, a geographical distributed heat map of noise and the dependency over time will be expected from this system. Well, some more standards and recommendations. The CISPR 1611 and spectrum management I mentioned before. Conventional noise measurement up to 30 megahertz on the line are done with the CISPR 1611, sequential tuned and measured with RMS. One frequency lasts for 1 second. Here, if you look here, it's 841 kilohertz, 850 kilohertz, and 859 kilohertz, and so on. And here you see the time, 86 seconds, 87 seconds from the starting of the measurement. And as you can see, when we want to measure from 55 kilohertz to 30 megahertz, we have a problem. One measurement lasts about 3,438 seconds. It's 57 minutes with the 9 kilohertz filter. And this procedure, this is standardized, but this procedure will be not a good idea to have a repetitive measurement every 10 minutes. So this measurement procedure is not possible to apply for our problem. I should make some remarks on the field sensor which we use in the ENAMs. The ITU regulation paper 372 noise figure recommends and refers to a quarter wavelength monopole antenna as a sensor. This means for the low frequency you need a very long quarter wavelength monopole. ENAMS uses an active antenna 1 meter length and 1 meter high over a radial network on ground. ENAMS antenna, the antenna factor can be calculated. So this is very important. You don't need a field calibration of it. You can calculate and it is calibrated. The measurement front end is according to the ITU Spectrum Management 2155 recommendations, with a specified antenna, a two-band amplifier, an SDR, and putting the results into the internet. ENAM's system overview show you on the left-hand side the ENAM's receiver system here and others. Then the ENAM server system in central, and you see the measured data are some parameters extracted and calculated into different tables of an SQL database replication system. And we have a web server to show some results of it here, a spectrum, waterfall heat map, and so on. The measurement procedure of ENAMs is done by a red pitaya with 2 channels, 14-bit ADC, 125 MHz sample rate, and a Linux OS. It's a standalone system. It takes a 1-second sample to the RAM disk by using HDSDR FPGA module for GNU Radio used. It is authored by Pavel Demin with 1.2 MHz band segment. Calculate the power spectrum density with 305 Hz binwidth. Collect the power spectrum density of the 300 Hz samples. Do 29 steps from a few kilohertz up to 30 megahertz. At peak measurement for pulsed amplitude with 9 kHz resolution, not with 305 Hertz. Put the results to a collecting centralized database. This means 110,000 bins per measurement. Measurement takes about 5 minutes and 30 seconds. Repeat measurement by cron could be done, or system D, every 10 to 15 minutes at the moment. There can be done some more calculations on the server, mean and RMS, peak hold, and so on. Calculate and show the results for different bandwidths. It's special for the hams who use CW filters or SSB filters, and the 9 kHz for ITU recommendations comparison. Okay, I want to go to the results. The RMS of the ITU paper 372 noise figure is shown here at a residential location, measured on January 14th in 2020. It's 0 hours, and here you find 24 hours. You see there are some dark elements going through here, these. And if you look on the frequency table, you see, this is very interesting. It could be a ham band. And indeed, it is a ham band. I will explain later. Let us take one cutoff of this picture at 7 o'clock. And then we make a two-dimensional figure of it. And this is shown here. And you see the levels of industrial, residential, and rural. And you see the measurement as a blue curve. Well, this is not so good to interpret as we have a logarithmic frequency scale, and this is not optimum. So we sort of transformation, and based on rural, we see this. As you have a look here, you find very clear the ham bands here at 10 megahertz, at 14 megahertz, 18 megahertz, and 21 megahertz. These are the ham bands. Yeah, this is very important, and I think it's better to interpret for hams when you have this look and feel of measurements. deviation to rural can be shown in a heat map, and you see, well, the dark blue from 14 megahertz, it's very clear to see, and it's an overview. Here you see during the nighttime good frequency activities below 5 megahertz. Another transformation gives us noise, power, and ham bands, and in total, the blue are in total the noise power calculations, and the red are only the ham bands from 80 to 10 meter. And you see the noise level in the ham bands is above the rural and below the residential. Let me conclude. Environment EMI could be measured with an SDR system as shown in ENAMS. ENAMS is in operation since end of 2019. A comparison with the ITU radio noise regulations is a must for external argumentation, I feel so, and noise figure is dependent on time and frequency. Thank you for your attention, and I'm open for questions.
Okay, we do have a couple questions. You answered them all, most of them already in the chat window there. One of the questions was, do you have access to one or more remote sites with very low local noise to act as a kind of reference?
Pardon again, I'm not concerned. I just finished my comments on the chat.
Oh, okay. Do you have some reference sites that you can use, some multiple remote sites that you can use to establish a reference for noise?
Not yet. We have the categories from the ITU papers, and then we think, well, this is a reference when we put one antenna there. And when we have 50 stations, we have different population around, so we can see what is the noise level typically for residential, for city, for rural. Quite rural is not possible. We are crowded land, crowded country. Many populations are very crowded together. So we have 3 categories which we want to measure.
Okay, and there was a question as to why there didn't appear to be a notch over 28 to 29.7 megahertz. The other hand bands seem to have notches.
This is, okay, that's correct. There are other stations where we can clearly see these notches for 27.9 megahertz up to 30 to 29.8 megahertz. And then again, an increasing amplitude after 29.8 megahertz.
Okay, and is there a way that, or how can we get the equipment in the US and start adding data, feeding data to your server? Is that something you plan on expanding?
It's a very good question. Thank you for that. Well, at the moment, it is a project for the IARU Region 1. And the EMI managers are in discussion how to roll out to other countries. And up to now, I'm not the responsible person for it, but I think there must be cooperation between the IARU regions. And I know that the president of ARRL know of our system, and well, maybe he is interested to roll out for Region 3 as well.
Okay, and Another question, would the noise figure of the receiving system be dominated by the LNA above 10 megahertz?
Yes, the noise figure will be adapted by two channels. We have a higher noise figure for the lower frequencies, and we have a lower noise figure for the higher frequencies. And the border between both is at 8 megahertz.
Okay, very good. And is it really correct to treat the power in all signals received as contributing to the noise power measurement?
Well, the noise power measurement, and I think I don't understand the question exactly. Can you repeat that?
Yeah, the question is it really correct to treat the power in all signals received as contributing to the noise power measurement, realizing that it would be difficult to tell in some or many cases? In other words, I guess the question is, are all noise contributing frequencies created equal, and is that valid to assume that?
Well, I think so. Well, we measure for 1 second, and we evaluate the RMS value, the root mean square value of this, like it is from the standards for EMI measurements. And well, the noise power, we want to see what it is in the area where we are measuring. And we are measuring from the surrounded houses, from the people, from the multi-million devices which are spread and used for the powers. I don't know if it answers the question correct.
Okay, well, Tim Shepard asked the question. He's clarifying if there's obviously an SSB voice QSO going on, is that noise or is that signal? Can you discriminate between that?
Yes, we can. I tried to explain the trick with my 7 megahertz foil. I showed how to calculate the noise level, and I showed you, well, there could be some determinate signals in the radio bands or wherever it is, but the noise level is the estimation of the statistics of the bins. When we took out a portion of 100 kilohertz, these are 372 27 bins, and you can make statistics with bins which are more than 1. With 1 you can't do any statistics. But so we find out when there is an SSB QSO inside 100 kilohertz, there may be several SSB QSOs. We find a lot of bins from 300 hertz bin width. They are at the level of the noise in the band. Hopefully this explains it. Thank you for the question.
Very good. Here's another one that, is it possible that the notches at the ham bands might be due to notches in power line noise? I know in the US here we had broadband over power line that and the providers notched those frequencies out. Is that a possibility that some of the emitters were notched out for the ham bands, which explains why they were a much lower level?
Well, there is when the power line modems use an OFDM or similar modulation schemes, they could notch out when they are correct configured, but they are not all configured and in a good shape. So you get a lot of noise out of the regulations. And when you remember, the noise is measured during the EMI measurement, not as radiated noise. And when you use a power line system in the house, all the power lines in the house are a very well conditioned antenna. for all these noise. And when you have a power line modem in bad shape, it will make more noise than it should be. And there are a lot of other power devices which increase the level more than you like. Hopefully this answers.
I think so. And one more question. See, I lost it here. Oh yes, for any of your sites so far, have you been able to show that the daily noise variation above, say, 20 megahertz is tracking sidereal time at 23 hours, 56 minutes rather than a solar day?
I'm not quite sure if I understand.
If you can see that sidereal time, I guess is star time, right? If I understand that right. That's from Gwen.
I do not understand. What is the question? Sorry, very sorry.
So the question is, have on any of your sites that you're monitoring, have you been able to show that the daily noise variation, rather than tracking the solar time of 24 hours, tracks sidereal time of 23 hours and 56 minutes?
Well, we measure 6 times per hour and 144 measurements over the day.
Okay, so if you multiply that out, that comes out exactly 24 hours?
Yes, it's controlled by cron. And the system gets the time. The RTTY is a standalone computer and with FPGA and signal processing capabilities. So,
okay, so go ahead.
Yes, so it is exactly 24 hours and 144 measurements per day
So
at the moment.
The question is, does your noise peak precess 4 minutes per day? Is to clarify the question. So in other words, is it tracked to star time or the rotation of the Earth?
This is an analysis question. I'm not quite sure if we did this before. Well, of course, you can ask if you are measuring the noise in the surroundings, or if you measure the noise coming over the ionosphere. But we try to measure the noise first and then think on the distinguishing between noise from the surroundings and noise from the ionosphere later.
Okay, well, maybe we can go into this further in the break. We're out of time now. I want to thank you very much for a very nice presentation, Michael.
Yeah, thank you very much for the attention to my talk. And hopefully we can have it later during the break.
Okay, thank you. Take it away, George. Are you? I guess up next is Zach Lefke. I hear your audio on there, Zach. Do you want to tell us quickly about your presentation ahead of time?
Sure. I'll be going over one of the candidate antenna designs for the HamSci Personal Space Weather Station. With that, I know my video is a little bit longer than the 20-minute limit, so I'll just go ahead and be quiet and let the video go.
Okay, thanks, Zach.
Thank you.
Hello, everybody. My name is Zach Lefke, amateur radio call sign KJ4QLP, and I'll be presenting today on an active HF dipole balun, which is just an active antenna design, active HF antenna design I've been working on recently. So this actually started as part of a work project, but I'm part of the HamSci group, and the kind of need for candidate designs for the personal space weather station popped up. So I offered this as a candidate for the personal space weather station. And then the nice folks at HamSci kind of poked and prodded me to also present here at the TAPR DCC. So thank you to everybody, to HamSci and TAPR for the interest and the it's always good to know that somebody else other than you might care about the project you're working on. And it's been a great motivator for me to kind of keep going with the project and try to make it useful to folks other than just myself and the project that I need it for at work. And so with that, we'll go ahead and dive in here. I'll go ahead and warn everybody. I've got about 40 some slides to get through, a lot of figures, a lot of pictures, and only about 19 minutes left now to present on. So I'm going to be moving really quick, but everything I'm presenting on is available on GitHub, including this presentation itself. And if there's any questions or anything that I don't cover or we don't have time to discuss in the question session, please feel free to reach out to me at zlefke@vt.edu, or you could submit issues if you would like on the GitHub page if it's specific to the project. Either way, happy to talk with folks however we can get that done. I would highly encourage folks, by the way, to sign up for the Hansai listserv and participate with that community. It's a great way to ask questions and get answers, and in a way that everybody can kind of see the question and answer there on the listserv. So with that, we'll get into it. And again, I'll be moving pretty quick here. So we'll do an introduction and an overview of the overall design. I'll get into the schematic and PCB layout in a little more detail, go over the bench RF measurements. That's probably one that I'll breeze through pretty quick to try to get to the end where I'll show some comparisons, some on-air performance comparisons to a tilted terminated folded dipole and an active magnetic loop antenna that are fairly popular and out there. Okay, so introduction and overview. So who is this guy? So my name is, again, Zach Lefke, KJ4QLP. I'm research faculty at Virginia Tech with a group called the Hume Center for National Security and Technology. I did my bachelor's and master's in electrical engineering with a focus in RF engineering and communications. For my master's, my faculty advisor was Bob McGuire, N4HY, when he was still with us here at VT. He's since retired and moved on, where we sorely miss him, but it's good for him. Now he can do the fun stuff and the stuff he wants to do. So that's me on a good day, up on a tower, turning a wrench on an antenna. This is when we were raising our 3-meter dish at our satellite ground station at VT. And for those who know VT and the Space VT group that runs the Super Dual Auroral radar network, the HF radar network, that's Kevin Stern there in the bottom right, KJ4OAP. He's a colleague of mine at VT, research faculty here at the Hume Center, but he spends about half his time working at SuperDarn as their RF engineer for their HF radar. So I owe him at least a little credit because I'm constantly bending his ear about the types of topics I'm presenting on today and HF propagation and all of that. So, okay, so that's me. That's who I am and kind of where I'm from. So the design I'm presenting on today is actually not really my design. It's the active front-end electronics from the long wavelength array, which is a radio astronomy instrument. The long wavelength array is a massive array of HF cross dipoles that they use to do radio astronomy with. So it turns out that a faculty member at Virginia Tech in the electrical engineering department, Dr. Steve Ellingson, was a big part of the LWA design, and he hosts the memo series. And the memo series is fantastic. It's about 200 documents that describe the design of the LWA in detail. And the one that I pulled heavily from is document 190, which is kind of a summary, an overall summary of the front end design. It's a collection of documents that kind of go over their front end performance and or design and the performance and all of that. So I really just took their design and then tweaked it for amateur radio use. And so the table in the bottom right kind of shows the main deviations. The frequency of operations a little bit lower. They use about a $30 hybrid, real high performance component. A big driver for me is to keep the cost down. So I use about a $2 mini circuits component for that 180-degree hybrid. I have low pass filter, band pass filter, and a bypass feature if you don't want any filtering, whereas the LWA just uses a low pass filter. I changed up the DC bias a little bit, and I needed it to be a little bit more compact than their design to fit in the PVC enclosure. So a big driver for me is everything I'm doing, again, is open source, open hardware, and the KiCad design, this schematic and layout is all available at this GitHub link that I have here in bold. There's also documentation there, including this presentation, all of the RF measurements, the raw data that I took, all of that's posted there. One day I'll have this WordPress site up and running, but I don't have it yet. So the big motivator for me is that I wanted this design to be useful to the amateur community or DIY SDR enthusiasts in general. And so I wanted to keep the costs as low as possible. So that was a big driver. So this table on the bottom left shows kind of the overall numbers. So for everything you see in this top right picture, this is a crossed HF dipole with an inverted V configuration. That I'm estimating that costs about 150 to 200 bucks, including all the PVC and all of that. But you can kind of see here, if you bought 3 PCBs from Osh Park, right, you got to buy in batches of 3. And then you bought enough components to populate a dual balun, right? You could build the PCB and everything for about 100 bucks. And that's for 2 active antenna elements, right? If you add in all of the extras for the PVC and all of that, that's where I'm coming in. I'm estimating about 150 to 200 bucks, depending upon how intricate you get with that kind of thing. You can see my super advanced plastic coffee can water protector for the coax connectors. What's not included in that cost are kind of the back end components. So things like the coax and the SDRs that I'm using, I'm not including in that cost. So again, that's 2 antennas at about 150 bucks to 200 bucks, which is pretty decent for DIY sort of budgets. There are some really good active antennas out there, but they're pretty pricey. The one I compare to, one of the ones I compare to, comes in at around 500 bucks for a single active magnetic loop. Yeah, so hopefully this is within the realm of possibility for folks if they wanted to build one of their own. And everything you need to build it is there at that GitHub link. So I won't belabor this too long in the interest of time, but basically these numbers, the reason I have this in the deck is these numbers come in at about what the numbers for LWA and their front end comes in at, which all that really means is that I didn't screw anything up, or I didn't screw anything up too bad. I did screw one thing up, which I'll talk about later when I was populating one of the PCBs. The nominal input voltage, I kind of changed that up. That's worth mentioning a little more in detail. I changed that up for a 13.8 volt nominal supply, which is why I use an 8 volt regulator. I could envision a version of this that you might want to operate portable on battery power. So I wanted the design to work with that. That's one thing that the LWA design, they use a 12 volt regulator. And so if you're operating off battery and the battery dips too low below the dropout of the regulators for the board, that might be a problem. Yeah, so these are the high level performance numbers. Overall, again, it pretty much worked the way I was hoping it would, and it kind of came in right at where the LWA numbers were, so everything makes sense. So here's the overall kind of shape of the design, or what it looks like. This is a single linearly polarized active HF dipole. The big part that was new to me is I was expecting, when I first started reading the documents, I said, well, where is their radial? Do they tie it to ground? Where's the, you know, I can imagine an active side of the dipole. Where's the quote inactive or ground or radial side of the dipole? And that doesn't exist. It's, for this design, both elements of a single dipole are active elements, and they use these Galley 74 amplifiers from mini circuits. It's an RFIC, MMIC, that's the main sort of guts of it. So those 2 elements then get combined with the 180-degree hybrid. They go through a filter. In my case, I use a bandpass filter. And then there's another amplifier that's a line driver. Future versions, I might bypass that if it's not needed. If you had, for example, your SDR right up against in like a weatherproof enclosure with the antenna, you might not need that line driver there. So building in a bypass feature might be in the future here. And then the integrated bias T, the recommended way to supply power to it is over the bias T so that you can keep EMI and RFI down on the DC supply. So that's overall how it works. This is more detail about the changes of the filter design. The thing worth calling out is that I use QUX, right? This is a free and open source software called the Quiet Universal Circuit Simulator. It's similar in a lot of ways to SPICE or Microwave Office for those that have used sort of electronic simulation software. But it's free, and you can do things like filter design with it and get these nice, pretty plots and use that to, you know, for your own projects. So this slide is basically showing where I deviate. The left figure is the long wavelength array and their low pass filter that includes both broadcast AM and FM. I wanted to be able to reject broadcast FM and broadcast AM, so I put a bandpass filter design kind of swapped out for that. That said, I did want to retain a low pass filter feature. If one of these personal space weather stations happens to wind up in a nice radio quiet environment, maybe we don't want to filter out the broadcast AM band. So I have an option in there for using the low pass filter. So this is showing low pass filter response on the left, band pass filter response on the right, but these are the simulated numbers. You'll see the measured numbers later. This is the overall schematic. I won't belabor this in the interest of time. It's similar to how that block diagram works. Maybe the one thing to call out in the bottom left is I like to use solder jumpers for sort of circuit selection. So that's what this little network of solder jumpers is. The other thing to call out is that in the original design, the first time I built this, I used 30 ohm resistors and a 33 ohm resistor to bias the amplifiers. I was intentionally trying to make it a little bit hotter with a little bit more current draw, which should have improved in linearity. In the end, it didn't really have that much of an effect. So I ended up going back to 39 ohms. So everything you see, I'm actually using 39 ohm resistors for all three of the amplifier bias circuits. So just watch out for that if you pull the design as it sits today, 12 September 2020. It says 30, 30, and 33, but actually it should be 39, 39, and 39. Okay. So the way this works is you get one of these boards. If you want a cross dipole design, you actually populate two separate boards. And so this is what the board looks like. If you were to flip this board along the dashed red line here, it would look like the figure on the right. And you can see, like, for example, down here in the bottom left, this is the SMA connector for the east-west elements. And when you flip it over, that SMA connector is now up here, and that lines up with this cutout. Similarly, this SMA connector, if you had a second board, would line up with this cutout. And the idea is you take two of these boards. When you get them fabricated, there's no solder mask or silk screen on the bottom of the board, right, on the ground plane side. So this is all bare exposed metal here. And the idea is you take two of these boards, populate them, flip one over along that axis, and then bolt them together. And this is kind of what it looks like, right? So you've got the one SMA connector down here, the other one up here. And that's what the sort of weird nomenclature around these four larger holes are, right? So the west and east element, right? So west-east, east-west element is on the top of the board, and the connector for that is down here. But then the board that you flip over and place on the bottom, what was the west element now becomes the north element, and what was the south element now becomes the east element, right? And I think I said that last one backwards. What was the west element becomes the north element. What was the east element becomes the south element. And that's where this north-south connector is now located, right? And so you attach the actual elements directly to the board. In my case, I use ring terminals and number 6 screws to do that. So here's what the boards look like when they're actually populated. And again, kind of the one on the right is the one to pay attention to. This is where there's the east-west connector, and then the north-south connector, and then the north-south element is kind of top-bottom of the page, which is the board that's on the bottom. And then the top board is the east-west element, which is all of this up here with its connector right here. So that's how you kind of put together a cross dipole configuration for this. If you wanted, you could do a single polarization and it would look just like it looks on the left here. Okay, so this is just a little more zoom in detail. Like I mentioned, I like the solder jumpers, so I use them heavily to select. So there's the low pass filter on the left, the band pass filter on the right, and then you can see in the solder jumpers that I'm routing the signal through the band pass filter down into the driver and out. Other things worth mentioning, there is a gas discharge tube for some lightning protection. There are also these output protection diodes. They're actually on all of the RF legs, and they serve a little bit to do some ESD protection. I did also do a separate bias T design for back in the shack. It's about $5 for 3 boards from Osh Park. Everything is available again on the on my GitHub page. There's a separate project for the bias T layouts, and you can see everything sort of packaged up here, where I put 2 of the boards inside an enclosure so that I can power both the north-south and east-west active dipoles. I'm going to gloss through this section in the interest of time. Basically, I took a large number of RF measurements. The way I did it was populate all 3 boards, do the benchtop measurements for all 3 boards. This is kind of what it looked like. All of this test equipment is not mine. I think the only thing in this picture that's mine is the Astron power supply and the Fluke multimeter. Everything else is owned by Virginia Tech and the Hume Center. So thank you to the Hume Center and VT for letting me use all this equipment. This is in my garage. It's during COVID-19, which I guess one silver lining of it all is it's easier to take expensive test equipment home as long as you sign out the paperwork and do all that right. So anyway, so that's what I use to take all the measurements. Like I said, I'm going to gloss through this. I'll quickly mention when I populated one of the boards, I noticed kind of degraded performance on the low end when I jumped ahead on the air with it before I did the measurements. And it turned out I had bad solder job. Everything is surface mount components that I do by hand with my super advanced hot plate technique here. And basically on the first board, I used way too much solder. And so you can see these solder beads built up on the inductors, which threw off the bandpass filter performance. So I was able to compare this to the good board that I had and kind of meticulously go through and ohm out each inductor until I discovered the bad culprits here. So I used a hot air gun, pulled them off and replaced them, and everything was hunky-dory. So again, I'm gonna breeze through these real quick so that I can get to the comparisons because I only have about 3 minutes left in the presentation. So again, all of this data, all of these plots, everything is on the GitHub page. This deck is on the GitHub page if you'd like to go through things in detail. And all of this was summarized in that top level table for the overall RF performance. So to kind of close things out here, and again, even with this, I'll move quick. I wanted to get on air and measure, or compare rather, not really measure. There's nothing super detailed here. But just kind of do a one-to-one comparison of my active antenna design with a tilted terminated folded dipole and a magnetic loop. So here are the models that I used. Again, these are Hume Center owned equipment that I was able to take home and get set up at the house. This is how my active design was set up. So when I say the north-south antenna and the east-west antenna, I mean the physical orientation of the antenna elements themselves, not the sort of broad side of the pattern, right? It's a dipole, so the north-south element actually has maximum energy to the east-west, right? But when I talk about alignment, I'm talking about the true alignment of the elements, right? So the north-south elements are pointed towards true north. And then all of that is tied through some lightning arresters into my bias T that I showed into a dual band software-defined radio. So again, this is not my software-defined radio. I wish I owned 2 X-Series usurps. I was able to take these home for work or from work. So thank you again to the Hume Center for letting me use these. And inside these guys are 2 LFRX daughter cards so that I can measure and receive HF signals. You can kind of see the tilted terminated dipole here. When I took this picture, I didn't have the magnetic loop set up. I set that guy up about here. And then there's my inverted V cross dipole that I took the measurements with. So here we go. I'm going to burn through these really quick because I'm getting close to the end here. But basically, you can see the AM filter appears to be doing its job. It's suppressing the tilted terminated folded dipole is on the left, and then my antenna is on the right. So it's suppressing AM band pretty good. The performance at about 3.8 megahertz is better with the larger antenna, kind of as expected. It's never thought my antenna would be better than a T2FD. It is cheaper though, and so you can see that it's halfway decent at 3.8. Here it is at 5 megahertz. Things are starting to look pretty good. You can even make out some of the CODAR transmissions here, the coastal ocean radars. Here we are at 7.2 megahertz. Things are, again, starting to look pretty good. So you can see kind of the full band here. Here's the 10 megahertz WWV emission. You can actually see now I'm starting to get a little bit better SNR compared to the T2FD. Here's 14 megahertz. And again, things are looking pretty good. The noise floor is a little bit higher, but overall the SNR is doing better than the T2FD. Here it is compared to the magnetic loop. Again, I'm filtering out the AM band, so you can see all of this is the AM band coming through. Down the street, at less than a mile from me, is a broadcast AM tower. So that guy's still poking through, but overall, there's pretty good suppression of the AM band. Here we are at 4.5 megahertz. Again, you can see the CODAR transmissions in there. Here we are at 7.2 megahertz. Things are starting to look pretty good. Again, a comparison at WWV, 10 megahertz, and pretty much equivalent performance at 10 megahertz, and then things are looking pretty good at about 14 megahertz. I didn't measure above 14 megahertz because of my local QRM conditions are pretty bad, so it kind of wasn't worth, the noise would look like I'd be comparing noise to noise. So next steps, I got a lot more documentation I still want to get together. All that'll be on the GitHub page. Everything I've done so far is already on there. I did do some initial tests to compare the PGA 103 active device to the Galley 74. And I swapped that out on one board. It was a little bit too hot. I basically got crushed by that local AM station that made things go pretty badly nonlinear. It really needs more investigation. I didn't do anything in great detail. I just kind of went back to the Galley 74 design because it works pretty well. Future PCB revisions, just a couple of things to clean up. It's a little tight in the PVC enclosure that I use, so ways to make that a little easier to assemble everything. And then once that's good to go, there's a lot of areas for experimentation. So I've kind of focused on the Balun design today. All I'm using are about 5-foot wire elements. There's a lot of exploration that can be done there for what type of actual elements do you want to use for this. The LWA, for example, uses a blade design that helps increase overall performance and sort of the wideband nature of the antenna. And really what I'm trying to get at is ordinary and extraordinary mode discrimination. I want to be able to see the different polarizations and measure polarization of the incident wave. And so that's kind of one of the reasons that drove this design in the first place. And that's could be very useful and helpful for science investigations for HF radio propagation. So that's kind of what's on the near horizon for me. And with that, I'm about 2.5 minutes over. Hopefully there's enough time for some questions. This just shows sort of the overall assembly process, right? You go from the board design, bolt on the wire elements, shoehorn it into the PVC enclosure, have the jumpers there for the BNC connectors, everything assembled up, and then I have the my little PVC radome elements that I used to house the wire elements. And again, they're just 5-foot, like 14 gauge wire or something like that. And then all the references down here for all the different things. Try to do everything open source. So all the SDR stuff you saw earlier, that's all Gnu Radio. All my PCB designs are in KiCad, Quux for the simulation, driven by the LWA design. And with that, I'm pretty much done. So thank you to the HamSci group, and thank you to the TAPR folks for giving me the opportunity to speak today. And I think at this point, it's time for questions.
Okay, we have about 4 minutes for questions. I think, Zach, you answered most of the questions in the chat window. There was maybe a couple that you didn't get to. A question about the backside grounds of the two boards. Are they isolated or are they connected together?
They are connected together.
Okay, and are there any analyses of the antenna's performance on WWV frequencies?
Yeah, so at my location here in Virginia, I do most of my on-air testing at night when I'm not at work. So 5 megahertz is pretty good. 10 megahertz is also pretty good if I can get down there early enough. So yeah, I quickly breezed through a lot of those plots, but I'm seeing 20 plus dB of SNR with WWV signals, kind of at 5, 10, and 15 megahertz.
Okay, and John asked, does the operating voltage impact your 1 dB compression point numbers? I think you answered
right,
that.
Yeah, so I kind of answered that with my bias changes. The actual active devices are biased the same. Right now, actually, the recommended bias points per the mini circuit data sheets. But the thing that really affects the linearity more so than the change in the input to the voltage regulator is the output protection diodes. So those guys, I really glossed over really fast. Those guys are there to provide a little bit of ESD protection, but really what they do is they start clipping when you get into the higher input levels. So they actually clip long before the active device itself would saturate and go nonlinear. So there's versions of this design I could see where you might not even include at least the output protection diodes. But overall, no, the change in the kind of higher voltage regulator doesn't really affect the bias points of the amplifiers because I changed the circuit to match the correct bias voltage for each device.
Okay.
Hopefully that was clear.
And Graham asked if since your bandpass filter is after the amps, do you see any overload issues on the input amplifiers?
Yeah, I highly encourage you to join the HamSci listserv, and maybe we can dig back through the history of back and forth conversations on this. Yeah, so that's one of those great classic engineering opportunities for the type of answer that, it depends, right? For me, where I'm operating, things are okay the way it is. But yeah, we've had a lot of discussions about this on HamSci. I think my quick comment in the chat was everything I've done so far is open source, open hardware, and it's all on GitHub, so experimentation is highly encouraged. I don't have all the time in the world. I wish I had to do all the experiments and testing, so I would love it if somebody grabbed this design and did a ×2 on the filters and put them out in front of the Galley 74s, and then do some comparisons.
Okay, it sounds great. And there was a question whether TAPR might offer kits, and I think that was, if you want to work with us, I think that would be a definite possibility. Also, can you post your GitHub address on the chat for people to go look at what you've done? And I think that's all we have time for. So thank you very much, Zach.
Well, thank you very much.
It was very good.
Appreciate it.
Okay, so I guess we're ready to roll right into the next talk. We originally had Bob McGuire talking here, and we were sad to hear that Bob McGuire couldn't make it, but once Michelle stepped forward and helped us out, we were considerably less sad, and we're really appreciating the fact that she took the time to fill in for Bob, and she's going to have an awesome talk here. So go ahead, Michelle, tell us about what you're going to talk to us about.
Hello there. This is about the Gnu Radio and the runtime, or the program beneath the Gnu Radio companion that actually handles the DSP. So for a while now, we've been looking at runtime improvements. The runtime is architected as a data flow, meaning it sends streams of data from source blocks to sync blocks through all sorts of different other blocks that operate upon it. And this does need some improvement. There's been lots of public discussion about it. And we are going to tackle that coming up. If you're interested in this sort of thing, we have a public session on this coming Friday at Gnu Radio Conference, which runs all next week. And it's an open public workshop on Friday. So check the schedule at gnuradio.org and join. However, there's another way to look at runtime improvements, and that's to back up and look at whether or not the data flow methodology really serves us in a modern context. So that's what this talk is about, is raising the possibility of returning to something that was presented at TAPR DCC back in 2007 and 2008. And that's using finite state machines as standalone computational engines for doing the DSP work. Back to you.
Go ahead, George, if you want to run the video.
Visuals driven by text are how we accomplish mass communication through television and film. Visual presentation of text documents is the content our internet is made up of. Visual manipulation of the code contained in blocks or a canvas is a compelling and powerful way to control the electromagnetic spectrum in GNU Radio. Our engineering is heavily influenced by our understanding of narrative. We tend to think of progress in terms of journeys and quests. We believe in connected streams of existence. We believe that those streams obey the passage of time. These streams encounter various obstacles in the way. There's a start, a development, a climax, a resolution, and a finale. The idea of a single stream of consciousness is embedded in our natural languages. This way of thinking extends into our work as programmers, developers, and designers. We make assumptions about the software and hardware that we all use based on our understanding of time, observations, and what it means to process, and how we measure progress. The standard way to draw a schematic circuit diagram in the United States is left to right data flow style. Most of us write computer code linearly. The vast majority of code will not compile if you fail to define a variable before you use it. If digital signal processing code is a textual poem, and if the two-dimensional graph representation of a GNU radio work is the visual art of the narrative, then we have a place to start discussing something about GNU radio that has been true since the very beginning. We have an architectural dedication to data flow. This stops us from doing some of the things we want to do with the GNU radio framework. In GNU radio, streams of data are sourced. They flow through blocks that act upon it, and the results sync either into hardware or files. All data is shared. It's seen and touched and often changed by everything in the path. Switching the data or having one data type run out while the other data type continues can and does result in errors. We came by this data flow approach quite honestly. One of the earliest demonstrations of GNU radio by Matt Edis and Eric Blossom was at the 2007 Tucson Amateur Packet Radio Digital Communications Conference. There were contrasts drawn with another project that also got a lot of attention with presented work that weekend called DTTSP. For those that wonder why the GNU Radio Conference organizing team has made so much of an effort over the past 2 or 3 years to coordinate with DCC, it's because of long-standing connections and interactions between the two communities. That's a big reason. That demonstration, which had a BPSK demo and an HT emulator, made a big impression and sparked a lot of conversation and development. During discussions between the participants, it became clear that the constraints on the two projects were different. Early decisions about how each project addressed their different sets of constraints had lasting repercussions. Previous software work in the relatively new field of software-defined radio was accomplished by doing things like all the processing inside hardware interrupts, in things like Visual Basic. This included handling the screen and user interface. While this met some performance goals, there were some obvious practical limits to this approach. DTTSP filled a need for a cross-platform body of software. It became an SDR engine that would run separately from the user interface and other functions. Signal processing was done by multi-threaded processes running somewhat autonomously. It was multi-threaded from the beginning. Design constraint was to provide something called minimum latency. This is not the same as real time, which incurs additional and, in this case, unwanted constraints. The reason latency was so pressing is because the most commonly used hardware at the time had a hard switch between transmit and receive. DTTSP was designed under the assumption it would have to manage audio hardware. Latency was the primary constraint. GNU Radio prioritized ease of programming in Python. This became a fundamental constraint for GNU Radio. The data flow approach that prioritizes ease of programming in Python is a very good one. Data flow methodology is authentic and legitimate digital signal processing. GNU Radio is highly successful. But data flow is not the only way, and restricting ourselves to a data flow approach enforces a limit on our work that we as a community increasingly care about. This limit includes cognitive radio, machine learning, deep learning, and expert systems. A data flow approach where we gather our fellow sample friends and walk to Mordor through filters, amplifiers, descramblers, matrix manipulations, multipliers, shifters, and so much other landscape cannot deliver an expert system. A cognitive radio is an expert system. The signal processing components necessarily occupy only a corner of that structure. A departure from strict data flow design would allow GNU Radio to adapt to recent demands of signal work and would more easily enable cognitive radio. Consider any two arbitrary blocks. One is a source and the other is a sink. How do you gracefully disconnect one block from the other and switch it somewhere else on the fly? If we cannot do this, then we cannot do cognitive radio. GNU Radio does not formally represent all the states that a block can be in, or require that blocks define all their states. Cognitive programmability is outside the digital signal processing framework. In order to allow us to incorporate cognitive radio, we have to put the digital signal processing at the sensors and evaluate states in the central cognitive brain. This brain decides what state transitions to make based on what is coming in from these sensors. A probability model or utility computation makes state transitions based on the reported observations. The sensor says, I am attempting to demodulate and it's suddenly producing hash of a particular type. The brain goes, oh, we need to change things. I think I see the problem. Try this instead. In accordance with the utility and the policy, The brain either changes the parameters of the demodulator or invokes someone else's assistance. This means the data path may have to be switched somewhere else without crashing or restarting. That's why cognitive radio can be very difficult to implement with a data flow approach. We don't want to move the digital signal processing and the data flow to the brain. The brain needs to look at the states. In simplest form, the brain is watching essentially a green, red, light, a stop-go signal on each of the DSP functions. If we see a red light or a stop, then we dump metrics on how well that sensor has been doing the processing. We can use a data flow approach in the sensors, but we will never get real cognitive radio traction if the brain is inside the data flow. The brain has to be separate from it. The alternative to data flow in terms of mathematics is to do just this. We separate what we do into blocks that are as independent as possible. The blocks are all separate computation engines. We copy the data whenever it's needed in order to do whatever math is required. A module or block can agree to hand over a copy of its state, but that's a capability that needs to be built explicitly. We give up the overarching narrative of a two-dimensional directed graph with unbroken streams of data in favor of distributed processing, where there may be no explicit stream, and we do not share data. We understand that we cannot know the entire system state without effort. It is possible to infer the state, because you can query all the other individual pieces. You can say, "What are you? What are you doing?" You can retrospectively reconstruct the global state at a particular point in the computation. However, there is no supervisor that knows the entire state, and that is a consequence of not sharing data. We simply get done with what we need to get done as a state diagram within our block, within some specified amount of time, or else we raise a flag that we are the critical path and we have failed. That state diagram approach is crucial. Each block is forced to be a state diagram. There are no undefined states. Unused states are handled in orderly and expected ways. Data arrives, it's processed, and leaves. We know the limits of each block in terms of timing. If there is no shared state and no shared data, then exhausting all the possible state transitions is a finite problem. No block will ever explode. They are robust. This is the whole game in terms of being able to gracefully switch from one block to another as expert systems and cognitive radio require. Each individual block or module has to know what states it can be in and what transitions need to occur. There has to be a state transition diagram for each individual module. This means leaving the two-dimensional data flow map. We have to take a step back from our dedication to the journey to Mordor. The quest to get the one ring from source to sink through blocks, never giving up control and maintaining our unique soul and special trajectory through time, must be abandoned. A secondary and related problem is the lack of control over latency. There isn't a good way to get visibility on problems with latency. You might not be able to tell from within GNU Radio that there is a serious problem with your USB and your Type E amplifier project. Everything might appear to be completely fine within GNU Radio, but the glitches in the produced signals are not acceptable and cannot be used to control your amplifier. Do we solve both of these problems at the same time? Can we improve our approach to latency while also enabling cognitive radio? Are the latency issues really that bad? Our current data flow approach is just a stream, and it's up to us to keep track of any time-based ratios or the calculations will not work. The learning curve and debugging on this is time-consuming. Latency control improvements are usability improvements. The throttle block exposes the latency issues. It usually takes a sample rate and is generally used in the absence of hardware to not let the flow graph run rampant. But even with a throttle block, there is no guarantee on the timing. With discipline, practice, and well-conditioned problem sets, a lot of excellent software-defined radio work has been done, is done today, will be presented, and will continue in the foreseeable future. DTTSP didn't have to worry about this because all the computation was being done as close to locked synchronous fashion because of the tight integration with hardware, specifically audio hardware. Best effort delivery of data provided a large degree of control over latency. Decoupling as many of the systems as possible and forcing them to be finite state machines doesn't just enable integration of things like expert systems, it also improves visibility and control over latency. Blocks that are programmed from the point of view of a state diagram, and not only as a data flow, can take advantage of the benefits of a minimal latency mindset. If you want someone else to process something, then you send a copy. Let the other block follow its own clock. It might be the same clock that you're following, but it might not be. We may have memory subsystems that are operating at one rate, I/O at another rate. We may have scheduling issues dealing with weird branches, and we may be sending data to a GPU for yet more processing. This means that architecture becomes more like a chip and much less like a directed graph. And this means the design of the signaling between separate blocks is critical. The most appropriate synchronization mechanism may be a barrier. Unfortunately, barriers are the least popular mechanism for synchronization in terms of language support. Barriers are best known from high-performance Fortran. So why barriers and not messages or semaphores? Well, barriers may provide the function we are after. We do want minimal latency. We want computation engines to finish within certain amounts of time and signal appropriately at some preordained time. Barriers can be thought of as walls. Everyone has to reach that wall, and they have to be listed on that wall before they can proceed past that point. There's another wall further down. The computation is carried out by independent blocks that coordinate at known barrier points. So can C++ do this? Quite possibly. Would another language be better? Quite possibly. Should there be a custom design language for GNU Radio? Well, sure, why not? We're worth it. But this goes back to the fundamental and productive constraint of making GNU Radio easy to program in Python. And this is not a constraint to relax lightly, if at all. What about a language like Erlang? And what about GNU Radio Companion? Well, you just got curvy lines. You want to blow all that up for disconnected blocks that look like so much wreckage on the Pelennor fields? Well, let's pretend that we rewrote the set of blocks we want to use as finite state machines. And let's say we decided to do this in Erlang, and we got it working within a Pythonic structure. In a full-blown Erlang application, the lowest level processes can be designed to do error trapping and recovery, but they usually aren't. And this is deliberate. The lowest level processes are really children of supervisory processes that let the children fail. The supervisor then restarts them, or whatever else is appropriate to the policy. Those supervisory processes are the primary interface of the low-level function to the rest of the application and to the world. A GNU Radio flow graph, even in this extremely unlikely case of the rise of Erlang, can still serve as the graphical user interface, and it can still define our radios. This means we don't lose GNU Radio Companion. We can choose to interpret flow graphs as a fictitious map of connections among low-level blocks, which all have invisible supervisors behind them. Or we can think of the blocks as actually representing the supervisory functions, which maintain the fiction that only the data flow part matters, while the supervisors make everything hygienic. So is MATLAB a potential engine for GNU Radio computational blocks? Well, no. MATLAB is not expressive enough to be an interface for programming GNU Radio. MATLAB does have frequent and productive use in support of an enormous variety of digital signal processing, simulation, and work. However, there's a lot that simply cannot be done in MATLAB from a programming language perspective, and those things are required for GNU Radio. This is especially true if we are concerned with doing cognitive radio work. If there was a way to reliably control the latency in the interface to and from MATLAB, then we could consider using it for live computation. These ideas are not new. They were presented at DCC starting in 2007. They were perhaps introduced at a time where the hardware, the software, and the community programming expertise were not quite up to execution that would deliver the results required for enough performance to justify the work. However, we are past that point now. Therefore, we are looking at expanding the runtime of GNU Radio to include potential architectural changes like what is being discussed here today. Questions, comments, and critique, welcome and encouraged. Thank you to TAPR for the opportunity to present this work today. It's an honor to be part of such a long and rich tradition in open source software-defined radio.
All right. Thank you very much, Michelle.
You're welcome.
Very interesting and lots of food for thought. Do we have any questions? Got some positive comments, but this mostly, I think, is food for thought and thinking about things. I know, apropos to your talk, mostly a comment is we in hardware, we do things like boundary conditions and change for interaction between finite state machines. So that kind of fits into your whole methodology of the finite state machines versus the flow architecture.
Yes, that's actually very relevant to the larger issue of where this sort of work fits in. In GNU Radio, there's a very wide dynamic range in the type of people that use GNU Radio and contribute to it. There are a lot of people who come from the software side, from computer science, from programming. And there's a lot of us, like you and I, we've talked many times about hardware background. We come from the hardware side. And meeting in the middle and trying to make a framework, a DSP framework work for both software-centric and hardware-centric people has over the past 10 years been a quite remarkable experience and thing to see. Yeah, so a lot of people that have actively worked on GNU Radio as a programmer, they're not familiar with finite state machines, really. They might have seen it once or twice in school, but they view the digital signal processing from a computer science point of view. So these sorts of discussions on how to configure and renovate the runtime, they're not an either or. This is sort of a both and, because we're always going to need the data flow approach. But putting these ideas in for finite state machine work to have it separate computational engines, where the GNU Radio runtime starts to look more like an ASIC or an FPGA, and maybe less like a flow graph or a schematic.
Yeah, you've got some background noise on there too that's coming through, so you've got a good mic there.
Oh dear. Okay, let me attend to that.
But anyway, we've got lots of great comments. Here's a question: any considerations of distributed processing over multiple PCs? If you've got your noise issues handled there.
Okay, I'm back.
Okay, so are there any considerations for distributed processing over multiple PCs?
Yes, there was a demonstration that was, I believe, also at DCC, maybe 5 or 6 years ago, where something like this was attempted. And yes, that is definitely part of the discussion moving forward. We're getting to the point where the hardware to support these sorts of things is now plentiful and available, and we have enough horsepower to do it. So it's more of a question of trying to adapt our software expertise to distributed and parallel programming.
Yeah, I know inside FPGAs we use state machines all the time, finite state machines all the time, but they're not really elevated to the level of your description. So it's very thought-provoking presentation, and lots of comments on that too. Let's see. NASA had done distributed processing requests for large programming crunching. That was a comment.
Correct.
And yeah, this is great. Every time I hear your voice, I learn something new. So
thank you. That's made my day.
And raising the definition of radio to a whole new plane.
Oh, I see a question that says microservices with state. I hesitate to automatically agree, but what I know about microservices is that may actually be related or accurate assessment. Let's see, the status of the project. The SourceForge. I'm not sure about SourceForge, but GNU Radio is on GitHub and has daily updates. So I would start at gnuradio.org, gnuradio.org, and then you can either go to the issues page or the on GitHub for GNU Radio, or join the mailing list. And our conference, oh, I see, I'm sorry, I misunderstood. DTSP, yeah, I don't think that SourceForge is updated. I think that the project moved off to GitHub, and it has not been updated in many years. The authors were happy with the way it worked. It then was adopted and moved on to several other DSP cores, which went off into the commercial realm. So that may be why it does not appear to be, the open source original version did not appear to be updated.
And we have a question from YouTube, a comment rather. A first good step would be to include a Verilog simulator in GNU Radio. Is that something you want to comment on?
Oh, sure. There is actually a GR-Verilog out-of-tree module, and I'm not very familiar with it, but I learned about it on the mailing list, and it's on the list for things to get around and look at. So the GR-Verilog exists.
Is that part of the normal distribution?
There is a core distribution with lots of blocks, the most commonly used ones. But a lot of these functions, especially with things that explore machine learning and cognitive radio and like the GR Verilog and GR satellites, those are called out of tree modules. You would find them from a separate distribution. And then of course, that begs the question and raises the immediate possibility of, wow, you have version skew and people have to keep their out of tree modules up to date. So yes, that is a recurring perennial problem, just like with any large software project. Let's see, how can we learn more about this without delving too far into the hood, into the internals of GNU Radio? That's a really good question. It's almost, it is actually very hard. The learning curve with GNU Radio, I'm sure anybody that's used it would agree, is pretty steep. Some people would consider it to be a wall. And talking about the runtime, you're diving into the deep end. So unfortunately, there is a bit of digging around under the hood required to learn about the internals of GNU Radio. You're messing around with, something that controls one of the fundamental forces of nature, and it's a lot of math. So unfortunately, it is kind of a hard slog. The best way to learn more, I think, would be to join the mailing list and the Matrix server. We have a chat server that you can get to from gnuradio.org, and then just start talking to people and asking questions. There's an awful lot that you can get without having to actually go read the source code.
Is there an active, there probably is, but I want to give you a chance to give a plug for it. Is there an active users group where you can ask questions and get information and get help with things that you're stuck on?
Yeah, there's a large and active GNU Radio discussion email list. And then there is the chat server, the Matrix chat server, chat.gnuradio.org. Both of those places are a really good bet for getting explanations and attention. Both of them have almost all of the active core developers on them, and they will respond to your questions. See, there's a question about the workshops. I can address that. The workshops, like from National Instruments and Xilinx and people like that, it's up to the workshop, the person running the workshop or the organization running the workshop to record it. And some of them have agreed to make them publicly available after the conference next week. The sessions, the Friday Developer Summit sessions and the runtime discussion is one of those, will be publicly available and recorded. And so that's open to everybody.
And a question above that, see, should I just await the conversion to Erlang, which is really readable?
Yeah, I'm actually a big fan of Erlang, coming from the telecommunications background, and it is actually designed for DSP and SDR. It's remarkably well matched because of the point of Erlang and the reason why it was developed. So I'm with you. I've advocated for it. I'm somewhat lighthearted about Erlang being employed for a runtime here, but there's a seed of a kernel of truth there, in that it would actually be a very good choice. The neat thing about the GNU Radio Companion, which is what we all see when we drag and drop all those little blocks, the GNU Radio Companion sits on top of the GNU Radio runtime. And there are movements to make multiple runtimes, like we're talking about here, to have multiple runtimes that maybe coexist. But there's also a third one, the OpenCPI framework, that we're going to talk about and present at the GNU Radio conference this next week. That is handling some of the functions of the runtime. So making this a modular thing and improving both and giving people as many possible tools in the toolbox is the overall point of the project.
Yeah, and so I would also encourage all the people who have questions on GNU Radio. As Michelle said, the conference is coming up next week. So here's your opportunity to learn more than you ever wanted to know. And do you want to give a little bit of a quick description on what they might expect next week, Michelle?
Oh, sure. Yeah, it's a virtual version of our in-person conference. And we were really looking forward to being co-located this year with TAPR DCC. We, fortunately, TAPR and also GNU Radio have postponed our in-person event to 2021. But this conference is very similar to the sort of thing that you get at TAPR DCC. There are presentations by people, and there are some social events and some workshops like this, and something sort of like the Sunday seminar. So what you will see next week is recorded and live presentations, some keynotes, and a lot of workshops, and then the developer summit on Friday. So a very similar sort of technical level as you would get here. There's a variety of different backgrounds represented at the Gnu Radio conference, ranging from hobbyists and researchers, lots of amateur radio operators. One of our keynote speakers is Becky Schoenfeld from QST, from ARRL, all the way to people that are very academic, and everything in between. Also, industry participation. Gnu Radio, its use in industry is also a big influence on what the DSP framework does. So very similar to DCC.
Okay, so can you post the links to the GR conference in the chat window?
Yes.
The ones that you just mentioned?
I think when someone very kindly earlier posted, and I can try to get back to that and copy that from Shirley. That was very kind to post the longer link. So I'm just gonna, unless somebody beats me to it, I will. Oh, looks like someone. Oh, someone did. Okay, yes, that's the link, direct link to the conference.
Okay, and there's one other question I don't think we touched on. Prior discussion on the GNU architecture talked about moving away from block data flow to service worker pool. Would did you?
Yes, I read back. That was I know about this prior discussion, and I'm not sure about the status of that, about the service worker pool effort. But yeah, finite state machines would fit into this model. I believe that the service worker pool was how to fit the workload to a general purpose processor. And that has always been a big discussion and a continuing need as we all see hardware and software, evolve at sometimes different rates. So yeah, it would fit in. To me, the finite state machine is essentially the work function in a block. And if you say, okay, we are going to force you to be a finite state machine, and we're going to allow you to either be in the stream or you can punch out. We just now have to be able to ship data to you, and you have to be able to respond. So to me, there's two things are complementary.
Okay, very good.
Yes, the past GRCon workshop papers and presentations, there's pubs, P-U-B-S, pubs at GNURadio.org. And that's all of our previous work. Everything is on YouTube. So it's just like TAPR DCC, we publish as much as we possibly can and make all of the presentations as widely available as possible. It's a shared value between the two communities.
Okay, any other questions for Michelle before we transition to break? Let's see, I don't see any. So anyway, thank you very much, Michelle, for a very thought-provoking presentation.
Thank you,
You're very
Michelle.
welcome.
Okay, so we're going to segue into break time. The chat window will remain open, and you may hear some side conversations during the break, but we will see you at the top of the hour. Okay, John, you can take up the moderator duties, and there's Nino. Hello.
Glad that you're here, Nino.
Hi.
Hi there. Why don't you just do a very quick introduction of yourself and what you're going to be talking about, and then George will start the video rolling.
Okay, great. Hi, everybody. I'm Nino Carrillo. My call sign is KK4HEJ, and the video is going to be a quick description of my improved layer 2 packet protocol, IL2P. And I go into describing more or less the structure of the protocol and some of its features, and why I decided to include some of those, and it'll go about 20 minutes. Hi, everybody. My name is Nino Carrillo. My call sign is KK4HEJ. I'm going to tell you about my improved layer 2 protocol, which I call IL2P. This is what I'm going to present. So my motivations for development of this protocol were to make a more robust link layer for narrowband packet radio. The de facto standard now is AX.25, which is widely deployed, and I think it has a few opportunities for improvement. For example, AX25 lacks forward error correction, so a packet will be rejected at the receiver even if it has only a single bit error. Some numbers to go along with that on what that can cost. Let's take, for example, a 256 byte packet. That packet has 2048 bits. Let's say that the bit error rate for your link is 1 in 100,000. At that rate, the chance that your packet gets through, if it's 256 bytes long, is about 98%. The chance of one bit being flipped in those 2048 bits is about 2%. If the BER drops to say 1 in 10,000, then the chance of that same packet successfully decoding is about 81%. And let's say the bit error rate drops further to 1 in 1,000. Well, now the chance of receiving that packet without a single bit error in any of its 2048 bits is only 13%. So there's an opportunity to improve the efficiency of some links that have relatively low signal to noise ratio or a moderate bit error rate. It might be possible to improve those links with some forward error correction. There's been an attempt to add forward error correction to AX.25, that's FX.25, which was specified in the early 2000s. And it was a lot of good work, and there's some great ideas in it. FX.25 is significantly less efficient than AX.25, and it's rare to see implementations out in the wild these days, though I think there are some people working on that, which is great. I think that one of the motivations or reasons that FX25 is a little bit less efficient is that the designers wanted to maintain backwards compatibility with legacy hardware and on-air hardware and modes using AX.25. So FX25 basically wrapped a Reed-Solomon code block around a complete AX25 packet, including bit stuffing and all. To do that, the designers had to zero pad to fill in the code block to the required length for proper Reed-Solomon encoding and decoding. There were several different code blocks and sizes available with FX25, and those were identified with different correlation tags, which are like sync words, that are 8 bytes long, and they're unique. And the receiver would have to search for these in the receive bit stream to identify what kind of code block followed that correlation tag. I have another method that I'll present that I use in IL2P that's a little bit different and allows a more efficient use of the data in the code block, the Reed-Solomon code block. I also wanted to integrate bit scrambling into the protocol to support non-audio modes, modes that might require DC balancing in the bit stream. Also, IL2P incorporates a 24-bit sync word, 3 bytes, which is more useful for detecting the start of a packet than, let's say, searching for the 8-bit sequence of the AX25 flag OX7E, right? The 7E hex value. That pattern, when searched for in sliced random noise, that occurs very frequently since it's only 8 bits long. Every couple hundred of bits that go by, a detector is going to see a flag in the presence of random noise. As you make that sync word longer, then it's less likely that random noise generates a matching sync word, which is something I take advantage of in IL2P. I also wanted to move away from bit stuffing. It works really well as a packet delimiter, especially in high signal-to-noise ratio situations, but I think it's cumbersome to encode and decode, and there are other ways to delimit a packet. And finally, I wrote this protocol with an eye towards integrating it with existing host packet software. In other words, programs that utilize keep it simple stupid interfaces, QESH interfaces, to talk to the TNCs. So here's a picture of the IL2P packet structure. You'll see it starts with a preamble. I use an alternating 1 and 0 sequence as a preamble rather than a sequence of flags. Flags don't really have a meaning in IL2P. That can be a variable count. It's obviously based on the type of radios used on the transmitter and the receiver. Then the sync word occurs, which is 3 bytes long, 24 bits, and it's always the same pattern, which is shown there on the screen. That 24-bit sequence has an equal number of zeros and ones, so it's DC balanced. The IL2P header is always exactly 15 bytes long, and within the header there's enough information for the receiver and decoder to determine what's following the header, which will be up to 5 payload blocks, though a header can be sent alone without payload blocks as a valid packet as well. Error correction is applied to the header and all subsequent payload blocks. And each payload block, as well as the header, is a Reed-Solomon code word on its own. So some background on Reed-Solomon error correction. Reed-Solomon codes are block codes, which means that each block is one complete code word. In order to decode a Reed-Solomon block, the decoder needs to know how long the block is. In FX25, that was the function of the correlation tag to identify how long the blocks were, as well as how many parity bytes were included in the block. I use a symbol count or a byte count in the header to do the same thing, but I can specify exactly how many characters or bytes are in the block. Reed-Solomon blocks are composed of symbols, which can be any number of bytes long. For most computer purposes, we choose 8-bit bytes as symbols. and that's what has been chosen for IL2P. The maximum block size for a Reed-Solomon code word, or the size of the code word, is based on the bit width or the size of the symbol. So in this case, an 8-bit byte can represent 256 values. This drives the maximum block size of 255 symbols or bytes for each code word. Those symbols are all treated as finite fields, a special kind of finite field called a Galois field. The capability of a Reed-Solomon code word to detect and correct errors in the code word is dependent on the number of parity symbols that are encoded into the word. Generally, a Reed-Solomon code word can detect a number of erroneous symbols up to half the number of parity symbols. So if a code word is made with 8 parity symbols, then it can recover and correctly decode up to 4 erroneous symbols in the block or the code word. Another characteristic of Reed-Solomon decoders and code words is that the decoder can make erroneous decisions if the number of errors in the received code word exceeds the capability of the code. In other words, sometimes when more errors than half the number of parity symbols occur, the decoder will happily decode, not knowing that that's the case, and present a decoded code word that it thinks is valid, but is actually invalid or still erroneous. So this is the structure of the IL2P header. It's exactly 15 bytes long. In those 15 bytes, there are 2 parity symbols at the end, which allows up to 1 symbol anywhere in the header to be corrupted, and the header still be effectively decoded. A couple things are going on here. I've chosen to use DEC 6-bit encoding for the letters of the destination and source call sign to save a couple bits per letter. There are control and PID fields similar to the AX25 header fields. There's also a bit that tells the decoder what forward error correction level is being applied to the follow-on payload, and the header encoding type. More details can be found about that in the specification that's included in the proceedings of this conference. I also include a payload byte count, which is 10 bits wide, which allows payloads up to 1023 bytes. The source SSID and the destination SSID, analogous to AX25, are only 4 bits each, since only 16 SSIDs are valid. So all that information is a little bit compressed. It's a modified form of a lossless compression so that we can fit more information into fewer bytes than the same information as encoded in an AX25 header. When the encoder creates this header, it will compose all the subfields and put them together in separate bytes. Then it will apply scrambling to all those bytes, and then it will apply the Reed-Solomon encoding onto those scrambled bytes to compute the 2 parity symbols. Then those parity symbols are added as the last 2 bytes. So the payload is encoded in blocks that are each a contiguous Reed-Solomon code word. The data comes first and the parity is at the end. Just like the header, the payload block is assembled of payload bytes, then it's scrambled by a multiplicative linear feedback shift register, then encoded to compute the parity bytes. This removes the opportunity for any of the scrambling to multiply bit errors, and that's described more in my specification paper. There are two levels of forward error correction that can be applied now in IL2P. There's baseline, and then there's max forward error correction. Baseline uses a variable number of parity bytes to maintain about a 1.5% block or byte error rate capability. In other words, correcting up to 1.5% errors in the blocks. And that will allow the blocks to each contain up to 247 bytes of payload. When using max forward error correction, there is a fixed number of parity symbols applied to every payload block, and that's 16 symbols, so every block can correct up to 8 errors, and that means 239 bytes are available for payload. This graph shows the protocol efficiency versus the size of the payload for different protocols. In yellow is AX25, no forward error correction. You notice that at the left, when the payload is 0 bytes long, the efficiency of the protocol is 0. That's because everything that is sent is the header data and no payload. So as the payload gets bigger for all these protocols, efficiency generally increases. The blue line is baseline IL2P efficiency, which you can see is very close to AX25 efficiency, and it starts to drop a little bit as the payload byte count gets bigger, as more and more parity symbols are added to the payload blocks. The green line is IL2P maximum forward error correction efficiency, and that line you can see is a little bit less efficient than baseline efficiency. However, it's still more efficient than FX25. And notably, the FX25 encoding scheme that I'm representing here is the 16 parity byte encoding scheme. In other words, blocks that are up to 239 payload bytes. The significant sawtooth pattern in the red line for FX25 is related to the 0 padding that's required to make up the contiguous Reed-Solomon blocks that are fixed size. So you can see that at certain points, the blocks are most efficient at certain payload sizes. And then that efficiency drops a lot as you add one more byte to the payload because the encoder has to switch to a block size that is bigger. IL2P is more efficient because the header has a payload count that tells the decoder exactly how many payload bytes are to follow, which allows the decoder to apply code shortening to the Reed-Solomon block precisely. So now IL2P is fielded in practical use on about 20 VHF links in the Tarpon network in the North Carolina area. The Tarpon network was founded and managed by Tad KA2DEW, and he and I have been working to implement IL2P on some of those links to see if we can get some real-world experience on how this is working and what it can do. So we started with the baseline forward error correction level and started to find that we ran into limitations on that capability. So we saw some false decodes on weak links or marginal links where erroneous packets would make it through the decoder, yet not be identified as errors. In other words, the error count in those blocks exceeded the capability of the code to detect the errors. And those would show up as basically garbage packets at the next layer. That's what drove the decision to add another mode with more forward error correction capability. And so that's where max FEC came from. We still need to validate the performance cost and benefit. In other words, the cost of efficiency of adding the parity to the blocks. Is it worth the benefit, right? Some ways we could do that is through simulation or by setting up some hardware on a bench and using measured noise injection to create a controlled level of noise and compare that to the packet error rate that we see on the other side. I also think it'd be interesting to experiment with broadcast or beacon applications, such as APRS beacons and things like that, but I have not yet put any effort towards completing that project. So if you've got any questions about IL2P, feel free to contact me at the email address below. I'd be happy to talk to you about that. Also, the IL2P specification paper will be included with the proceedings of the conference. Thank you very much.
Okay, Nino, thank you very much for the presentation. And please say hi to Tad for us. He was with us in Packet Radio in the early days, and glad to see he's still here. There are a number of questions. The first was, does your packet contain, oops, and things are scrolling, does your packet contain TTL and other flags?
So I think TTL stands for time to live. The header doesn't contain a time to live flag. I think that's something that can be contained within the packet payload, depending on the protocol that's being carried. This is, IL2P is think of it as a container to move a packet from one station to another. And then the payload inside the packet is taken to the layer 3, which can do what it wants with that. But I do not have a specific time to live in the header.
Okay, thanks. Then the next question, are there possible extensions to support other FEC algorithms like LDPC or polar codes?
I think that it would be really interesting to experiment with some of those. I don't have the theoretical background in low density parity check or polar codes, but I'd like to learn about that. I have built convolutional encoders and Viterbi decoders and wrapped those around. In other words, transported an IL2P packet over a convolutional code. This is very analogous to what NASA was doing 30 or 40 years ago on its deep space probes. In fact, that's where I learned about some of this stuff. So that's obviously a little bit old tech. I think low density parity check is more modern and it'd be interesting to learn. I'd be happy to talk to someone if anyone's interested in extending it to new kinds of error correction.
Okay, the next question, can IL2P tell the difference between an error in the data and an error in the FEC section of the entire data packet?
So it doesn't need to. When the Reed-Solomon code block is created and decoded, it doesn't care where the error occurs. So let's say the packet's 100 bytes long with 16 parity bytes. The capability will be to correct 8 erroneous bytes anywhere in the packet, even if it's all in the forward error correction section, or if it's all in the data block, or if it's spread out between the two.
Okay, and then there is a conversation going on the YouTube channel that I'm not technically qualified to try to really summarize, but it started with the question of why you're scrambling the payload before you're doing the Reed-Solomon encoding, and wouldn't it be better to do it the other way around? And beyond that, I won't try to go further because there were lots of comments about that.
Yeah, that's a great question. And so if you read the specification of FX25, there's something called out at the end as a recommendation for further work, which is frame synchronous scrambling. And that's what I'm implementing in IL2P because a multiplicative linear feedback shift register, right? Basically the feedback taps on a shift register that create the scrambled data. multiplies bit errors at the receiver at a rate of 1 bit error multiplication per tap. So if you have a 3-tap linear feedback shift register, 1 bit will create 1 erroneous bit creates 3 bit errors. So what I've done is applied the scrambling to the data bytes before the forward error correction. So the decoder can decode the scrambled bytes, get rid of all the bit errors, and then pass it through the receive side of the linear feedback shift register to decode or descramble the data. And that takes away the opportunity for those that method of data whitening to amplify bit errors.
Okay, and I don't think there are any other questions. There is a question about there being no repeater fields. Is that something you may implement in the future?
Yeah, that's a great question. So I was very intentionally stingy on how big to make the header. And it's something that frustrated me about making AX25 encoders and decoders, was that the header was basically indeterminate until you get information to put in it. It could be as long as it needed to be because you can extend call signs with repeater fields and that kind of thing. So I explicitly don't plan to add repeater fields in the header. Now, when, for example, I've implemented the encoder and decoder on a microchip DS PIC on this TNC that I make. And if it encounters a KISS packet that has those fields in it and determines that it can't stuff everything into the ILTP header, then it just puts the entire payload block, the entire packet into the payload block and allows all those fields to exist. In other words, my workaround for not having more fields for repeaters is just to accept lower efficiency when I get those packets and I stick it all in the payload and take a little bit of a hit on the efficiency.
Okay, another question just came in. By the way, there's an awful lot of conversation going on and a lot of kudos for a great presentation here, Dino, so great job. Do you think there will be any support for fragmentation allowing for larger payloads?
So that could be handled at the layer 3 level, right? The payload right now is up to 1023 bytes. It would be straightforward to set a set of rules to fragment a packet. It just gets a little bit more complex and it goes beyond the scope of the problem I was trying to solve right away with the specification as I wrote it.
Okay, I think that is all the questions that we've had. Again, lots of compliments for the speech and also the underlying work that you've done. There is another one. Any advantages to using IL2P versus AX25 for tunneling other protocols like IP?
I'm not sure, other than it depends on what medium you're pushing your other protocol over. So IL2P gives you an advantage if you have a low signal to noise ratio. You're going to reduce the retry rate on that link, right? More packets will get through the first time. So that maybe you'll see a performance advantage. I think that if you're tunneling IP, it would work just fine. You could place the IP packet inside the IL2P packet, just like AX25 does when it's carrying an IP layer 3 packet.
Okay, I think that's all the questions, and we are just about ready to transition over to David Rowe. So I thank you again, Nino. And
thank you. Thanks for the opportunity. This was great. It's the first time I've done a conference like this, and I appreciate the feedback.
Okay, thank you much. And David, welcome. Why don't you give us a brief introduction to your talk, and then we'll start the video rolling.
Hi. Yes, good morning. Oh, good morning for me. Yes, I'm going to be talking about FreeDV 700D and FreeDV 2020. Two digital voice over HF radio modes that myself and a team have been working on for, well, nearly a decade now.
Okay.
Hello, my name is David Rowe, VK5 Delta Golf Romeo. And today I'd like to talk about FreeDV 700D and FreeDV 2020. I'll start with talking about what is FreeDV, and then talk about why you might want to use FreeDV, what's attractive about the project. I'd also like to acknowledge a few of the people involved, and by looking at some of the things they've been working on, you can get an idea for what the project is up to and where we're going with it. There's been some interesting work going on with FreeDV QSOs over Kiwi SDRs, and I'd like to talk a little bit about that and the people involved with that. One of the main topics of the talk is lessons learned with the FreeDV 700D mode. That's been out for a couple of years now, and we've got a fair bit of on-air experience. So we're putting that together and having a think about where we can go next. And I'd also like to talk about the FreeDV 2020 mode, which uses a fairly new algorithm called a neural net vocoder. And finally, at the end, I'll play you a few off-air samples. So what is FreeDV? Well, it's open source digital voice for HF radio. It consists of a voice codec, a modem, and forward error correction, all wrapped up in a protocol that ties it all together. So the way you use FreeDV is through a GUI application that you can download for various different operating systems. Another way to use it is there's a library of C code, which we call the FreeDV API, and that can be linked with other SDR applications. So it's just software that can be linked with other software and will allow you to receive and transmit FreeDV signals. Yet another way to use it is through the SM1000 FreeDV adapter. That's a little embedded box that has all the functions you need for FreeDV in one little unit, doesn't need an external computer. And FreeDV is being developed, being led by myself, but in collaboration with an international team of developers who have contributed over the years. Okay, so why would you use FreeDV? Well, it's at the leading edge of ham radio experimentation. And I'll show you a little bit about why that's so and some of the topics coming up. It has low SNR performance that in some cases is competitive with SSB. So we're starting to get signals through on FreeDV that you can't on SSB. It's a way to get around some of that annoying HF background noise, especially the growing urban noise floor. Importantly, it's a voice mode designed by hams for hams. This is not something that was born in the commercial world and has been pushed back to us. It's something that's been developed specifically by us, for us, our use. We're not locked out by any commercial companies, nothing proprietary, no patents or license fees to worry about. And that's because it's completely open source. In particular, key parts such as the codec and the modem are open source. And this gives you some freedom to experiment. There's no legal barriers, and because it's based on software, there's very few other barriers, and there's a very low cost to entry. Some of the developers that have been actively involved with the project, and this is just over the last 12 months, I'd like to mention Steve. He's done some wonderful work with the OFDM modem that we use as the basis for several modes, and lots of ongoing support. And similar with Richard. Richard works on the build system for FreeDV and Codec 2, which is the software that ties together the software and turns it into something that can be packaged for release on your Windows or Linux machine. Munir has been working very hard on the support for the Mac OS X and also improving some of the tests. Don, he did some great work on porting the FreeDV 700D mode to the SM1000, which is a little running it on a little microcontroller, which is quite remarkable. He does some great work with that, and in particular the automated tests about 12 months ago. Also last year, Brad was very helpful with the FreeDV 2020 mode, in particular modifying the FreeDV GUI program to handle the higher sample rates and various other little details we needed to implement to get the FreeDV 2020 mode going. I've been working with Mark VK5QI for many years. He's particularly interested in high altitude balloons and balloon telemetry. And we've worked together on a few projects with that. That actually employs some of the modems from the FreeDV project, a little bit separate from digital voice, but uses some of the same building blocks. Bill, BK5DSP, I've been working with recently to do some work on forward error correction, and in particular, very powerful FSK modes combined with powerful forward error correction can detect very weak signals. Jeroen has done some great work on data modes for EDV, in particular for VHF, so alternatives to packet. And Jim has been helping out with proofreading, a lot of the documentation, which is very useful, helps share the knowledge and helps improve my writing skills, so thanks Jim. Plus there have been many other people involved, both operators and developers in the decade or so that we've been running, so I'd like to thank you all. Okay, one interesting use of FreeDV is over QE SDRs. So these are SDRs dotted about the internet that you can receive signals on with your web browser. And there's a group of hams in the UK, South America and Australia who have been using these for FreeDV. So they run they listen to the web SDR or the QE SDR in their browser and then connect it up to FreeDV using virtual audio cables. And that enables them to receive the FreeDV signal in areas where maybe they wouldn't normally be able to receive it, say due to propagation, poor propagation conditions, or issues with urban noise. So two people I'd like to mention who are doing some interesting experiments, in fact every night they're doing this, are Jose and Peter. Jose is from Argentina and Peter is from well, about 800 kilometres away from where I live here in Australia, just outside of Melbourne, and they communicate every night using SDRs to bridge the gap between them. It's something like a 13,000 kilometre path. They meet somewhere in between, often, for example, using Auckland, Kiwi SDRs in Auckland, where they can receive each other's signals. They tend to use the FreeDV 700C mode, which is a mode, a little bit of an earlier mode we developed due to the polar path. And I'll talk a little bit about why that is in one of our lessons learned slides later on. They use fairly modest power, just 40 watts and modest antenna systems. And it's important to note these are daily rag chew conversations. They're not shouting your call sign 5 times and reporting 5 by 9 and calling in a contact. These are casual conversations on pretty low power over long distances, augmented by the Kiwi SDRs, of course. So pretty cool use for Kiwi SDRs combined with FreeDV. So a bit of a roadmap about where we've been. The project was started over 10 years ago when we pushed Codec 2 out there into the wild. And since then, there's been a succession of these FreeDV modes, which, as I say, combine the codec, the modem, and some forward error correction, in some cases, to develop a mode you can use over the air. In particular, over the last 3 or 4 years, we've been releasing around about 1 mode a year, starting with FreeDV 700C 3 years ago. That was the first modem to use QPSK. And then we went to 700Z, which we applied forward error correction to. So they're the two I'm going to focus on in a little bit. And the idea is that we gradually improve the quality as we go over time in various ways. So I'd like to talk a little bit about FreeDV 700C and 700D. As I said, 700C came first, and then there was some lesson learned. We applied some more techniques to develop FreeDV 700D. Now they both use the same 700 bits per second speech codec. So under good conditions, they'll sound exactly the same. Where they're distinguished is how we handled the modem and the forward error correction and how they perform over different channels. FreeDV 700C doesn't have any forward error correction, but it does have something called transmit diversity. So we transmit the carriers twice at 2 different sets of frequencies. And the idea is if one set gets wiped out, say by frequency selective fading, we'll be able to pick up the signal on the second half. So that's one way it's made robust to fading channels, this transmit diversity, two copies of the transmit signal. FreeDV 700D uses another approach, excuse me, where we transmit, we use forward error correction to protect the data. So we send extra bits that help correct any errors that might occur over the channel. So that's a more traditional forward error correction type approach. They both deliver low to moderate voice quality. It does take a little bit of getting used to. However, so does low SNR SSB. So once you're used to it though, it sustains conversations quite well and people use it reasonably naturally. We've got a fair bit of on-air experience now, and we've got a feel for where one works and the other doesn't. And it turns out that FreeDV 700C tends to work a bit better on very fast fading channels. So when the fading is changing very fast, like several hertz. And that was also brought home by the work that Peter and Jose were doing when they were talking between Argentina and Australia, because the signal was going over the South Pole, which tends to have very fast fading. So they tend to focus on using 700C. However, 700D appears to work better for slow fading and low SNR. Because it's got that powerful forward error correction code, it's been optimized for very low SNR channels. So it'll go lower in terms of signal to noise ratio, down to perhaps -2 dB than 700C. But when the fading picks up, it won't do so well. So that was a bit of a surprise to me, because I thought 700D would be a lot better. But turns out this is experimental radio. We make a few steps forward and a few steps back. So they both have their pros and cons. And by studying the use of these and using them on air and collecting a few examples, we can use those lessons learned to help push the technology forward. So I'm now thinking about developing a new mode from the lessons learned. And I guess one principle I've got is that multipath, that HF channel, is much harder to deal with than low SNR. So the general principle here is to deal with multipath first, low SNR second. The other principle I learned by comparing the two modes is that small frame sizes tend to be a bit better in terms of sync, because they can acquire the signal much faster. When you lose data, you don't lose as much information. And you also get lower latency, so the delay in the signal is less, which is nicer for sort of push-to-talk type modes. FreeDV 700C has a latency of around 40 milliseconds, so we call it a 40 millisecond frame size. And 700D has a latency more like 160 milliseconds. And the reason we use such a long frame for 700D is that the forward error correction codes like big blocks of bits. They work a lot better when there are larger blocks. And as I said, 700D uses forward error correction, whereas 700C uses a transmit diversity scheme. So I'm thinking about going towards smaller frame sizes as well for higher performance. However, the FEC does work quite well, the forward error correction, so we'd like to keep that in some form. So looking towards a bit of a combination of the two modes. I'd also like to improve the speech codec in time, but that's pretty tough at low bit rates. Modems are a lot more easier to work on because, well, it's a lot harder to compare speech quality than it is to compare a bit error rate. There are some more advanced techniques that we can use to improve speech quality, and one of them is the use of neural nets, which I'll discuss in the next mode. Okay, LPCnet. This is pretty much a breakthrough in speech synthesis that was pioneered by Google a few years ago. It uses something called machine learning and deep learning. It was first applied to speech coding in 2018 by a team by Google. And this approach, however, was closed source and very high CPU load. It required a GPU card, the sort of card used by high-end gamers to run the actual algorithm. Enter Jean-Marc Vallin, a Canadian open source developer who I've been working with for some time. He invented a new neural net-based speech synthesis system called LPCnet. And two important properties that make it useful for us is it's open source, which means we can use it and develop and modify it. And it's also very efficient. Jean-Marc managed to make it get to run on high-end x86 CPUs. So that means it's now within the reach of a lot of people without a specific gaming card. And I've been applying LPCnet to FreeDV. I took Jean-Marc's algorithm and worked out how to quantize it and added some forward error correction and get it over the air so we can use it. And that led us to the FreeDV 2020 mode. That uses LPCnet quantized to 1700 bits per second. I added to that some powerful forward error correction. A code was developed by Bill, VK5 DSP, to handle that. And we used Steve's modem, the OFDM modem, the same one we used in 700D. That's very efficient in terms of bandwidth, so we just modified it to work on wider channels. Now this is kind of unique in voice modes in that it's 8 kilohertz wide audio bandwidth. So it's like AM or AM radio in terms of the bandwidth of the audio. Brad helped out quite a lot with modifying the FreeDV GUI program to handle that wider audio, as all the previous modes just dealt with 4 kilohertz wide audio. Now the neat thing about this, despite the fact the audio is 8 kilohertz wide, it fits in 1600 hertz of RF bandwidth. So it fits in less bandwidth than a regular SSB QSO. It's available in FreeDV now. You can download it and try it anytime you like. And it may be the first application of a neural net vocoder on air. So we've got ham radio leading the pack here. As far as I know, there's still nothing like it in the commercial or closed source worlds. So I'd like to demonstrate FreeDV 2020 now. I'll play some original source material, and then what that same file would sound like over an SSB channel at around 10 dB SNR. Then I'll play what it would sound like on FreeDV 2020. This is in a channel with no errors, but it gives you an idea of the best case speech quality. It's quite experimental. It's not as robust as, say, 700Z in terms of bit errors. However, it works pretty well. And one of the things we've discovered is it works on about 90% of voices. Because of these machine learning algorithms tend to be trained, some voices they work on and others they don't so well. But it's out there, experimental and ready to use. So I'll go across to the demo now. Okay, so first we'll play the original source material.
From Australia, this is VK1WIA.
And now what that would sound like is SSB.
From Australia, this is VK1WIA.
And now the LPC net vocoder.
From Australia, this is VK1WIA.
So I'll just play those again first. The SSB.
From Australia, this is VK1WIA.
And now the new vocoder.
From Australia, this is VK1WIA.
There you go. And there's some more samples if you'd like to listen to them that I'll include in the package of files for this presentation. Okay, now on to the FreeDV 700D demo. I've got some files here that Walter sent me over the weekend. Thank you, Walter. He was in a QSO. It was a pretty poor conditions, Walter reports. And this is an example of a channel where FreeDV 700D worked, but Walter found it difficult to have a conversation with SSB. So I've got some examples of files Walter recorded with FreeDV 700D and with SSB at roughly the same time. So first of all, the decoded 700D signal. This is what it sounds like coming off the air.
WH, W4VCX, Roger. Ray in Melbourne, Florida. Your SNR here is very good, about 18. Although the signal strength is not that strong. The signal strength S7, S8, the SNR is running at 18. So how copy?
Okay, and now what the SSB sounded like. I'll go back to the FreeDV 700D.
WH, W4VCX, Roger. Ray in Melbourne, Florida. Your SNR here is very good, about 18. Although the signal strength is not that strong. The signal strength S7, S8, the SNR is running at 18. So how copy?
And the SSB one more time. Now that SSB sample is very hard to understand. There's some impulsive background noise that was being picked up, but as well as the SSB signal, but it does demonstrate the ability of FreeDV 700D to ignore those sort of signals and still decode speech. Okay. So what are some reasons you might not want to use FreeDV? Well, one problem is who can I talk to? There aren't too many FreeDV users out there. There are, however, some tools that you can use to find them, such as the FreeDV QSO Finder, and some mailing lists that can be used to coordinate QSOs. Some people experience difficulty in setup. You do require 2 sound cards and a little bit of fiddling. This is an experimental mode. It's not DRM. It doesn't come on a chip in a HT. There's a little bit of work to get it going. It is constantly evolving. I'm always pushing forward. I like the experimental side of ham radio, but very happy to work with other people who want to do the polishing and you know, work on GUIs and make things easy to use as well. Just my particular interest happens to be the experimental side. There's very little commercial support, except I believe Flex supports an earlier version of 700C. So you typically need to use it on a device like a laptop or the SM1000 connected to an existing radio rather than it being built in. Some people complain about the speech quality, but as I said, what we've found in practice is once you use it for a while, it's quite, it becomes quite acceptable when you get used to it. And there are quite a few people of the general public who would complain about the quality of SSB as well. The development environment is Linux, certainly over Windows. So all the development gets done on Linux. And if people want to work on it and develop on it, that's the preferred way to do it. Some of the technologies we employ, there's an open source low bitrate speech codec. We have coherent OFDM, QPSK, HF modems. There's an FSK modem with pretty much ideal performance against the theoretical curves. We've got powerful LDPC forward error correction, which once again approaches some of the capacities that are possible. Neural net speech coding. It's cross-platform across a variety of operating systems, including Raspberry Pis and microcontrollers such as the STM32. A lot of the development is done on GitHub, and we have around about 100 automated tests that run on using the Travis system that test the software every time anyone modifies anything. And some of them even run on a small STM32 platform to make sure the code doesn't break and keeps working. When I build Windows code, I do it on a Linux box using a technology called Docker, which basically runs a Fedora Linux instance that runs the Windows cross compilers to build the Windows version that some of you may be using. And it's all open source. Okay, just as an example of the sort of things I'm working on today, I like home brewing in the physical layer. So that means making modems work really well. That's what I'm playing with a lot at the moment. I like open source and pushing the bounds of physics rather than being stuck by commercial barriers that might be put in front of us. One of the projects I'm working on at the moment is a system to do IP over VHF and UHF urban links using just a Raspberry Pi and an RTL SDR. And I've got a couple of blog posts up about that. Another project I'm working on are some taking the modems we're using for digital voice and converting them for HF data for applications like WinLink. And that's that project coming along okay. And we've got some quite competitive bit rates and performance under development, all open source. I've done a little bit of work with Bill, VK5 DSP, on some 4FSK modems combined with powerful forward error correction. And they work very well with weak signals. We recently sent several hundred bits per second across a 15-kilometer link using just 25 microwatts of power because these modems and waveforms are so sensitive. And quite a few more mundane things like planning FreeDV modes and working on FreeDV maintenance. So just to summarize, FreeDV is open source digital voice. The 700D algorithm is moved to the point where it's, in some cases, outperforming SSB at low SNR. We also have the 2020 algorithm, which was released last year, which can send 8 kilohertz wide audio and just 16 kilohertz of RF. And there's a couple of URLs if you'd like, and now I'd be happy to talk about some questions.
Okay, thank you very much, David. And I'll just start off with one of the comments right after the 2000 demo was wholly deleted expletive. And there have been quite a number of comments streaming in the last couple of minutes, so I have to scroll back here to try to find them all. First one, are the different ports, and I think he probably means modems, compatible with each other? Is there auto detection for what is being used?
No, they're not compatible, and there's no auto detection. They do become quite easy to recognize after a little bit of use, however.
Okay. Next, are there patent IP issues with LPCnet?
No, it's a ground up development of a neural net codec. So although it uses broad some things are broadly in common. The specifics of the algorithm are unique and open source, thanks to John Mark's kindness.
Okay, will LPCnet use a GPU if you have it?
No, not in normal operation. However, it is used for the training. So if you're going to do development and train your own neural nets, then you need a GPU.
Okay. What's the minimum compute requirements for LPCnet? Can it run on a high-end Raspberry Pi?
Won't run on a high-end Pi yet. That's probably possible if someone wants to do some porting work. It requires AVX instruction set on an Intel computer, and FreeDV automatically detects that and will let you know if you can run it or not.
Okay, then question, could you please explain in more detail the need for the sound cards?
There's quite a lot of information in that in the FreeDV user guide, but basically you need one sound card to hook up to your radio and another sound card to hook up to a headset, like the one a lot of us are wearing today.
Okay. I think there's a huge amount of commentary going on here, but I think we've caught all the Zoom questions on the YouTube channel. Let's see. I think there's a question about an RPi handling FreeDV. You've already answered that. Is the SM1000 firmware being improved over time? And if so,
Yes.
is it field upgradable?
Yes, it is field upgradable. I think we've released 3 releases in the last 12 months for the firmware.
And then another from YouTube. Is there any plan to implement part of 2020 on FPGA?
I'm not doing any work in the area. There was another group of hands talking about working on that, but I'm not sure where that project is at.
Okay, how do you think the quality compares to AMBV2 from D-Star and DMR?
Codec 2 would be a little bit behind. FreeDV 2020 would be a long way in front.
I think that is all the questions that we have at this point. But again, lots and lots of conversation and lots of kudos for the work that you're doing, all the great advances.
Great, thank you.
Okay. So George, do we want to queue up our next presentation or wait until the top of the hour?
Well, we can bring Dave on to introduce himself and such.
Okay. Our final presentation today is David Garner, N6WY, who will be talking about forward error correction and pictures from Mars. David, why don't you introduce yourself?
Hi. Okay. Well, thanks. Well, what I want to talk about is when I started doing research on this project, I was really looking for what makes the HF digital mode Oliver work. And it's, when I started doing web searches, oh, by the way, Oliver is, I said Oliver, Olivia. Olivia is a low signal keyboard to keyboard chat mode. And when I started doing web searches for Olivia, I found a lot of information about the Mariner 9 spacecraft, which is the first man-made object to orbit another planet. Reason why Mariner 9 kept popping up all the time, it uses the same forward error correction technique that Olivia uses. So one problem I had with the papers on Mariner 9, it was heavily loaded with mathematics, a lot of strange equations. And I wanted to show how forward error correction works without using complicated math equations. So that's what my talk is about. I do not have any pictures to show of the Mars surface because of time limitation. So why don't you start the video and I can answer questions later. Good afternoon. I'm Dave Garner, N6WY, and I'm going to be discussing forward error correction.
I am going to talk a little about the different type of forward error correction codes, and then I'm going to explain how the Hatterman forward error correction code works. The Hatterman code has been around for a long time. However, today it still has many applications. I have two examples. One is a very simple example, and the other is the actual code used for the Mariner 9 spacecraft to transmit pictures of the Martian surface back to Earth. Mariner 9 was the first Earth-made object to orbit around another planet. Forward error correction, or FEC, reduces errors in poor communication link. FEC is useful when there is no reverse channel available to request retransmissions or for a one-way broadcast. FEC is achieved by redundant encoding of data. The bit errors may occur anywhere in the encoded data. The maximum number of errors that can be detected is determined by the design of the FEC. With FEC, you do not get something for nothing. The major cost for adding FEC is increased time and or bandwidth to send the data. FEC types can be divided into two categories: linear block codes and convolution codes. I am going to be talking about the Hatterman code. The Hatterman code is also called the Wash code and the Wash-Handeman code. The code words for encoding the data words are the rows of the Hatterman matrix. What is a Hatterman matrix? Mathematicians like to show Hatterman matrices as a square matrix with ones and minus ones, as in an 8x8 matrix shown in this slide. The thin lines shown in this matrix are construction lines that I use to make this matrix from a 4x4 Hatterman matrix. The two upper quadrants and the lower left quadrants contain the same 4x4 matrix. The bottom right quadrant contains the same 4x4 matrix, except every entry has been multiplied by a -1. To make a 16x16 matrix, I first draw the construction lines. I then put the 8x8 matrix in the top two quadrants and the lower left quadrant. I then multiply every entry in the 8x8 matrix by -1, and I place that 8x8 matrix in the bottom right quadrant. My paper shows how, by starting with a 2x2 Hatterman matrix, you can build a 4x4, 8x8, 16x16, and so forth. The matrices shown on this slide have a Hatterman order equal to 8. Hatterman FEC requires a matrix that have an order divisible by 4. The length of the data word that can be encoded is determined by the Hatterman order. The data length is equal to the exponent of 2, such that when 2 is raised to that exponent, the value is equal to the Hatterman order. For the matrices shown on this slide, the length of the data word is 3. My simple example that I'm going to discuss next uses data words that are 3 bits long or a data values in the range of 0 to 7. Each row of the 8x8 Hatterman matrix is a code word for a 3-bit data word. Now, computers like to work with ones and zeros. You can make a Hatterman computer code words by changing all of the -1 in the Hatterman matrix to zeros, or change all of the -1s to ones and all of the ones to 0 as shown in the two right matrices. In my simple example, I am going to use the top right matrix for encoding 3-bit data words. While I am on this slide, I want to talk about Hatterman augmented code. By putting together the two right matrices and making a 16x8 matrix, you have doubled the number of code words. Now you can forward error correction to a 4-bit data words that have a value in the range of 0 to 15. When a 4-bit data word has a 1 as the most significant bit, you use the top half of the 16 by 8 matrix to encode the data word. And when a 4-bit data word has a 0 as the most significant bit, you use the bottom half of the 16 by 8 matrix to encode the data word. You will not increase the error correctability of the encoded data word, but you can increase the size of the data word by 1 bit. The black and white matrix is just another way of showing the pattern of the Hardeman code words. I guess if you're on top of a mountain using black and white smoke to send 3-bit data words, you can use this matrix to add forward error correction to your smoke signal. For my simple example, I am going to use an 8x8 Hardeman matrix. This is not a very practical example of FEC because an 8x8 Hardeman matrix will only give a correctability of 1 bit error in the code word. In this example, the broadcast station will use the same code word 4 times. From the encode table, the data word for 3 is 011, and the code word is as shown. In this example, I am using the same data and code 4 times to make it easy for you to follow. On the receive end of the broadcast, there is a problem with the receiver causing a few bit errors. The first receive code word has 0 errors. The second receive code word has 1 error. The third receive code word has 2 errors. And the fourth receive code word has 3 errors. After receiving the code words, our agent builds a decode table. The rows of the Hardeman matrix, or the code words, have the same assignment as the encode table used by the broadcast station. The RCW0 column is for the first code word. Our agent gives 1 point for each time it has the same bit value in the same position as a row in the Hardeman matrix. The row with the highest score identifies the data value. Our agent completes the decode table for the other received code words. Based on the decode table, our agent knows that the first 2 numbers for his mission is 33. The decode table for this simple example does not work for 2 or more bit errors in the received code word. For the third received code word, RCW2, there are 3 high scores. Our agent knows about FEC, and he knows that the FEC code that is being used can only correct 1 bit error, but can detect 2-bit errors in the received code word. Our agent also knows that the mission that have 335 and 336 as the first 3 numbers are for Chicago agents, and he is in Portland. So using deduction, he knows that the first 3 numbers for his missions are 333. For the fourth received code word, the decode table does not give any indication that the code word has 3 or more errors. In fact, the decode table indicates that the last received code word has only 1 bit error and the last number for his mission is 5. So our agent prepares to complete mission 3335. Oops, wrong mission. For the Mariner 9 example, you need to know that the picture data are split into a string of 6 bits data words. NASA engineers calculated that the maximum length for the FEC code word was about 30 bits. An option was to use a 5-repeat code for FEC. This slide shows what a 6-bit data word becomes with 5-repeat code. NASA wanted an FEC code that could correct more than 2-bit errors. NASA selected an augmented Hadamard code that would correct 7-bit errors per code word. Two other factors in favor for Hadamard code. Factor number 1, no memory required for encoding on the spacecraft. In the late 1960s, using the state-of-the-art memory and processor to store an encode table and do a lookup was not practical. Logic circuits wired together was used to calculate a transmitted code word from a data word rather than read it out of a stored array. Factor number 2, a NASA engineers with the last name of Green made the Green machine that would rapidly decode a Hadamard code words. I cannot find any information about the Green machine. This slide shows all the data words and code words used to transmit pictures of the Martian surface. The left side shows all the data words that have 1 for the most significant bit, and the right side shows all the data words that have 0 for the most significant bit. Put the two together and you have a 64 by 32 augmented Hadamard code. For the Mariner 9 numeric example, I have selected 2 data words. The only difference between the 2 data words is the most significant bit. I use the color blue to indicate transmitter and receive code words associated with the data word having 1 as the value for its most significant bit, and green to indicate the transmitter and receive code word associated with the data word having 0 as the value for its most significant bit. The receive code words alternate between blue and green. The color red indicates bit error in the receive code word. I said earlier that Mariner 9 did not use a table lookup for encoding and decoding the data words. But I am going to use the same technique that I used in the simple example to illustrate how effective a large augmented Hadamard matrix can be used to select the correct data word when using a bad communication link. I can only show on one slide segments of the Mariner 9 decode table. The first 2 received columns have 0-bit errors, and you can find the score 32 for the high scoring code word, and in the same row, the correct data word. For a received code word that has a single bit error, the high score is 31, and it is the same code word that has this code score of 32 with 0-bit errors. Moving on over to the received code word column that has the high score of 25 for 7-bit errors, you can see that it is the same code word that had a score of 32 with 0-bit errors. You can see a pattern that when a bit error increases by 1 point, the high score drops by 1 point, up to 7-bit errors. I should mention that when you are scoring the code words, if you get a score of 25 to 32, you can stop looking for a higher score. For example, as you start filling in a column and get a score of 26, there will be no score higher than 26 in that column, and you know that the code word has 6 errors. When you have 8-bit errors in a code word, you're going to have 4 code words with a high score of 24. You cannot determine the correct transmitted code word, but you will know that you have 8-bit errors. If you receive a code word having an average of 8-bit errors per 32 per code word, then your BER is 25%. BER at 25% is a very bad communication link. With 9 or more bit errors in a received code word, the decode table will give you an incorrect data word. FEC gives you the capability of determining the quality of the communication link while you are receiving data. For a set time period, you have information about the number of errors detected, and you know the number of bits received, so you can calculate a BER. I hope that I have illustrated to you how the Hatterman FEC improves data transmission over a bad communication link. I have made a few QSOs using the HF digital mode Olivia. Some of my QSOs I could only hear noise from my receive speaker, and the waterfall showed no signal present. My computer said that the SNR of the receive signal was minus 14 dB, but I was still able to have a solid QSO. I started searching the web for information about Olivia and how it worked. I did not find much information about Olivia, but I did find a lot of information about Mariner 9. I decided to write a paper and to prepare a presentation about FEC using Mariner 9 as an example.
Okay, David, you can turn your video on. And
okay.
At this point, we're open for questions. I don't think I see any right now, although there was at least one compliment for how clear that explanation was. So people appreciate it. And another comment about the great explanation. But we can leave it open here for a couple of minutes for anybody who has questions, please.
I might make a comment about what NASA said about it's a non-technical source I found, and they said that without this forward air correction, 26% of the pictures would have errors, and I guess that means unusable. After they put the forward air correction in, 0.01% had errors. So it's a significant improvement for sending pictures back from Mars.
Very interesting. Okay, a couple of comments. Someone commented they weren't aware of the Olivia heritage with Mariner 9. And then Mel on the YouTube channel pointed out that Olivia was named after the author's daughter. That's where the name of that code came from. From Phil, Hadamard codes are pretty old, but very easy to understand. They're also useful for M-ARRI orthogonal modulation.
Yes, and I also found a reference, I can't find it again, but a century and a half ago, the electrical engineers were using Hatterman matrices to lay out cables so that it minimized the crosstalk in the wires. And I wish I could find that reference again, but it's escaped me. But they still find many uses for the Hatterman matrix. And in my paper, I reference a source that gives all kinds of new uses for the Hatterman codes.
And Phil comments that he had heard the story about using it for the wires when he was at Qualcomm.
Oh, I used to, well, when it was called Linkabit, I used to go down there and have meetings with Qualcomm. It was Linkabit at the time.
Okay, well, Steve, I'm not seeing any further questions. So I think we're wrapped up here. I'll hand it over to you.
Okay, Dave, thank you so very much for your paper and your presentation.
You're welcome.
And thank you for taking the anchor position of the talks. Every time we put the schedule together, somebody's got to be first and somebody's got to be last, but everybody's equal. So thank you.
Well, at least this time I didn't have to worry about people leaving early to go catch the plane.
Yeah, there is that. And you did get a lot of compliments on the chat room there too. So, and of course, as we will do with all the talks, well, as soon as we terminate here, your talk will be up on YouTube, so you can send your friends and family over there to watch.
Okay.
All right, Dave. So thank you again. So for everyone, I want to thank the TAPR board and officers for all their hard work. They were the ones who put in the time, the planning, the practice, and you have experience now what we call the virtual DCC, the very first of its kind. And this is the 39th annual DCC. And of course, we're keeping the tradition alive. We also had kept the tradition of having a proceedings, and we've advertised where you can download the proceedings for PDF form, free to you. And of course, if you would like a printed version, you can order it for cost at $9 plus shipping. So if you would like a printed copy to go on your shelf. Okay, well, I'm not for big, long goodbyes, but with a tear in our eyes, we will close what we call basically the presentations and the talks for the DCC. Give us about 5 minutes and we're going to reconvene on the Zoom channel, the TAPR annual meeting. We hope that you'll join us and we'll give you a quick status report of TAPR and how it's doing, and then open it up for questions and comments to you. So let's give you about 5 minutes to recuperate there, and we'll join you for the annual meeting. Thank you, 73s.
And by reconvening on the Zoom channel, Stephen means sit in your seat, stay right here. It'll be right here.